Go for it. Just kind of free-form discussion. That's cool.
We are live now. Welcome to APEC. We're just waiting here in the pre-conference session, waiting for Kevin Knuth to arrive. He'll be our first speaker. If he doesn't get here in the next 5 minutes, we'll go to Tony Robertson and then come back to Kevin. But I wanted to have a little bit of discussion here. We were just kind of talking before I hit the live button. I wanted to recap some of the stuff we were talking about. One of the things I had mentioned was the Galileo project, which is, of course, has a scientific advisory board, and they're going to be getting telescopes for Harvard to go and look for UAPs. And I think that this ties into our first speaker's talk on the physics of UAP, because we're going to talk about some of the ideas of the physics of how these craft might be operating, and of course how that might affect our abilities to observe them with classical optical instruments. There's of course if you look up there's a lot of stuff that you guys should tie into this, non-classical light, also Terahertz Gap, that these things might be operating within a range which we currently don't have sensors to detect. The terahertz gap is a frequency band in terahertz region of the electromagnetic spectrum between radio waves and infrared light, for which practical technologies for generating and detecting the radiation do not exist. So if these things are using optical cloaking, and we'd have to basically build terahertz gap sensors to be able to potentially see them. I wanted to see what other physicists have to say about this this feasibility and the optical engineering of that. But anyways, it might be impossible to detect them currently with our current instruments. Whatever they are detecting and seeing. This is weird because it ties in. I don't know if you guys know who T.D. Barnes is. I interviewed him the other night on my channel, and he is a former special projects manager out at Area 51, and he did a lot of work on electronic countermeasures out there. And I asked him if about the anti-grav that claim. Cosmic Cat says U.S. has had anti-gravity since the end of World War II, and that they got it from Germans and other places. According to T.D. Barnes, they didn't study the anti-gravity out at Area 51. If it was developed other places. Again, I don't think that he seems to think that a lot of these UFOs that pilots are seeing are actually our own technology. He said that he's 100% positive that these are all our own technology and can be explained with present day off the shelf technology, stuff that he knows about, having been exposed to it and been involved in research out at Area 51 for years. He claims that they have not cracked gravity yet. Again, we're going to be talking to Tony about that too, because he's been one of the pioneers in a lot of the research that's been going on into anti-gravity, and I definitely want to get his opinion on that whole guess that we had already developed anti-gravity after World War II, and that they've had it somewhere and kept it secret. I think that there's I don't know. I think that if we did, then this conference would have been over months ago, and we would have gotten somewhere with somebody being like, "Hey, this is just how to do it. This is, here's some documents, or here's something."
I mean, the documents is not the issue. We've had lots of documents.
Sorry, guys. Let me jump in real quick. So Kevin just emailed me. He's dealing with a family emergency. He said that he can be here in just about 1 hour. So that gives us an hour to fill. So we could either go to Tony, or I had a presentation on the UAP nuclear correlation. It's up to you guys.
I was going to work on this,
And that might fit better with Tony later.
Yeah,
That was what I was
yeah.
thinking.
So maybe you could start with your UAP.
Okay. Okay. Well, let me do that then. Let me do that. I'll pop open my PowerPoint real quick. And I think you guys have already kind of seen this. And so I'll do just kind of a conference introduction. I owe everyone an apology for the disconnected nature of today's event. Maybe it's the flu shot threw my psychic mojo off. But
You heard that. It's all Tim's fault, so all blame can go to him.
It's my fault. Yes. I'm having a reaction to the flu shot today. So okay, so let me do that. So I'm going to mute everybody else out, and then I will start with the intro. Okay, and I'll start in 3, 2, 1. Welcome to APEC. It's August 28th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Kevin Knuth is going to be discussing UAP flight characteristics and physics. I will be discussing the UAP nuclear correlation. Tony Robertson will provide a historical overview of NASA's superconductor gravity control experiment. And Kenneth Griggs will explain his model for quantum electrodynamics and Phoenix theory. We're also going to have some updates from Mark Sokol and Jeremy Reese on the recent Tesla Tech 21 conference. And we are hoping to have some live superconductor experiments from Mark, who is joining us from his lab right now. So this is going to be an exciting conference. We have a little bit of a change up. We were going to start with Kevin Knuth, and I am expecting him in just about 1 hour. So I am going to launch right into it with a presentation that I've been working on UAP nuclear incursions. So I'm going to jump right in there. I'll share my screen. Okay. And yeah, there we go. Okay. And hopefully you guys can all see my screen okay. So UAP nuclear incursions, 1945 to present. And I guess just ping me in chat if you guys have any problems seeing the screen or anything like that. I know I have everybody muted out, and it is a little odd the way this thing is set up. So let me preface this presentation by saying, so this comes out of something I'd read from Luis Elizondo, right, the AATIP program. And so I started researching this a couple of weeks ago. I didn't think I'd find very much. What I found actually is pretty amazing to me. So I'll just kind of take it with there. So, okay, so UAP nuclear incursions, 1945 to present. The UAP nuclear congruency. Luis Elizondo said that UAPs have been observed at US nuclear sites as well as at sites all over the globe. Quote unquote, there does seem to be some sort of congruency or intersection between the UAP UFO sightings and our nuclear technology, whether it's nuclear propulsion, power generation, or weapon systems. And he also said that the observations have been made in other countries. They've had the same incidents. And so that's telling us that this is something that's global and not just a US strategic concern, I guess. He also indicated that there have been incidents where UAPs have interfered and brought offline our nuclear capabilities. So that was quoted in the Washington Post. Let me see. And then it also went on and said, he said in other areas, we also have data suggesting that these things have interfered with their nuclear technology and put them online. So there's enough data to demonstrate that there's interest in our nuclear technology and a potential to interfere with it. So that's kind of what got me started with this. I had read one of those quotes, I found the other. What you'll find is with the AATIP program, with Elizondo and Mellon and others, these are kind of scattered throughout there. They'll mention this nuclear congruency. And so I said, well, okay, heck, why don't I get started? I'll see if I can find something for that online. I just started with Google. You can start there. So do nuclear facilities attract UFOs? Again, I found some interesting quotes here. The answer about whether nuclear facilities attract UFOs appears to be yes. There's an excess of 3,051 UFO reports for nuclear site counties above would have been predicted based on non-nuclear counties. So there's an excess of 568 close encounter reports over what should have been expected based on other UFO reporting dynamics. So this is based on QFON. What they had said was, what we're finding is this is troubling. UFO reports happen more frequently in the vicinity of nuclear sites after you control for population and region and all of the other stuff. They don't know why. They just, they indicated that that's what's happening. So they'd also mentioned that, given that the events of September 11th drew attention to the vulnerability of nuclear power plants and terrorism, they suggested it would behoove national security agencies to redirect and focus a little bit more on this issue, right? I mean, something's happening here. We're not sure exactly what. We should probably look at it. The other one that was kind of interesting, and this has been thoroughly documented, UAP nuclear naval incursions. So this comes out of Tom Rogan and again, Luis Elizondo. I just wanted to kind of cover this because this is what brought this whole attention back to the limelight, even though it's been done to death. Tom Rogan had said, as I reported, the Navy is front and center for a simple reason. This is a quote. Its nuclear platforms keep attracting UFOs. UFOs tend, since the late 1940s, to appear near military nuclear weapon sites and nuclear-powered platforms, such as aircraft carriers and submarine forces. The potential threat is that UFOs can detect and intercept these platforms on land, sea, or undersea with impunity. The undersea part is interesting. I think that's something that's kind of coming more to light very recently. We're starting to get these stories about that they're not called UAPs. I believe they're called USPs. They're undersea objects that are encountered near submarines by submarines, right? Starting to get a little bit of publicity there. So Luis Elizondo had said, when you look at all the naval ships out there, like the Nimitz battle fleet, you're talking about a nuclear footprint that's bigger than most cities. The point that he's making is these things generate a lot of power, right? So they have a big footprint. And then in addition to that, you've got nuclear powered submarines that have nuclear weapons on board, as well as a nuclear power plant, a lot of other capabilities. And so he's saying maybe it shouldn't be surprised that there's an increased interest, because it's high tech, there's a lot of energy, there's some weapons potential, things like that. So let me jump into kind of notable events. This is, again, I just hit Google to start out with, and hopefully I'll be able to play some of these. Okay. So I do have links here. So the Fukushima nuclear plant in 2019, this was a YouTube video by Mavix, shows 5 unidentified flying objects hovering above the Fukushima nuclear plant. The video uploaded revealed that the strange footage was shot on August 20th, 2019. 5 UFOs with glowing lights can be seen moving eerily in the skies. It's unclear whether these are different from flying ships or multiple lights from a single ship. Let me see if I can play that. And guys, I guess just let me know if we run into issues with this. Just ping me in chat if you can't see it. Okay. And I'm not going to go too in depth here. Hopefully you guys can see this. My Zoom bar is getting in the way a little bit. I'm going to fast forward. So again, if you look up, Fukushima UAPs, this is about a 10-minute recording. You can see these lights in the sky. And again, I'm fast forwarding through here. They're not doing a heck of a lot. They are just kind of hanging out over Fukushima. And I believe this is actually a different event in Tokyo. In fact, I'm positive it is. So we do have our lights in the sky there. Okay, so let me go back to my PowerPoint here. Okay, so that was the Fukushima nuclear plant, just one example. The one that really got me, this video I'm excited to play for you, is Veracruz nuclear plant, UFO video from Laguna Verde nuclear power plant, 24-year-old nuke owned and operated by the Mexican government, shot with a cell phone camera on November 5th by an engineer. So let me play this. This is the one that I've been showing off to people for quite a while now. And I may have played this on APEC in the past. Okay. So hopefully you guys can see this object pretty well. To me, this reminds me a little bit of the outline of the Navy UAPs. That's kind of what got me. And let me see. Oops. Sorry, I paused it there. Okay, sorry, I just muted everybody out again. And yeah. So again, this video for me was very, very interesting. Okay, let me minimize that. Okay, so again, that was Veracruz. That was 2014. It had a resemblance to the outline, at least to my eye, of some of the Navy UAP videos, right? And again, right near a nuke plant, different people have offered explanations. Somebody suggested it was possibly a drone, but to me, it doesn't really look like a drone. It looks more like the UAPs the Navy recorded. So these I do not have video of, but French nuclear power plants, the same year, 2014, according to Austrian news site, there were 18 separate occasions that UFOs were seen flying over nuclear power plants in France between early October and early November. The incident was announced in early 2015. Nuclear power plant in Nogent-sur-Seine, probably not pronouncing that right, southeast of Paris, reported that 2 security guards saw 2 flying objects. At first, they thought that these objects were drones flown by anti-nuke activists, but they haven't been able to track them. So a director of one of the plants, after this hit the news, he came forward and expressed the opinion that the drone wasn't what flew over his nuclear power plant. Pascal Pisani, he addressed the drone issue, stating, "Here, we haven't seen a drone. We saw a UFO, and there was no impact on the safety of our sites. Our position is clear. When there's an overflight of the site, we complain, we communicate." And the reason is, in France, I believe there's like a 5-kilometer radius for any flying vehicles around there. So, so any kind of overflight there is actually in violation of their law and gets reported. Okay, so going back in time, you guys may have noticed I'm going backwards, not forwards. So we start with the more concrete stuff. We're starting with videos, and we're kind of going back into the mists of history. War and Air Force Base, 2010. To me, these are kind of interesting because we haven't heard a lot about these Air Force Base overflights in the 2000s, but they happened. They just didn't get a lot of publicity. October 23rd, 2010, War and Air Force Base lost the ability to communicate with 50 of its Minuteman III missiles. Again, these are nuclear missiles, right? 5 missile alert facilities responsible for launching those ICBMs. Alpha through Echo comprised the 319th Strategic Missile Squadron would have been unable to do so during the disruption. So they said that this communications issue, while intermittent, actually persisted over several hours. Now, the same individuals who reported this reported sightings by numerous teams of an enormous cigar-shaped craft that maneuvered high above the missile field on the day of the disruption. It's a huge UFO that, in their words, appeared similar to a World War I German Zeppelin that had no passenger gondola or advertising on its hull like a commercial blimp would. Okay, so this one, I'm going to blow this. This is in Wales, and it's Trosfinwyd power plant. Was closed and began decommissioning in 1991. In 2002, the plant had its own UFO sighting. In March of that year, Brian Roberts claimed that him and his wife saw a flying craft hovering for about 10 minutes near the plant. He described it as saucer shaped with a brilliant perimeter of light moving in a circular pattern. Now, what's interesting about this one was this plant started closing in 1993, and so was there a nuclear correlation here or not? So I started digging on this. So in 1993, they removed the highly radioactive spent fuel rods. That was completed in 1997. Intermediate level waste is being stored, it's being removed by robots, basically. Contaminated materials being stored in a specially designed building on the site. It'll eventually be removed for deep burial in the 2040s. But what they're saying is steel reactor cores that house the fuel rods won't be removed yet because they're still far too radioactive. So the site won't be done until actually 2071. What that means is this UFO event here, even though this site was decommissioned and offline, still lots of radioactive materials, highly radioactive materials around. This one was intriguing to me. I can't show you the video for this. I didn't even store it. It's online. So Bariloche, Argentina. Okay. The story that I originally found was 2 UFO hunters went to Bariloche because they were hearing about these UFO sightings there. And what they found was a failed nuclear fusion facility that President Perón tried to start there in the 1950s. He had this brainstorm. Apparently, he hired a bunch of Nazi engineers to try and build this, and they never got this thing off the ground, right? So they generated a little bit of, a little bit of radioactive waste or whatever, but not enough to do anything. That's the official story. So these 2 UFO hunters went there, and they saw these UFO reports in this area, and they said, "Well, why?" They found this old building, they dug in, they did some research. Well, that building, it turns out, was this fusion facility, which has been closed and decommissioned for years. So at first, I was going to write this story off because this Bariloche sighting, is there anything nuclear about it? Well, no, the site's been decommissioned and cleaned for years, right? So anyhow, in 1995, Flight Captain Jorge Polanco said, at the moment when he started the last descent, he suddenly saw a white light which came directly at full speed in front of him before stopping at 100 meters. When he started his maneuvers, the object made an odd turn to accompany the descent and paced the 100 meters about us. After a while, the saucer, which was the size of an airliner, changed color. 2 green lights appeared at the ends with an orange gleam at the center, which ignited intermittently, right? So that was the HuffPost. So again, you've got these UFO sightings here. There were several aircraft sightings, as I recall. This one is just one of many. And I guess the thing that kind of made me interested about this was I said, well, is there any real nuclear connection here? Did a little bit of research. As it turns out, even though President Perón's, I'm going to admit those folks, even though President Perón's fusion reactor was a failed project, it was dismantled, removed, the whole 9 yards, the Bariloche Atomic Center is one of the pioneering offices of the CNEA that had its beginnings in the 1950s. It houses a nuclear reactor built in the 80s. Nearby Institute Balsero is a research institute for physics and nuclear engineering. So Bear Loch actually has one of the, if I understand this correctly, it has a training reactor that's used to train, supposedly this is one of the biggest training facilities in South America for South American nuclear engineers. They have an active nuclear reactor. So there's an absolute nuclear correlation there. Hartlepool nuclear power plant, back to Great Britain. Newly released UK government files of reported sightings of UFOs include a 1993 sighting of something strange hovering over the Hartlepool nuclear power station. Object was seen in the skies over Teesside and Cleveland area of northeast England and has been seen over local chemical plants and military installations. And let me click this because I believe there was a link there. And you know what, I should probably, yeah, that's not going to load for us. Ah, okay, that one does not. There was some video of Hartlepool, but okay, sorry, let me go back into my PowerPoint. So I don't have the link to that. Nellis Air Force Base, 1990 to 2004. The government ended atomic weapons tests years ago, but Nevada incidents continue. Former security officers at Area 2 at Nellis Air Force Base, which was a storage facility for up to 200 nuclear warheads, have reported multiple intrusions by unknown aircraft from the late 90s through 2004. UFOs filmed by the US Air Force at Nellis, very interesting hard copy segment from 1995 about the UFO that was filmed at Nellis. Let me see. I wanted to get this one up. So this was one of the UFOs that was shot over Nellis Air Force Base. This is from an old hard copy news story. See. Please pardon the poor resolution. Now, what is interesting, I'm going to zoom back there. This does tend to resemble our gimbal again, right? Let me see if I can pause that, right about there. So you see this rim. This is the way I interpret it. You see this kind of saucer-shaped rim, and then if you notice, there's big bumps, right, over the top and the bottom. Oops, and yeah, you can see it a little bit better. So this, to me, this resembles the outline of gimbal, and it resembles the outline of the one that was at the Mexican nuclear reactor as well. I mean, this could be the same object. This is the 1990s. The other one was, okay, let me see how I can get out a hard copy here. So again, that was Nellis Air Force Base. This, to me, to my eyes, that looks like the same object that was at Veracruz at the Mexican power plant. Another thing that's interesting here is, again, these didn't get a lot of publicity. I never heard about UFO sightings over nuclear plants in the 2000s, but apparently they were still happening. Chernobyl nuclear plant. Mikhail Voritsky, senior dosimetrician with the dosimetry control department, alleged that on the night of the disaster, he and others observed a UFO over reactor 4. We saw a ball of fire. It was flying slowly in the sky, 6 or 8 meters in diameter. We saw 2 rays of crimson light stretching out towards the 4th unit. The object was 300 meters from the reactor. The event lasted about 3 minutes. He'd said that the radiation levels coming from the reactor dropped from 3,000 to 800 milliroentgens per hour during that time. Now, in the following years, dozens of UAP sightings have happened near the reactor, many accompanied by photos. In some cases, fighter jets were launched. I did not find, I saw some of the photos online, lots of blurry photos, so I'm not going to put any of those up. But events over Chernobyl, going back in time, Malmstrom Air Force Base. This is a name that many people in UFOs are very familiar with, and yeah, this one comes up again and again and again. In 1986, Joseph Solka said he got a phone call about a group of lights darting around the sky. A1 was the command post for the 10th Strategic Missile Squadron. He turned on the security control lights so we could see better. Sure enough, there was a group of 5 lights zooming around the night sky. They maneuvered like nothing man-made could have then or now. It didn't move fluidly. It was like a high-speed darting around, sharp-angled turns, one after the other, until they all stopped at the same time. So they were moving together, right? He was saying it was late fall with an overcast sky. It was pitch black outside. He told everyone on the site about it, shut off the launch control facility perimeter lights. He said then the phone started ringing off the hook as all the other launch control facilities in the squadron area called to report the lights. So presumably, when he shut off the lights, that made it more visible. Everybody else could kind of see those. As he hung up the phone, 5 more lights descended slowly from the clouds to join the first 5. They all stopped momentarily. Then all 10 began to dart around like crazy fireflies. Then they zipped off at high speed in all directions, disappearing into the clouds. So again, this quote comes from, this was on the Robert Hastings site, UFO Hastings website, which is worth checking out. Indian Power Point, nuclear power plant. I'm going to keep an eye on the time here. So what's worth noting is we've got like the last 3 of these: Chernobyl in 86, Malmstrom 86. You go from a Russian commercial power plant with an accident that's decommissioned to an active U.S. Air Force website. Indian Point nuclear power plant is actually in, I believe, upper state New York. And this one was interesting. I visited relatives as a kid. I actually visited this nuclear power plant. And just for giggles, I said, yeah, I remember going to that one. I said, I wonder if there was ever a UFO there. Yeah, guess what? Sure enough, 1984, giant UFO sighting. An American nuclear power plant was buzzed by an enormous UFO, say the plant's security guards, local police officers, and other eyewitnesses. The New York Power Authority confirmed the sighting. Philip Imbrogno, who's associated with Dr. J. Allen Hynek's center, interviewed 6 of the 12 guards who saw the craft. They said it was a gargantuan UFO, looked diamond-shaped, 450 feet in length, bright white, but at one point it changed from white to blue to green to amber, hovered over the plant for approximately 15 minutes above about 30 stories above the exhaust funnel of one of the plant's 3 nuclear reactors. So this is, I believe, also connected, and I might be wrong here, I believe this is connected to the Hudson Valley, which I believe Bruce Cornett and others have said is a hotspot in the New York area for UFOs. But so that's Indian Point, which I just looked up on a whim, and sure enough, there were sightings. Whiteman Air Force Base. Dale Hogan said he climbed up the nuclear weapons igloo, looking at a bluish red light. Light started to do a grid pattern, went from one corner to the other, about every 3 inches back and forth on a grid. When it got to me, the light stopped because he put his hand into it, right? So this is a smaller event there. In that video, I'm not going to play this one, Bill Wickersham described the 1984 Whiteman Air Force Base incursion in detail. Byelokorovich, 1982, back to Russia following the collapse of the Soviet Union. They came forward and began discussing their involvement in a similar issue during the Cold War. At Byelokorovich, when a disc-shaped UFO hovered over a nuclear missile base for an extended period of time, a number of missiles suddenly activated without authorization from Moscow or any action being taken by the missile launch officers. Fortunately, after 15 seconds, the activation ceased, the missiles returned to standby. Again, this comes from Robert Hastings. RAF Bentwaters, everybody in ufology knows about this one. Colonel Charles Halt said that in December 1980, when he was deputy base commander at Bentwaters, strange lights in the forest were investigated by 3 patrolmen. Bentwaters was also the Rendlesham Forest sighting. Several U.S. Air Force personnel reported seeing a strange metallic object in Rendlesham Forest near RAF Woodbridge, found 3 depressions in the ground, reportedly approached reporting triangular craft, 3 meters on a side, dark metallic in appearance with strange markings. 2 nights later, they investigated another sighting near the base. He was told by the commander, it's back. Again, they found indentations to the ground, broken branches, and low-level background indentation. So they also said it was shedding something that looked like molten metal and shined a beam of light down towards them. So that's the UK. Kirtland Air Force Base, 1980. 3 security policemen inside the Manzano weapons storage area sighted an unidentified light in the air traveling from north to south over the Coyote Canyon area of the Department of Defense test range, traveled at great speed, stopped in the sky over Coyote Canyon. At first they thought it was a helicopter. After observing its maneuvers, they said, no, the helicopter couldn't have done that. Further events happened on August 10th and 13th, including unexplained electromagnetic interference that rendered the radar scanner and radar approach control equipment inoperative for Albuquerque Airport, along with a security guard sighting an unknown object near an alarm structure on the base. So in this case, I did a fair amount of reading on this one. There was a larger area at work here, and this was interfering with Albuquerque Airport's electronics and their radar and all of their equipment. And so this was a lot more than just Kirtland, but the events were actually happening right near Kirtland AFB. Grand Forks Air Force Base, 1977. Let me take a look at the time. I may have to push through these a little faster. So he heard on the radio they were dispatching a security alert team to investigate a situation 4, which is penetration of the launch facility. Again, this is a nuclear missile base. They were seeing unidentified lights in the sky. Some appeared reddish, kept jumping around. 1 minute they'd be hovering, but they'd rapidly move to another spot. Security personnel had been briefed about unidentified helicopters. That was what they were calling them. They've been intruding above missile sites and other strategic air command bases. But what he was listening to the team on the radio. They weren't describing helicopters. He said they were rapidly jumping around at the blink of an eye. A short time later, one of the missile launch officers at Gulf told us they had lost control of the missiles right when the lights appeared over the sites. He wasn't sure if they meant all of them or only some of them. Okay, so that's Grand Forks in 77. Now, when he talked about the helicopters, he was talking about this one. And let me see, I think I cloned this. Oh no, it's not a clone of the slide. It's just a big slide. Okay, so multiple US nuclear sites. This was a series of encounters in 1975. I think it went just into 76. These were described as unknown helicopters penetrating the security of multiple nuclear, Department of Defense, Air Force Base, weapon sites, things like that. When they describe it as helicopters, it's difficult to know what that means. So it happened. They never really did figure it out. During 2 weeks in 75, a string of the nation's super sensitive nuclear missile launch sites and bomber bases were visited by unidentified, low-flying, and elusive objects. According to DoD reports, the sightings made visually and on radar occurred at installations in Montana, Michigan, and Maine. So the 3 bases were Malmstrom, Wurtsmith, and Loring Air Force Base. And you can actually, if you want, you can look those up independently. I did that. They led to extensive but unsuccessful attempts to track and detain the objects. So the Air Force and DoD described the objects as helicopters, aircraft, unknown entities, and brightly lit, fast-moving vehicles that hovered over nuclear weapons storage areas and evaded all pursuit efforts. They sent fighter planes and airborne command planes aloft to pursue them unsuccessfully. Okay. And those are the same slide. That's a duplicate. My apologies. The Air Force Base. This was interesting. Again, very similar. En route to the CSC, we noticed that the MMS area was brighter than usual. The igloo bunkers that housed the nuclear weapons were surrounded by ballpark lights, which are really bright. They saw a glow over the weapons igloos, right? And again, this is something when I was looking at these, I saw this multiple times. These UFOs, UAPs are over the weapons igloos. In this case, the three K9 teams reported that the dogs were afraid and acting up. They were worried that the dogs would have problems, so they ordered them withdrawn. They also had a C-130 that was on approach, and they ordered that to do a flyby to try and get a look out of it. The next thing they heard was an order to fire on some kind of an object hovering over the weapons igloos. Order to move it out of the area came from SAC headquarters at Offutt Air Force Base. Seconds later, they could hear gunfire across the base. They saw a streak of bluish white light moving at high speed toward the southwest. It was the UFO getting out of there. It passed over the end of the runway. So, what do they say? They said one of the other sergeants said he'd never believed in UFOs, but now he did. Another person described it as a large ball of light that hovered 150 to 200 feet above the weapons igloos. That was DS in 73. Minot Air Force Base, 68. Object was sighted in the sky above a number of Minuteman missile silos. As it flew over the silos, electronic consoles at the launch control facility began acting strangely. At one point, they had to hit the inhibit switch because the launch in progress indicators had inexplicably been activated. When the flying object disappeared, the consoles reset to normal. So again, at the top of this presentation, I mentioned Luis Elizondo, and he was quoted as saying, look, these things have activated missiles on various occasions. These are the specific equations. These are specific occasions, sorry. Malmstrom Air Force Base, again, I'm not sure what it is about Malmstrom, but UAPs seem to really love this place. Robert Salas said in 1967, in the middle of the night, he got a call from one of the guards upstairs telling him they'd seen some strange lights in the sky flying fast, stopping on a dime, reversing course, and making 90-degree turns. 5 minutes later, he called back, said there was a reddish-orange oval-shaped object hovering right above the front gate. When this happened, they got a call saying that the missiles were no-go. Missiles had been disabled, all reading guidance control system failure. Within seconds, they lost 10 missiles while the object was overhead. Ellsworth Air Force Base, 67. Let me see, retired Air Force Major Galen W. King. He was a captain, missile combat crew commander, 66 Squadron. Several cases of UFOs hovering over sites. Everyone there, quote unquote, knew that weird things were going on. So apparently many cases of this had happened. Most interesting occurrence was when he was in the Echo capsule. If I understand things correctly, that means he's at the control capsule underground, right? Limited visibility, and they're relying on teams that are, above deck to kind of let them know what's actually happening. There was a security violation and alarms, both inner and outer. They sent out a strike team and received a visual report of a UFO hovering over a launch facility. He doesn't remember which one, with a light beam coming down from the bottom of the UFO to the site. Team leader told the commander at Charlie that it looked like a flying saucer. The beam was described as reddish in color. Walker Air Force Base, and let me see, we're on slide 28. Got a call from one of their sister sites. Again, this is 1967. The other missile crew said a UFO was hovering over the site, rapidly moving away, then returning. So let me see. He's saying that at times it hovered over site 6, then flew extremely rapidly. The other site stopped and hovered over that one, basically going from one to the other in terms of missile sites, right? Minot Air Force Base, and they were in 68. This is back in 66. Launch Control Center. So basically there was issues interfering with radio transmission. While he was trying to fix that, a personnel on the surface reported seeing a UFO with a red light high in the sky. At the same time, a radar crew picked up an object at a height estimated 100,000 feet. They sent an F-84 up to try and track or stop the UFO. After several minutes, he reported seeing an object with lights of varying intensities. While he was pursuing the UFO, he noticed that his gun sight light had flashed on, indicating that his plane's radar was picking up a target. So they had it on ground radar and the F-84's radar. The object was ahead of his aircraft, but at a slightly greater altitude. Then basically it climbed rapidly and took off. So that was Minot Air Force Base. Let me see. I believe this is another one. Captain David Schindel was Minuteman ballistic missile crew commander. Experienced a situation in which all 10 of the nuclear tipped missiles he was responsible for became unlaunchable. About 35 years after that incident, he learned about Captain Robert Salas' incident at Malmstrom, and that was when he decided to come forward and talk about his incident. So, okay, so then Ellsworth Air Force Base. I'm just going to try and push through these because I got about 15 minutes left. Staff Sergeant Albert Spodnik testified that someone else with his team was sent to correct an electrical malfunction that, again, rendered the Minuteman I missile temporarily inoperable. After fixing the problem, they learned that an Air Force security team had been sent to investigate a security alarm near another launch facility that had mysteriously lost power. They found an unusual object sitting within the security fence. It flashed very bright light, at which time they noticed the launch commander about the situation. So what Spodnik said was they heard the launch commander ordered the team to approach, but they refused. They asked for permission to fire on it, at which point he said, don't shoot until you know what's going on. Helicopter was ordered to the site. As it approached, the object sped away in incredible speed. That was Ellsworth. Whitman Air Force Base, 66. Whiteman Air Force Base, sorry. And I think that we've come back to this one. Anonymous soldier reported a call from Wing Security asking him to tune his radio to the base frequency, at which he began listening to a series of events involving a missile site losing power and a strike team being deployed to see a flying saucer hovering over the site. The device slowly began to depart, passing over the missile sites and causing them to lose power as it did so. Warren Air Force Base, 65. So let me see. They had UFO sightings at Echo Flight. There were times security forces would report strange things like lights in the sky. Because he was a missile commander, the security people were required to call down to the capsule and report anything unusual. The information that he got was that none of the UFOs came inside the fenced area. None of them touched down the area outside of the fence. So what he was saying was that they were all just strange aerial lights making no noise that would stack on top of one of each other and disappear. The security people described them as oblong or disc-like, no reported markings or navigation lights. If a color was reported, it was usually reddish or orange-reddish. They were orange-reddish shades. They were reported as aloft or up in the air, but he doesn't recall any mention of altitude. Vandenberg, 1964. So this is one of the few instances where a UFO interfered with an ICBM in flight. Okay, an Atlas ICBM launched from the Western Missile Testing Range was reportedly interfered with in flight by the UAP, which damaged the missile, destabilized its trajectory. Basically, what they're saying is the UAP circumnavigated the warhead while emitting 4 distinct and bright flashes of intense white light, which hit the warhead at the 4 cardinal points of the compass, or so they believed. Following this unearthly display, the craft departed in the direction from which it came. Jacobs noted that the shape of the object was that of a classic saucer. On top in the center of the disk was a dome from which the 4 bright lights emanated. So these lights, whatever it was, supposedly caused the warhead's trajectory to be disrupted. It malfunctioned, tumbled out of control into the Pacific, hundreds of miles short of where the Nike Zeus was to intercept it in a crucial test of missile defense capabilities. Now, if I remember, I believe this is the one that I'm thinking of here. So this is one where the military, because this was a test, they actually hired someone with a camera. They had multiple cameras on this thing to film this from a distance. And I believe that there is actually black and white footage of this test out there somewhere. But it was reported that they at least filmed that. So, Kirtland Air Force Base, 1964. Again, Is it again? Maybe. Two, let me see, civil aeronautics at the tower, white light traveling eastwards across the airfield. It appeared to maneuver. A brief radar contact was confirmed before men saw a dark object descend steeply at the end of the runway. They crossed the airfield, and it crossed the airfield at a moderate speed. Through binoculars, it appeared to be 15 to 20 feet tall, vertically elongated and egg-shaped with a single light at the base, came within 3,000 feet of the tower before hovering, and then it moved eastwards to the base boundary. They called the Albuquerque Radar Approach Control Unit, who were able to confirm that the target moved eastwards in the expected area. Let me see. Target moved back towards Kirtland, hovering over the outer south marker of the north-south runway. Finally took up position half a mile behind a C-46 leaving base and followed it for 14 miles before again hovering over the outer marker and fading. So this was about a 20-minute contact. That was actually in Wikipedia. Nevada test site, 1955. Again, we're going back in time here. 14 A-bombs were detonated as part of Operation Teapot, witnessed by thousands of military personnel. But there were other observers as well. It was what we called flying saucers. They were prevalent at the test site back then. So the former test site photographer. This one was reported by George Knapp. I think you guys all know George pretty well. Great Falls, Malmstrom, 1950. This one was interesting. So, okay, we're back to Malmstrom Air Force Base. Bright light caught Mariano's eye, and according to reports, he saw two bright silvery objects rotating while flying over Great Falls at a speed he estimated to be 200 to 400 miles per hour. He got his 16-millimeter movie camera and filmed the UFOs for 16 seconds. At Wright Pat, the film was examined, and they said it was reflections from two F-94 jet fighters that were over Great Falls at the time. The controversy arose when he claimed that they cut a few minutes of his film footage, which clearly showed the videos were rotating discs. And people in the Great Falls area who had viewed his footage supported those claims. They claimed that the missing frames clearly show the UFOs as spinning metallic discs with a notch or band around their outer edges, which again, it reminds me a lot of, that description is very similar to Veracruz, very similar to the other videos. So the Air Force went back in 1952 and did a more detailed analysis of the films, and they concluded that the objects were not birds, balloons, or meteors. And the original conclusion, the objects were reflections from the jets, was also ruled out. So basically the Air Force kind of dismissed this one and then came back later, took a closer look and said, no, that's not the case. This was interesting to me for a couple of reasons. This was one where it made a lot of local news headlines. So that was that was interesting, I guess, in that context. It was also interesting because when you talk about UFOs being sighted around nuclear facilities, nuclear weapon silos, things along those lines, usually it's right in the proximity of those. In this case, Great Falls is right near Malmstrom, right? It's only a few miles away. And so what you're seeing is UFO reports that are in the area of these facilities, right? Which you would expect. You would expect that if the UAP or the UFO has an interest in the nuclear facility, I mean, it's got to get there, it's going to leave, right? People are going to see it coming and going. So there's a correlation with reports in the greater area, as well as just around the facility itself. Oak Ridge, 1949. Officials at the OSI in Knoxville. And again, I'm almost out of time, but I'm almost done too. Flying saucer was sighted at Oak Ridge. Consisted of 3 objects, 1,000-foot altitude, 2 identical rectangular shaped objects, which appear to be coordinated in movement and moved in a wave-like motion. Third object was circular in shape and appeared to be in level flight between 2 rectangular objects. That came out of Project Blue Book. Killeen Air Force Base, 1949. On patrol at the Special Weapons Project, saw a blue-white oblong object hovering near the area, followed by Army patrol issues. Nearly a dozen sightings of objects were seen in the 2 months at Camp Hood, Killeen Air Force Base. Metallic cone and cigar shapes and diamond-shaped lights in the sky were repeatedly described. Roswell, 1947, which probably needs no introduction whatsoever. I think we could probably effectively skip this. It's just worth mentioning that, again, with Roswell, that's tied to the 509th Bomb Group. They had nuclear weapons, so there's a correlation there. Hanford nuclear site. This is as far back as I went. A fireball on 3 separate nights buzzed the Hanford plutonium production plant. Members of the Navy Hellcat fighter squadron in Pasco tried to intercept a fireball over the facility. The bright object evaded the planes and zipped away. Let me see. He basically said he reported chasing a bright ball of fire. And according to his account, he could never catch a thing, which after a few minutes zoomed off towards Seattle and off the radar. So this is interesting because this Hanford sighting goes back to before Roswell, right? Roswell, I think, is generally accepted as the first. So I'm going to finish up here because I'm almost out of time with more resources. I've got just about 40 events that I've documented today. I appreciate all of your patience. I found a book called UFOs and Nukes by Robert Hastings. It's on Amazon. The book is 500 pages long. It has hundreds more UAP sighting events at nuclear power plants, weapons depots, processing facilities, naval shipyards, and more. So UFOs and Nukes by Robert Hastings. He also has a website, let me skip back there, called ufohastings.com. Some of the materials I've used came from that website. I would recommend visiting that website. He has a little bit more there as well. But I think if you really wanted to drill down into this, his book, a lot of the stories are anecdotal. They're hard to prove, but nonetheless, it is a massive compendium. And this I just learned about the other day, Trinity by Jacques Vallée. That was co-authored by Piola Harris and Jacques Vallée. It explored a report about a New Mexico crash and recovery in 1945, 2 years before the Roswell incident, and the famous sighting by Kenneth Arnold in 1947. So again, the mythology says that 47 is when most of this stuff started, but now we're pushing that date up to 1945, in terms of the modern era. The correlation between the crash of the object and the explosion of the first atom bomb in White Sands, less than 20 miles away, has been missed by the media. Harris and Vallée suggest that the correlation is significant for various physical, geographic, and biological reasons, aside from the obvious strategic implications. Okay, so that is the end of my screen share, and we are just about out of time for this presentation. Again, I appreciate all of your bearing with me. So that was UFOs and Nukes. We don't have time for Q&A right now on that, but I am more than happy to do that later on. Again, I would recommend taking a little bit of time to look that up. There is definitely a correlation there. I have no idea what it means, but it is there. Okay, so Kevin Knuth has joined us. Let me find him now.
Hey, first, let's get a round of applause for Tim. Thank you for that excellent.
Kevin, are you with us?
I am. Thank
Hey,
you. Hello.
Can we first get a
Wonderful.
round of applause for Tim? That was an excellent presentation. Let's go.
Thank you, everyone.
Sorry to interrupt.
Thank you, Jeremy, for reminding us for that. Tim was too polite to ask for.
I know
round
he
of
can't just
applause.
ask for it himself, so I have to initiate that.
Well, if guys, if I could make a very quick statement on that, the 40. Again, I didn't think I'd find anything. I read Luis Elizondo's comment and I said, oh, okay, just for giggles, let me see what's out there. I found those 40-something events within, that was probably 3 hours worth of work to put all those in the PowerPoint. And then when I found Robert Hastings' book, he has hundreds and hundreds of those events documented. In fact, my original thought was when I got his book, I got a PDF of it and I thought, well, I could take some of the key events. And I realized that there are so many key events they documented, there's no way I could put them all in. So that's why I just referenced the book. Again, I'm not going to make any claims to know why or how or what it means. But in terms of a correlation, there seems to be a definitive correlation between UAPs and nuclear silos. And what did interest me was, again, I think I had 2 videos and a couple of different descriptions there that seemed to describe the same device, you know, that gimbal looking device. So, well, guys, let's go to Kevin Knuth now. Let me do a brief introduction first. Okay, Dr. Kevin Knuth is an associate professor of physics at the University of Albany with over 2 decades of experience in machine learning algorithms for astrophysics, Bayesian probability theory, information theory, robotics, signal processing, neuroscience, nonlinear dynamics, QM, and many other areas. He is also the editor of the peer-review open access journal Entropy, as well as being a member of the Scientific Coalition for UAP Studies. Last September, he co-authored Estimating Flight Characteristics of Anomalous Unidentified Aerial Vehicles. And at the recent SCU conference, he presented the flight characteristics and physics of UAP, which he'll be discussing today. So everyone, let's welcome Kevin to today's event, and I will hand it over to him now. Sir?
Right. Thank you very much for having me. And I'm sorry for the delay. I had technical difficulties. And let me get my screen sharing working here. Share screen. And there we go. All right. So now you should be able to see my slides. If I make it a slideshow, I think this will work. All right. How does that look? Can you see the title slide?
Yeah, that looks great. That looks great.
Right. All right. So, great. So, yeah, so I'm going to talk about flight characteristics and physics of UAPs, hoping to make some headway into the understanding of their physics. And I've been working with the UAPX group, founded by Senior Chief Kevin Day, who you see front and center. And we're basically a group of former Navy people and scientists and engineers who are actively working to collect data on UAPs. So we've actually had some sense in recording data, recording images of UAPs. So I'll mention that a little bit. And of course, we learned from Elizondo in the from the AATIP program that they developed or introduced the 5, what they call the 5 observables. The first one is positive lift. The second is sudden or instantaneous acceleration. As a physicist, I get a little nervous when I hear the word instantaneous anything because that's not measurable, but I'll mention that a little later. And very high rates of acceleration is what they're noting, and at times immeasurably high. 3, hypersonic velocity without signature. 4, transmedium travel. And 5, low observability or cloaking. So I'll talk about each of these a bit and more. So of course, I gave this talk recently. I used these slides for the presentation that we made to a special session of on UAPs at the American Institute for Aeronautics and Astronautics. And we were very pleased to be invited to give talks at this meeting. It's basically the world premier conference in aeronautics and astronautics. And so to be able to address aeronautical engineers and discuss this with them was very exciting. And of course, we were careful. So this slide is to reinforce the idea that, of course, most UAPs are misidentifications of astronomic and atmospheric phenomena or conventional aircraft, and another large proportion are hoaxes. And it really comes down to about only 3% of UAP are of interest. And what I'm really interested in is the subset of those that appear to be anomalous unidentified aircraft. So here's an example of mistaken identity. This is a purported photo of a UAP. And I'm a bird watcher. I've been a bird watcher since I was 5 years old. My father was a wildlife artist. So I looked at this and was able to identify it pretty quickly. It's a seagull. Very often when people take photos of scenery and, oh, there's a strange object in the picture that I didn't see while I was there. Well, it usually is an insect or a bird. Images are sometimes also altered. So here's an image where clearly the stars aren't real, and you can probably guess what else also is not real. Although I've been told that this was meant to be a mock-up image just illustrating what the lights over Phoenix looked like. So in all fairness, this might not have been put out as a purported UAP, but instead an illustration. But it makes the point. And the important point in my mind is that some UAP have been partially identified as structured craft. The whole idea of it's funny. There's people, will use anything to argue in these situations, and the fact that these things are called unidentified, whatever, leads some to say, well, if it's unidentified, it could be anything, and that's really not true. That's not how identification works. And I like to give, as a bird watcher, I like to give bird watching examples. I have a lot of, in my notes, when I go on trips, I have lots of birds that remain unidentified. I did identify them as a bird, so that's what I mean by partial identification. And very often I can see a bird in the distance and say, oh, that's a heron, or that's a pigeon. I might not know what kind of heron it is, depending on where I am, but I can partially identify it as a heron, or identify something as a hawk and not an eagle. But I don't know if it's a red-tailed hawk or a red-shouldered hawk. So identification isn't a binary thing, and it also depends on what level of description you're interested in. Somebody might just be excited to see a bird, and that's it. Oh, I saw a bird, and they're done. It's been, in their mind, it's been identified and case closed. Days, and so you get large craft hovering for days. It is pretty hard to imagine how you would do this and not run low on fuel. So the mechanisms for generating lift are really unknown at this point. And the other thing that we see is, or don't see, is we see no heat signature or from the engines, and we don't see any exhaust. So this again is an infrared image, and you don't see any hot exhaust coming out of there, and it's not quite clear that it's no obvious heat from the engines. And I'll point that out in a few other videos. Another point, another one of the 5 observables is the sudden or instantaneous acceleration. When they use the word instantaneous, they mean it's too high to measure. So we've looked at several cases and published a peer-reviewed paper on a few of these cases demonstrating these accelerations. So one of these, probably the best example of a high acceleration, is the case from Kevin Day, who you saw a picture of earlier, on the USS Princeton, monitoring when they first discovered these tic-tac-shaped objects in the Nimitz encounter in 2004. He observed them basically cruising along at an altitude of 28,000 feet, moving at about 100 knots horizontal velocity. And they would then sometimes drop down to the sea surface or 50 feet above the sea in 0.78 seconds was the measured drop time. So you're basically accelerating. You start accelerating in the y direction downward, and you then, of course, are going to come to rest just above the sea surface. So you're going to have to decelerate again. And you can estimate, you can put bounds on the minimum acceleration to do this. The minimum acceleration to do this would be to accelerate at a rate A to the midpoint and then decelerate at the same rate to your stopping point. That would give you the minimum acceleration. That's what we're going to estimate here. And putting some uncertainties on the measured heights, these things varied in height by about 300 feet, about 10%. And so, and of course, we have some uncertainties in the time as well. We introduced that for good measure. And when you plot a histogram of Monte Carlo samples based on all these uncertainties, you find that the most probable acceleration is over 5,000 Gs. So you're looking at least 5,000 times the acceleration of gravity to accelerate to the midpoint and then decelerate to the stopping point. Now, of course, you could have a different acceleration profile, but that would be a greater acceleration. You could accelerate much faster to a constant and then travel at a constant speed and then decelerate at a much higher rate to stop. That would be possible too, but that would be a higher acceleration. So this is the minimum possible acceleration, which is impressive. And I should make some statements about this. I should have added these to my slides. Forgive me, I'm going to pop over and open up another talk and show some slides from this. I want to show what 5,000 Gs of acceleration gives you. Here we go. That should do. All right. All right. Let's see here. Let me stop sharing and then reshare, so you see the right thing. There we go. Stop share and share this. There we go. All right, so right now you should see the relativistic rocket equations. Can somebody let me know that you see this all right?
Yeah, those look fine.
Great. All right, they do look fine. These are the equations that you would use to calculate how far you would travel after a certain amount of time in the spacecraft while you're accelerating at a certain acceleration A. And these are the equations we would use if this thing were going to be accelerating for any period of time, because you're going to very quickly reach relativistic speeds. How quickly? Well, that's a good question. Let me go to the velocity here. Here we go, velocities. So just to give you some idea, at 1 G acceleration, this is a graph of your velocity over time. And you can see that at 1 G of acceleration basically gets you to 90% the speed of light after a little over 2 years. So would take you about, if you accelerate at 1 G and can keep that up, you'll be traveling about 90% the speed of light in about 2 years. Now, we're talking like 5,000 Gs, so this is 1,000 Gs of acceleration. You can get up to 80% the speed of light in 11 hours. So we don't know if these tic-tac objects can travel in space and if they can accelerate in space. There is some indication that they were detected by radar operators on the USS Princeton, the radar operators who are watching for ICBMs. That Kevin Day has told me personally that they were observed to drop in out of orbit to 80,000 feet when they showed up on his radar. But nobody's come forward to corroborate that yet. So assuming that these tic-tac shaped objects could accelerate in space, even if they accelerate at 1/5 the rate, 1,000 Gs, you can see that they're in a half a day, they're already traveling at 80% the speed of light. It only takes an hour of this acceleration to get up to 1/10 the speed of light and 3 hours to reach 30% the speed of light. So this is a really impressive rate of acceleration. And I like to say this, why people often ask, skeptics often ask, why do people always assume that these things are spacecraft? And the answer is quite simple, because they accelerate and travel at speeds that are spacecraft-like speeds. Of course, most typical eyewitnesses wouldn't be able to recognize that, but they can recognize unreasonably fast. And these things are unreasonably fast. At these accelerations, how far can you travel? That's an important question. So here, let me see. I'll put up even at 100 Gs, so I only have graphs here for 100 Gs. These were some of our early estimates before we worked this out in detail with this data here, so don't go by these numbers. But basically at 100 Gs, this is the distance as a function of time. So, in 3 months of ship time at 100 G acceleration, you're already traveled a long ways. To get to the other side of the galaxy will take you a little more than 3.5 months. Now that's ship time, of course. The time in the rest of the galaxy, they're going to see this take. Basically, you're traveling something like 60 to 80,000 light years. So what do I have here? I guess this is around 100 light years. So they're going to see this take 100,000 years. But for the people in the ship, in the Tic Tac, accelerating at 100 G, so this graph is actually for accelerating halfway and decelerating the other half. They're going to be able to traverse the galaxy in just over 3.5 months, which is really impressive. So these things do act like spacecraft. In fact, I would say that they don't just have the same speed and accelerations that you would expect from spacecraft. They have the speed and accelerations of exceptional spacecraft. That's something that you would only dream of, right? So these spacecraft are probably better than what we have in our science fiction. And that's an important point to note. All right, let me go back to this presentation here. All right, so we've measured accelerations ranging from about 70 Gs all the way up to 5,000 Gs. All right. We see that these things have achieve hypersonic velocities with no signatures. The hypersonic speeds, this tic-tac dropping from 28,000 feet to sea level in 0.78 seconds under 5,000 G acceleration, the speed at the midpoint would have to be on the order of 46,000 miles an hour, or Mach 60. That's about the same speed as the New Horizons probe that has now passed Pluto. So this thing's traveling as fast as one of our fastest spacecraft, and accelerated to that speed in less than 0.3 of a second, or on the order of 0.3 of a second, which is really insane. Now these speeds aren't unusual. In fact, Hermann Oberth, the rocketry pioneer, mentor of von Braun, gave a presentation in 1954 on UFOs, and he noted that their speeds had been tracked on radar up to Mach 55, which is about 42,000 miles an hour. So the numbers we're estimating here are consistent with other observations that were made in 1950s, which again begs the question, why was no one concerned about this? Why was no one neither concerned nor interested? It's fascinating and a little scary. Now, the other problem is energy deposition. That's a crazy amount of kinetic energy, and it just doesn't disappear when the object stops. That drop maneuver should have deposited on the order of, if we don't know the mass of the tic-tac shaped object. So we have to take some estimates here. The thing was about 40 feet long. It's almost the length of an F-18, and F-18 is about 15,000 kilograms. So we lowballed this to estimating its mass to only be 1,000 kilograms. So it's basically an order of magnitude less massive than an F-18, while it's the same size as an F-18. So at 1,000 kilograms, the amount of energy that it had to deposit was on the order of 4 times 10 to the 11th joules. That's basically 100 tons of TNT, and would be the same as about 250 Tomahawk cruise missiles going off at once. And that's what should have happened when this thing stopped. And of course, none of that's observed. And which is shocking. So what's happening with the energy? Where does the energy go? You don't see heat signatures in the infrared, so we don't have any idea. This energy does not seem to be being dissipated in any way. Here's a clip from Hermann Oberth's presentation, where he notes these high speeds. He says their speed is sometimes very high. 19 kilometers per second has been measured with wireless measuring instruments, radar. Accelerations are so high that no man could stand it. I don't think he realized how high they were. He says he would be pressed to the wall and bruised. He would be gel, actually, in the case of this tic-tac here. The accuracy of such measurements has been doubted. And he says, if there would only be 3 or 4 measurements, I would not rely upon them and would wait for further measurements. But there is existing more than 50 such measurements. The wireless sets or radar of the American Air Force and Navy, which are used in all fighters, cannot be so inaccurate that the information obtained with them can be doubted completely. So he's making this argument that we continue to make, but he's made it over 50 years ago. Transmedium travel is another one of the 5 observables. UAPs can travel effortlessly in multiple media. Here we have, in this video, you can see the UAP is underwater. This is from the Aguadillo case. This UAP, which is estimated to be rather small, a little bigger than a football, was cruising about 100 miles an hour just over the sea surface and then dipped below the water. And so here's a plot from the detailed analysis provided by SCU, the Scientific Coalition for UAP Studies. It enters water at just around 110 miles an hour, and its speed then drops to about 80 miles an hour, and then averages to the average speed while underwater is around 85 miles an hour. And it varies its speed slightly and then exits into the air. These transitions are not as dramatic as they would be if it was some of our equipment. So very strange that these objects can move from one medium to another, can keep their speed up. They don't seem to be impeded. They don't seem to interact with the water or the air. So this is very puzzling. And I put in here in red, or pinkish, I guess, salmon colored, Can they travel in space in a vacuum? That's not been totally verified yet, but I suspect that's probably the case. And solids. Can these things travel in solids? There have been some observations of these things flying into mountainsides, and I would be interested in collecting more of that information, because if they can travel through solid, then if you can travel through water like this, very possible you could travel through solid. It's hard to imagine that the two are that different. And let's see, there was something else in my mind to mention with the water. What's interesting about traveling through water like this is that these things have been picked up on sonar. So there are cases when they've been picked up on sonar, but I don't know of any particular cases where they were traveling at a high speed and were observed to go into the water unimpeded and then were picked up on sonar. So we don't know if they're the same objects. This is one delicate point, is that since we don't know what we're dealing with yet, there could be various types of craft, each using different propulsion techniques and or different technologies. And to make matters even more confusing, you could have the same craft also using different technologies at different times. And so we have to be very careful not to speak in generalizations. Our first inclination is to try to generalize what we can learn from data, but these are not that easily generalizable. For instance, I could go pick a car off the road and it could be a diesel fuel car, or I can pick up an unleaded gasoline car, or I could pick up a hybrid or an electric car. And the hybrid at times will be an electric car, but sometimes it'll be a gasoline powered car. So just like the Starship Enterprise can fly with warp drive or impulse power. So it's not clear that these things are all using the same technology. But what's interesting about the sonar recordings is that sonar requires that the sound waves bounce off the object. And in something like water, these are not displacement waves, they're pressure waves. So you've got basically the pressure wave has got to hit the object and bounce off of it. But if these things are able to move underwater at very high speeds, which has been observed, then, and it appears they're unimpeded by water, then you shouldn't be able to bounce pressure waves off of them. So it's not quite clear how sonar would work in cases when these things are moving through water at very high speeds. So there's another clue there as to what's going on, but it's not clear to me at this point what that is. All right, so low observability and cloaking. So here's an example again from the Aguadilla case. You can see it goes through various, it changes size, almost disappears at this point, and then comes back again, and it's blurry. And so often skeptics complain, oh, these images are always blurry. And it turns out there are possibly reasons for that. And it could have to do with the physics that are involved. Some of these objects appear to have plasma sheaths surrounding them. And here here's the gimbal video, US Navy gimbal image from their video that was recorded in 2015. I have superimposed next to it a picture from a Super 8 film taken by Ray Stanford back in 1985. And this is, of course, Ray Stanford is debated throughout the UFO community. And part of the reason is that he does not want to share his imagery with UFOologists, and so he'll share with scientists, though. So people don't all get to see this, and that seems to get people's undies in a bundle. And And Ray is an interesting character who's made some pretty fantastical claims throughout time. So it's difficult to know what to believe. And so I want to make the point that this imagery is not independently vetted. We have not done that yet. I've been working with Ray over the internet for the last year or so. And I'm hoping to visit him this fall, where we'll get his films digitally scanned and authenticated. So we plan to do that. Now, others have seen these films or seen still images from these films shortly after they were recorded in 1985. And so despite the fact that this image is possibly contentious, I decided to include it. And I include it with that statement that this has not been independently vetted, but we plan to. And there are several reasons I included it. One is you can see what looks like could be a plasma sheath surrounding this. So this was a nice example of a plasma sheath. The object appears to be disc-shaped, surrounded by a plasma sheath. And I actually checked with some of the people at SCU to see if they had imagery that had been vetted that demonstrated plasma sheaths, and they did not have any. So one of the difficulties here is that most images of UFOs have not been independently vetted and authenticated. So it's very difficult to pull an image up and say, oh, this is this, and this illustrates this. This is one of the problems. And this is why we're collecting data now. This is why I'm working with UAPX. So I'm showing this because you can see the plasma sheath. You can see that the object looks similar in shape to the gimbal image, which I find to be interesting, especially since this was recorded in Stanford's image is 1985, and this is 2015. And we've had some people claim that the 2015 image is just jet exhaust. Well, this jet exhaust looks very similar to images that Ray Stanford has captured. Another important point that this image makes, so this image I'm including because it makes several points, is that the object was traveling in this direction of the arrow. So the object is traveling to the right. And it's a disk that is traveling, basically, when these disks hover, they'll hover like this. When it's time for them to move, they tip up on end 90 degrees, and then they travel in the least aerodynamic way possible, which is really interesting. And you can see this here in this image, from the claim from Ray Stanford, which direction it was moving. So we have to take him at his word for that. But I'll back that up with other statements in a moment. And another thing you can just make out in this image, you can see a very light beam, what looks like maybe some kind of beam or line coming out of this object, coming out of the point here, which Ray calls the tower. He contends that this is a plasma beam that is fired off in the direction of motion. So, so that's interesting too. And of course, the gimbal video, this thing wasn't moving. Remember, it was just hovering, and they were circling it, and the thing would change its orientation at times. It would have been nice for them to record the video until it took off, or for us to be able to see that video, but I don't know if that even exists. Now, what is the importance about this plasma beam? Well, this plasma beam, what appears to be a beam in that image, is important because we now have a technique for achieving hypersonic velocities, and that is to basically fire a laser out in front of the craft. So you fire a laser in front of the craft, and you heat up the air, and that basically creates a plasma explosion of air that creates a shock wave. And the shock wave usually would be on the nose of the aircraft. But if you shoot the plasma beam out, you can create the shock wave back here, and the aircraft just travels within that shock wave at hypersonic speed. So it greatly reduces drag. And this is a technique that we're actually using at this point. So this appears to be similar to what is being observed here. So since I'm interested in the physics and the engineering, this could be evidence of this, of a type, it could be a plasma beam that could be used to make a shock wave so that this thing can travel through the air more freely. So to not show this image would be kind of foolish, because we might be missing some physics here, but we can take it with a grain of salt, until it is authenticated. Now, this traveling in the least aerodynamic way possible is interesting, again, because Herman Oberth noted in his 1954 talk that the disks typically fly bottom forward. He says the disks always fly in a manner as if the drive is acting perpendicular to the plane of the disk. When they are suspended over a certain terrain, they keep horizontal. And when they want to fly very quick, they tilt up and fly with the plane directed forward. So this has been observed multiple times. There are other cases of this where people have seen this happen, just as Ray Stanford had described. Now, I'm also told, I also have some evidence that the aeronautical engineer Luc Mirabeau had seen this and was inspired by this description. And it's also known that he worked to develop this this plasma beam ahead idea. So I'm right now researching what his connection to what the connection of Ray's imagery is to Luc Mirabeau to the development of this technique. It could very well be that this is one of the first techniques that was developed and inspired by UFOs. Another aspect of low observability and cloaking is what we call multi-imaging. UFOs are often observed to split into multiple objects. In many cases, this appears to be an optical effect, and it contributes to the blurred imagery. So these are individual frames from the Aguadillo, Puerto Rico case of the object moving, and you can see at this point the object appears to be splitting up. I think it goes like this, and it splits up here and then makes what look like two objects. And they actually separate for some distance until this one fades away, and then you're back to the original object. So there's some kind of optical distortion going on here. And it could be that, it could be something else, it could be more. So here's a picture of the multi-imaging. You can see it happening there. And the upper one is starting to fade. So some of this multi-imaging can be very subtle. Multiple images can appear many times a second, which we call flickering. What you want to do in these cases is image this with as fast of a frame rate as possible. If you're taking photographs, you want to take it very high speed, 1/2000th of a second, as fast as possible. And you'll get multiple simultaneous images of the object. And sometimes these images can be seen to have different orientations. So it may not be simple refractive effects. And sometimes it looks like these objects are dividing or spawning new objects. And it's not clear whether that's actually the case or whether it's optical. The distortion field. Objects are often surrounded by a volume through which the background imagery can appear to be distorted. Here, as this object, watch again, it'll recycle. As he flies over the lines, you'll see the lines warp around the object. I hope you can see that over Zoom. You can see the lines distorted. So is this a refraction effect? Is it due to a varying index of refraction around the object? Is this due to plasma or the heat from the object? One might think this. We have some reasons to think that's not the case. Or is this a distortion or lensing due to a gravitational field around the object? And these are all important questions. Now for some physical of our observables, which we're going to introduce that were not discussed by AATIP. One is low temperature. Some of these UAP, or many of them, turn out to be cold objects. They're not hot. You don't see any waste heat. You don't see any waste heat. In fact, you see the opposite. You see that they're cold, which is very strange. So here's an image from the US Navy's Go Fast video. Some people have claimed this is a seagull and that it's not going fast. I don't think any of that's, well, first, it's not a seagull, and I don't think it matters whether it's going fast or not. Go Fast is the name of the video because it looks like it's going fast in the video. I don't think its speed is the important point here. What I see as the important point is the object here in the center inside the reticle is white, and you can see that the camera is set so that hot things are black. You see the BLK down at the bottom. That means hot things are black, cold things are white, and this object is colder than the sea surface. So that's very unusual. You expect a machine to be able to be dissipating waste heat, but it's colder than its surroundings. Is it a balloon? No, a balloon would be in thermal equilibrium with the surroundings and would be the same color in this infrared image. Is it a seagull? No, a seagull is warm-blooded. It would be hot and would be black in this image. So it is neither a balloon nor a seagull, and it is strangely cold. And that's what I find to be the important point. The other thing about these videos is many skeptics have argued that, these videos aren't impressive, or, they don't provide a lot of information. And I don't see that as the purpose of these videos. The importance of these videos really is that these videos corroborate the eyewitness testimony of the pilots. These videos are basically corroborating evidence. So to pick these apart and look for all these little crazy things is really pointless. These are corroborating evidence, and you don't expect to be getting a lot of data from these videos. So we at UAPEX have been collecting our own videos, and I'm going to show you one of those now. This is a FLIR video, a long wave infrared video taken with a thermocam it's a PM695 thermocam. That's a jet airplane. It's hot, hotter than 64 degrees below zero. And it's being followed by this object. This object was actually picked up on 2 cameras. You're actually seeing it on 2 cameras at this point. The jet airplane was only picked up on 1 camera. So this is not an artifact. This is an actual object. When you zoom in on this, it looks like it's trefoil shaped. I jokingly like to call it the Klingon bird of prey, but because it looks somewhat like that. That's a jet airplane. That's a passenger jet. It's coming into land. It's about 3,000 feet. Assuming that this object is at the same altitude, it's about the same size as the passenger jet, although we don't know what altitude it's at. What we do know from the temperature is it's much colder than, its temperature is down around 60 degrees below zero. So this is a very cold object. Also, strangely, many of our recordings we detect these things on the long wave infrared cameras, which are very useful because we can get temperatures, assuming that they're black body radiators. But they're not visible with shortwave IR using night vision cameras, and they're not visible in the visible range with the naked eye or binoculars. So this is also another example of low observability. Some of these things are not observable in the visible wavelengths, and we actually have some testimony to that from the pilots in the USS Roswell case, where they were picking these things up on radar and not seeing them until they were right on top of them. So this low observability is, again, an issue. It's not clear whether, just taking telescopes and aiming telescopes at the sky as the Galileo project wants to do is going to work, especially because we've had experiences where we've only seen these in long wave infrared. Now, there's a hypothesis that these things are using general relativity in some way to create these warp bubbles or use anti-gravity in some way. Now, with anti-gravity, if you're hovering, you basically want to have anti-gravity on the bottom where you would expect a blue shift, and you'd have gravity on the top where you'd have a red shifting. Or if you're moving, you're going to be red shifted in front and blue shifted in the back, and to propel yourself. So this is the gravitational redshift, and a hovering craft ought to be strongly blue shifted on the underside, which should appear hotter, not colder. So the fact that we see a strong, the fact that we observe these objects to be very cold seems to run against the hypothesis that these things were warping space-time in some way. However, the strong blue shift of a thermal black body radiation that is hypothesized here could explain radiation burns in victims. So during its encounters, and there's numerous cases of this. So again, it's difficult to generalize. The craft that we are looking at with our infrared cameras that appear to be cold might not be warping space-time, but other craft might be warping space-time. So we can't just make generalizations here. But we got to keep all of these hypotheses on the table. So are these things warp drives? There's a good question. Well, an interesting thing that we noted, I was working with Matthew Shadagas, and we both noticed this, is that one type of warp drive spacetime that's been recently published by Bobrick and Martier has a physical shape that looks very similar to what you see in the gimbal video and Ray Stanford's video. So is this a coincidence or is it not? So it's not clear whether this is evidence that this is a space-time warping or not, but it's a possibility that we need to consider. And of course, we know that these craft create strong magnetic fields, strong electromagnetic fields. These fields can adversely affect electronics in airplanes and other vehicles. And there is some additional evidence for this, which I don't have in this talk. And that is pretty much it, what I have for their characteristics in physics. Some of these UAP appear to be anomalous physical objects, and they exhibit numerous observable physical effects. Of course, we can't assume that they're all the same type of craft or the same type of thing. We can't assume that they have the same origin, characteristics, or even the same technologies. And even a single craft might have different technologies during different modes of operation. So it's very difficult to put all of this data together and to come to some concrete conclusions. Potentially, we're looking at a diversity of technologies that may exist to match the diversity of objects. And I'm working with UAPX to actively study these things. And there's a link to our website, which you can feel free to visit. And we should be taking donations, or we would like to be taking donations. So if you want to donate, that would be wonderful. All right, that is basically it. Thank you. And I've got a lot of things coming up in the chat. So
yeah, well, Kevin, thank you as well. So before we do anything else, let me do this. I want to, okay, you stop your screen share. Let me put it on gallery view. And everyone, please give Kevin Knuth an enormous hand. Sir, that was a wonderful presentation. And the exciting thing for me too is you really illustrated, I mean, like in terms of acceleration, but a number of other factors, you really drilled down on what makes the UAPs so just different, so that's incredibly exciting. Let's go, let me see, I'm going to allow people to unmute themselves, but let's go and do Q&A now. I'm going to put it back on speaker view and move spotlight. Okay. And I think I've got it all set up. So let me see. Oh, Gary, go for it, sir.
I really appreciate the talk, especially the quantitative aspects. I came to a slightly different conclusion, though, about blue shift versus red shift. I used to work on FLIRs, and I know the black body radiation equation. And if you upshifted that black body equation, those frequencies, that curve, if you blue shifted it, you're upshifting it, aren't you? And so you're seeing that infrared peak now in the visible, which would explain why they're glowing. And it would also explain why the remaining energy in the infrared appears to be lower. It's because you're blue shifting or upshifting the frequency of that black body curve. Tell me what's wrong with my logic there.
Oh, that's a good question. That's something that I've not looked into. We wanted to go through the details of that particular camera and the algorithms that it uses to estimate the temperature from the black body. And that's a good question. You're right. Because if you shift it far enough, then you're going to be on the other tail. Right?
The object could be room temperature or warmer, but if you're upshifting the black body radiation itself, then it would appear to be more visible radiation and less infrared radiation. And so you really do, I think, have to look at, hey, what bands is that instrument sampling? Because they usually compare 2 or 3 bands, right, to calculate a temperature. And so it could be completely wrong analysis because it's dependent upon the classic black body radiation curve, which could be, the entire curve could be upshifted, right, if it's really easy in anti-gravity.
No, that's a really good point. And it really suggests we ought to see if we can pull the data off the camera that tells us what the amplitudes are in each band so that we can estimate the black bodies ourselves.
Exactly. Okay. All right.
Thank you very much. That's very helpful.
Yeah, thanks, Gary. Okay, so who wants to go next? We did have a ton of stuff in chat. In fact, I'm just kind of scrolling through chat right now. Let me see. Jeremy, go for it, sir.
Hey, Kevin. I wanted to, well, first off, I noticed one of your slides, the photo image was credited to Brett Tingley. And then I think he got that from a patent by Kevin Kremeyer. And I posted the link to that patent in the description. So you could look that up as well, just for the photo credit that came from the patent.
I see that in your comments. Great, thank you.
The other thing I wanted to ask was, some of my questions got answered already. One of them was going to be about whether spoofing technology might exist to basically fake these things, and how can we distinguish, between spoofing technology and legitimate UAP sightings. But I think some of the distinguishing factors would be transmedium, obviously, right? If it goes into the water, it's really hard to spoof an object that goes in and out of the water. That would be one giveaway characteristic. But anything else that you could think of that, because I had a TD Barnes on, who was the head of special projects out at Area 51, and he seems to think that all the Nimitz encounter and all these things are spoofing technology and not legitimate actual craft. So
is he believe that they're spoofing the observations of the pilots themselves? Right. Yeah. So that's a good question. And spoofing and faking things is very hard. It depends on how good the spoofing is, right? And so that's going to be really difficult to assess. I think that to assume that all of these things are due to spoofing is rather silly. Tim mentioned that some of the first recorded UFOs are in 1945 or so, but there really are recordings that go back much further than that. I have several reports of discs coming out of the water and hovering next to ships and then taking off into the sky that go back to the 1850s. And I'm happy to send, happy to send that information to Tim to distribute that. So these things have been observed since well before the 1700s. And in fact, in the 1700s and 1800s, a lot of them were reported in astronomical journals because they were considered to be astronomical phenomena. Most astronomers don't know that. And the scientists just assume that, well, scientists would have studied these things, right, or reported them. Well, they did, but they didn't get resolved and people forgot. That's common. And so the spoofing technology didn't exist in the 1940s and 1950s when Herman Oberth was giving his presentation and noting radar measurements up to Mach 55. So I would think that it would be foolish to just blow this all off and assume that it's all spoofing. If it's spoofing, then somebody's in trouble, because if we can be spoofed that well, then everyone ought to be paying attention and we ought to be trying to figure this out. So again, it's easy for people to flippantly say, oh, it's spoofing, oh, it's got to be Chinese or Russian. If that's really the case, then this is a national emergency and people aren't acting like it. So again, worrisome. Yeah, a friend of mine who I do work on quantum theory has a very great, appropriate saying. It's a motivated skeptic can deny anything. So, or a sufficiently motivated skeptic can deny anything. So it's, you have to be careful of over skepticism because it leads to extreme ignorance, as Vlob says.
Yeah, I would, I mean, just to put my 2 cents in, I would tend to agree with that. And what intrigues me is, again, I've been focused on this nuclear correlation for the last 3 or 4 weeks, but there's a consistency to these reports that goes back decades. And, like in the context of the Air Force, right, maybe you could make the case that it's, bored airmen pranking someone or something like that. But the issue is that it goes back. I mean, you see very similar reports, in the 2000s that you see in the 1980s and the 70s and the 60s. And it goes all the way back, and they're describing the same things. And to me, that's the point where, and you're right, the spoofing technology, maybe it could be done now. I'm not sure about that, but could it be done back then? That's doubtful.
Yeah, and you just have to go sufficiently far back, and there's plenty of reports that go back, as far as you want, arbitrarily far. So.
Let me see. Well, Jeremy, let me go to Harold. Harold, do you want to go, sir?
Yes. My question is that you mentioned that this craft generates strong magnetic fields. Is there any evidence as to what magnitude of the magnetic field and what is the effect on the environment? Any leftover evidence, for example, around affecting the other airplane that are taking the measurement or anything?
I know that there are some direct measurements. I don't know what the magnitudes are. And, but I know from the indirect measurements that these things can be quite powerful and can interact with electrical equipment and things like that. But those are good questions, and that's something that we're trying to assess at UAPX. We have gradient magnetometers that we're going to be employing in our next survey. So hopefully we'll get some data on that.
Well, thank you. That's an important question. I hope you find a way to solve it. Thank you.
Thank you.
Great presentation.
Thank you so much.
Thank you, Harold. Let me go to Michael Boyd next. Sir?
Hello. So I have some questions about space time metric engineering. Tim, would it be possible for me to share my screen?
Well, yeah, I mean, it might be better to just, it might be better not to right now, because that might distract us from the Q&A.
Oh, well, I was just going to show the Tic Tac video and ask some questions about space-time metric engineering related to that.
Yeah, sure. I would say go for it. I just don't want to get too far off on a tangent, but yeah.
I'm not. It's totally on point. Okay, can you see that there, Kevin?
Yes.
Okay, so now here what I'm looking at is I took some of the frames out of the 2004 Tic Tac video FLIR 1 and eliminated any of the 2x frames. You know what I mean by 2x? They're all 1x. You see the one over here. It's all in the 1x. There's
right. Yep.
And the reason I did that, I used to work in company Hughes Aircraft Santa Barbara Research Center making the infrared detectors for like FLIR 1. and it changes the field of view is basically, and so you won't see these the optical effects will look different if you mix them. So what I was going to ask you about is, so if you see here on the left, there's these like little circles. You see those there?
Yeah, I can see that.
And then you see up above here is this dark balloon type thing. See that dark balloon over the top of the Tic Tac?
Right.
And then over here on the left is this dark region where the Tic Tac is moving to. Okay. And then if you look at the Tic Tac right around the bottom of the Tic Tac, it looks like it's it's changing the thermal signature of the surrounding area. Wouldn't you agree?
It looks like it on these images. Yeah, I hadn't noticed those effects on the images I have. So.
Right. Well, they don't show up on gimbal. They only show up on Tic Tac.
Yeah. No. We analyzed these frames to get that final acceleration. It's accelerating away to the left and away at about 79 Gs.
Yeah, and you can see that it actually makes the Tic Tac look like it's stretching.
Right.
You see that, and so those are what I would call a general relativity effect. And on the left is what I talked to Hal Putoff about this, and so my hypothesis is the region on the left is expanded space-time, and the region on the right is denser space-time. And basically, it's kind of like, think of a bow and arrow, where you're pulling the region on the right is the bow, and then it lets go, and it pops out. So the question, a couple of issues that you raised is I'm curious if that dark region is hotter and the white, like you were saying before, is colder. That would be interesting to know. And the other thing I'm curious about is you were describing this thing as it would like when it was going to move, it would get like this and then go like that, right?
Well, the discs do that. This is a Tic Tac,
would turn and then go in. The bottom of the disc would basically be going to the right direction of motion, correct? But this obviously doesn't look like it's doing that, does it?
No, the Tic Tacs, what they do is when they fly, they don't fly in the most aerodynamic way possible. They'll be off axis slightly, and they'll just fly that way.
Now, the other things that I observed, if you look real closely, it shrinks. A little bit right before it takes off. It gets really tiny. So
yeah, and that's hard because it could be rotating. It could be it's a tic-tac shaped object, so it could be rotating slightly and changing.
Yeah, well, what I'm thinking is it's going like this. It's like going like in a loop-de-loop, like this, to take off. So it's building up angular momentum is basically what it looks like it's doing to me. It's building up angular momentum too.
Oh, that's a good question. The motion could be complicated. I have other images from another source that shows tic-tacs tumbling. So yeah, they do some strange things.
Yeah, okay, thank you.
And it's hard, and it's, again, difficult to generalize because, while the disks tip up and fly plane forward, the tic-tacs don't behave that way at all. They do other things. So these are possibly different technologies, possibly from different sources.
This tic-tac, part of what I heard was it was associated with a USO. There was a USO when it first appeared. They saw some turbulence in the water, like there was something down below it. So it sounds like there's a USO aspect to the tic-tac as well. Would you agree?
That's one of the hypotheses, is that it was a USO. I don't think it's been established what that object was. And I thought it strange because Fravor described it as looking like a submerged 747. And from my experiences flying off the coast of Southern California, that's what gray whales look like when you see a whale from the plane. So my hypothesis was that the object was a whale, underwater was a whale, and that the tic-tac was studying it or looking at it or something. And that was one of the hypotheses I had. So of course I presented this to SCU as a possibility, and there was a great bit of ridicule referring to Star Trek 4, right? Where they come back.
Oh yeah, that's what I was just thinking about when you said that.
Right?
That's
That's
funny you bring that up. I'm just thinking, oh yeah, wasn't that a Star Trek?
I've watched whales out of airplanes, taking off from San Diego. So it's and they look like submerged aircraft. And in fact, I did find, after I made that proposition, somebody from Norway had heard about this, and they sent me an article from a Norwegian newspaper that talked about how whales look like 737s. And so.
Well, thank you. I appreciate it.
I think it's not clear what was underwater, and that would have been nice to know. It would have been nice to have a better description of what was underwater. It might have explained what the tic-tacs were doing or how they were related to the object underwater or what.
One final question on the tic-tac. One issue that came up is it seemed like the tic-tac somehow knew the rendezvous point before and appeared at the rendezvous point. And any thoughts on the possibility this could be ours?
That is a really good question, and that is one of the strangest things about that whole episode. We made a point of that in the paper we wrote, and let me find that, because we estimated the probability that could happen by chance, given that it could have gone anywhere within a 60-mile radius and chose to go to that point.
If I could interject really quickly, I've met several people who have used that to suggest that these are time travel.
Right, yeah, so I don't think it's a strange thing, but so the probability that could happen, we estimated was about 8 1,000ths of a percent or 9 1,000ths of a percent. So
what would you figure the probability that the Navy was being spoofed by the Air Force?
That's hard to say. I mean, it's hard to say.
Better or worse?
It's hard to say in the Nimitz case, because in the Nimitz case, it was but the situation was rather benign. For a lot of the encounters in the USS Roosevelt, a lot of those happened in the Persian Gulf, and those encounters happened when you had planes flying, taking off from the USS Roosevelt and flying into Syria. So that's a war zone. So now you have if you had the Air Force spoofing the Navy during a war zone would be treasonous. So that's hard to imagine.
But the Nimitz was a training flight. Correct?
That was a training session off the coast.
So that would be a great opportunity.
That's possible, yeah.
So, okay, well, thanks for asking my question.
Sure.
Answering my questions. I appreciate all your answers.
Certainly, thank you.
Thank you, Michael. Okay, yeah, and it just occurred to me, what if the whale was actually the spoofing? But that's a completely separate. Yeah. Who would like to go next? Let me see who would like to go next. And we have tons and tons of comments. Let me see. Remy, did you? I see some comments from Remy. Did you have some questions, sir?
Hi, Tim. Hi, Kevin and everybody. No, I didn't have any questions at the moment. I'm just still taking
okay.
something in. Your presentation and Kevin, excellent presentations. Very gripping. That's all I'll say for now. Yeah? Okay.
Well, thank you, sir. Let me see. Who would like to go next? I'm just going to scroll through the questions here. Oops, there's one new one. And I am sure we have more questions. So Rob Chambers had asked, and this is up there a ways. Rob was wondering, this goes back to what you said about aerospikes. He was wondering about the, let me see, sorry. You know what, I probably shouldn't even get into that. Sorry, I'm getting lost in the questions. Rob, are you still with us? Let me see if Rob is still. Okay, and in the meantime, there's, okay. Oh, Remy, do you have a question now?
Yeah, can you hear me?
Yeah, and
okay.
if possible, could I get you to turn your camera on?
Oh, okay, I'll turn it on.
Thank you, sir.
Start video. There we go. Here we go. Wrong angle. You mentioned something about the Navy and the Air Force. I heard there's a bit of rivalry between them, where the Navy are responsible for ships, and various naval intelligence apparently have their own UFO program, but the Air Force naturally thinks it has dominion over that area. Do you know anything about that? There's a kind of gentle rivalry between them.
Yeah, that rivalry certainly exists, and but I don't know much about the rivalry, and I would be surprised if it would be taken to the point where you had one spoofing the other in a serious situation. Now, of course, we noted that the Nimitz case in 2004 was a training mission, so perhaps not as serious, but you are putting pilots' lives in danger, so potential danger. So I think that I would hope that would be treated more seriously.
Yeah, thanks a lot. Thank you.
Okay, thank you, Remy. Okay, let me go to Matthias. Matthias, go for it, sir. And could I get you to turn your camera on, Matthias?
Sure. Can you see me now?
Yeah, wonderful. Thank you, sir.
Okay, so it's about the Super 8 film. This blue image that was shown. Is this directional motion actually confirmed by the one that took the pictures, or is it inferred from something?
Well, it's from the Super 8 film, so I haven't seen the whole film, and that's one thing that we're going to take care of this fall, hopefully. So, so I've only seen frames of the film, and so from the description of the people who've seen it, say that they're traveling in that direction of motion. But
okay, so but are you going to get a hold of more frames soon?
Yep, that's the plan. Yep.
Oh, wonderful! That would be
we're
very interesting to.
Yeah, we're going to. Yeah, we're going to digitize the film and hopefully go over it in much more detail.
So that'll be on the UAP Expedition website.
I'm not sure if it'll be on that website, but we'll have it. I'll have it posted somewhere. Certainly on my research page at some point. You know, the aim is to publish this in scientific papers and then put it on the website. So.
Okay, brilliant. Thank you.
Sure.
Awesome. Thank you, Matthias. So let me see. Let me go back to Harold really quick. Harold, go for it, sir.
Yes, the other question I have is that I see a lot of the report that the pilot saw a craft, a UFO, but I rarely see, I see any the indication. They say, for example, the camera angle, the photo that they took, or when somebody taking a photo, what is the distance, what is the size of the UFO, or the UAP, the craft, for example, weight, dimensions, what speed is moving, and anything like that. I rarely see those details. Do you have any detail like that, an example to give us an idea? And thank you again.
Yeah, no, those are good questions. Typically you can't get that information all from just one photograph, and very often when these things are photographed, the conditions haven't been noted, so the person or pilots aren't noting which direction it's in, and none of that gets recorded. So so a lot of that information's lost, and so in just photographs from the public or even from the Navy aren't that useful because you can't reconstruct the whole situation. What we're trying to do at UAPX is to have multiple cameras set up some distances, known distances apart at known angles, so that when we do record these things from multiple cameras, we can triangulate the position. We can then estimate sizes. You can then estimate speeds and distances and all of those factors.
But what about witnesses? They say, oh, they saw a craft. But I never hear they say how big the craft was, or anything.
Well, you would be able to get size. If you could triangulate, you could probably get sizes. Once you know the distance, you can obtain the size. So that would be possible. To get how much the craft weighs, you wouldn't be able to get that.
Right,
We'll have to start capturing them to do that, and I don't know if that's a good idea.
Yeah, I know it's a difficult subject, and you're trying your best. But thank you for your efforts.
Thank you, Harold. Let me see. So we had a question actually that came in on YouTube. Kevin, they were asking if you guys had taken into account the aura or halo effect as an artifact of infrared.
Oh, that's a good question, and it could very well be. We haven't used the halo effect so much. We haven't done an analysis of this yet. So in that we would, what looks like a plasma sheath, we would want to record that with visible cameras and get spectra and all of this. And that's something that we're now gearing up toward. So.
Wonderful, wonderful. Let me see. I'm getting questions about uploading. Yeah, and if possible, well, if there's a copy of this presentation that I could put up, I can put mine up, definitely. But with yours, I know you delivered that at SCU. I would love to be able to put a copy of this up.
It's fine. All right. I presented it at the AIAA meeting, the American Institute for Aeronautics and Astronautics.
Okay. Yeah.
Yeah, I can certainly. Okay, I can put my slides up too, and then contact you, and you can do that.
Oh, sure.
The same.
Yeah. No, I'd be more than happy to link to them. Okay.
Great.
So let me see. Do we have any other questions? We're actually running a little bit ahead of time, but yeah, I think we're running a little bit ahead of time, Kevin. Well, I guess when you get,
for me.
Yeah, I know that's unusual for a conference too. Usually, let me see. Rob's posting videos up, so no, we'll say I'm not going to do the video quite yet, unless Rob had a question. Oh, there's Sean and Jeremy. Let me go to Sean first. Sean?
Hey, how's it going? Can you hear me?
Yeah. Can you turn your camera on, Sean?
I don't have a camera. I'm sorry.
Okay.
All right. I have a quick question though. Do you think Bose-Einstein condensate is taking place on the surface of the craft in order for it to be cold?
These are all good questions. I have no idea. I'm not sure exactly how I would go about trying to detect something like that. And
well, I saw in a document with Mirabos Technology, a guy was creating like a carbon glass over top of it, and then which was a great dielectric, and then he was making carbon glass with, I believe, excited oxygen. and it made it into a superconductor that could work under hot temperatures. And I believe that it was his idea that like when the microwave beam hits the craft, it creates Bose-Einstein condensate like all across the top of the entire craft, and it assists with the effect.
Oh, no, that's a good question, and I think what we're going to have to do is once we've collected more data and we see some hypotheses that may fit, more data is going to, the data we collect, we hope to rule out hypotheses as we go, right, and pare it down to a small set that we can deal with, and so once we have a small set of hypotheses, that will dictate what new data we might need and new instrumentation we might need. So this is going to be, it's a learning process, and it's going to be an evolution in our equipment that we use to record these things. And again, it's difficult because we can't overgeneralize. This may be, you might have one craft that creates Bose-Einstein condensates, and that's just that craft does that, and no others. And so that's one of the difficult points here. These things clearly are not the same, and they appear to be using different technologies, sometimes at different times. It's been noted in some cases that you've had discs take off, and they'll take off and make one type of sound, and then they hover above 20 feet above the ground or so for a moment, and then they just shoot into the sky super fast. So it could very well be that you're using one technology to get off the ground and another to get away once you're off the ground. And so things could be arbitrarily complicated.
Right on. Thank you very much.
Awesome. Thank you, Sean. Okay, so why don't we do this? Why don't we take Jeremy Reese, and then I think we'll probably wrap things up with questions, if that's okay, because I think we're running low on questions. And so Jeremy, go for it, sir.
Yeah, at this point, I'd recommend using a diverse array of technologies to see what works best. And it's going to be difficult because different craft may require different types of technology to best capture imagery or data. So I think at this point, using a diverse array of different types of cameras over multiple wavelengths would probably be wise.
Okay, wonderful. Okay, well, thank you, Jeremy, and Kevin. Thank you very much. So let me do this. I'm going to mute everybody out, and let me put it back on gallery view. And again, everyone, please give Kevin an enormous applause for an incredibly detailed and wonderful presentation, sir. Thank you very much, Kevin. And I know that you were juggling some scheduling issues also. So thank you for bringing it together for us. Okay, so next, again, we're a little bit ahead of schedule, but let me call on Tony, because next I believe we are looking at, and oops. There we go. Okay. Perfect. Tony, would you like to go with your presentation now?
It's fine. I'm ready.
Okay, well, let me do this then. Let me give you a brief introduction. Okay, and everyone, Glenn Tony Robertson has over 40 years of experience in propulsion, holds 10 patents, and has published over 20 papers on propulsion and power generation. He's also chaired numerous professional and technical conferences and played an important role in emerging and alternative propulsion research. Tony was also a key figure in NASA's experimental replication attempt of the Knuth rotating superconductive gravity shield experiment, and more recently, he's been a regular attendee and presenter at the APEC conference. Tony is far too humble to call himself a legend, so I will do it for him. Everyone, let's please welcome Tony Robertson, and let me hand it over to you, sir.
Okay. You guys want to know about the superconducting experiment that we did at NASA, but I want to give you first a history of it. Ning Lee wrote that paper when she was at the University of Alabama in Huntsville. She apparently met the center director of Marshall Space Flight Center, who probably invited her to come talk to him, which she did. And she got sent down to the preliminary design office to try to get funding, and ended up in Whit Brantley's office, who eventually ended up being my boss there in preliminary design. And he called me up, and so we got together with Ning Lee and decided to do a center director's discretionary fund to do an experiment that she proposed. And what she came to, the experiment she came to NASA to propose was actually to spin a superconductor about this size. It's about 3 inches high, about an inch in diameter, with about a half-inch hole, up to about 35,000 RPM. And we thought the speed was too high, so we focused the Center Discretionary Fund on the spinning device for that. And so in 1996, we spent about a year making some of these and looking into doing a magnetic levitation spinning thing and stuff. And then at the end of the year, when we went to propose for a second year of funding, we found out about the Pekletnoff experiment. And so we discussed it and decided that that might be a better experiment to do, since he was only spinning it at about 5,000 RPM instead of 35,000 RPM that he suggested. But what I wanted to point out was this device, that superconductor she wanted to rotate, is actually an experiment that was proposed by Rocker. Can y'all see my screen? Hey, Tim, can y'all see my screen? Let me share screen here. There we go. Can y'all see this screen? I don't hear anybody. Well, anyway, Robert Becker, the Master of Science thesis, actually proposed the experiment that Ning Lee came to Marshall for. So she actually wasn't her experiment, it was somebody else's experiment. Guys, if nobody doesn't talk to me, I don't know if you guys can even hear me. But we went on to do the Pekletnoff experiment instead of this experiment because of the slower speed, and spent about a half a year doing that. And then our management decided to turn it over to the science directorate. And when they went to the science directorate, they brought in a group of people from the science directorate. And this is the team that was formed from the science directorate. This is me, this is Ning Lee. Ron Kozar was put in charge of the team. This is Whit Brantley, my boss at the time. This is the big superconducting disk we had built to do this 11 or 12-inch disk. There's a paper that was put together that discusses some of the stuff we were doing at the time. But we never really did much of anything. Once this team was formed, there was really no organization. There was no accountability for what we were doing whatsoever. Ning Lee was charged with building the superconductor, but she never gave us the superconductor she built to even determine if they were viable for doing an experiment. Ron Kozar was off doing his own thing, making large superconductors too. I was doing off on my own thing, doing some superconductors. We all had different other jobs to do, so it was really just disorganized. David Nover did a few things. In fact, there's another second paper with Nover and COSAR on it that talks about the gravitometer, which really was useless, to be honest with you. But in the long run, we pressed superconductors, gave them to Ning Li. She supposedly fired them up. I did go to her lab once and saw some of the ones she fired, but most of them looked like they were partially in what they call the green phase, which is non-superconductive. So as far as I know, no big superconductor was ever made by Ning Li that was viable to do an experiment. And she never just wanted to prove that, so we don't know whatever. So the program ended basically in failure because of the disarray of the whole program after the science director took over. And then, so that ended at about either in the 97 or in the 98, where Ron Kozar was able to get an SBR through a company to relook at it. And they spent several years looking at it, and they had hired Knuth to help them design the disc and make the disc. It did make the disc, but they, in my opinion, wasted a lot of money, because once you give money to an SBR contractor, they can do anything they want to with it. Basically, they bought a Dewar for like $60,000 that was totally useless for the program. They spent a lot of money on Knuth, and Knuth basically used that data to put in his other papers on the impulse experiments. Some superconductor data that's in there is actually the data that the SBR people actually did. But they ended up failing too. They ended up making a disc. They gave us a disc. They gave us a dual magnets on it and showed that it would levitate. But then the program died and nothing happened. So basically, NASA paid 2 programs about the same amount of money, and they got to the same spot, and it never got finished. So, hey, Tim, can y'all hear me?
Oh yeah, no, I can hear you fine.
Yeah, I'm just hearing myself here, so I don't know if I'm talking to anybody or not.
Oh no, yeah, we're all here. We're just listening.
Okay.
I really appreciate you sharing this history with us also. I mean, because this is, I think it's incredibly valuable to have just better understanding of what NASA attempted and all of that.
And the other thing that people keep saying that Ning Li is probably in some secret laboratory. And can you see this picture that I got up?
It's still showing the NASA superconductor gravity team.
Yeah, or I'm on the left side, Ning Li's on the right side. I'm about 40 years old in this picture, and she's at least 10 to 15 years older than I am. I'm 67 now, so she's around 80 years old right now. So if she's in some secret lab doing any experiments, she's crawling around or with her cane is. But so I don't believe that she's off doing any secret stuff. I ran across a guy about 4 years ago who said that he had met Ning Li 2 years prior to that here in Huntsville. So at least 6 years ago or so, she was still here in Huntsville doing something. But as far as I know, after 2000 something, early 2000s, I never heard anything more about what she was doing. I know she got sick and went back to China for a year or so and came back. And I met her after she came back. And we talked a little bit, but she said she wasn't doing anything at that time.
Tony, if I could interject for just a second, I was going to wait on this for later because I think it was Jeremy or Mark that had told me. But so they had just found an obituary from Dr. Ning Li, and if you want, here, let me stop your screen share really quick. Okay, and let me bring this up, and then I'll do a screen share on this. Okay, and hopefully you guys can see that. So yeah, unfortunately, what it's saying is Dr. Ning Li of Huntsville, Alabama, passed peacefully on July 27th at 79 years old. She was one of the world's leading scientists in superconductivity, anti-gravity. She'd constructed the first 12-inch HTSD in the late 90s. And then it said that she's survived by her son, her grandchildren, and let me see, they have a plan for a celebration of life. And that was back, so she passed on July 27th. The celebration of life was on August 1st. So unfortunately, it looks like she's passed, and that's a tragedy because, she definitely was. She had recognized expertise, and of course, we would have loved to have her on APEC as well. So let me stop sharing there. But
my guess about her age was about right. She's 79. She's almost 80. But Ning Lei was an odd character to work with. She at some point in time, she would run to management and tell them to fire somebody on the team, including myself, because she would disagree with us or something. So I don't want to disrespect somebody, but she wasn't the angel that everybody thinks she was, as far as it goes. And so. But if anybody wants to know any more, I've got some of my paperwork from the Center of Discretionary Funds and the SBR, but I didn't want to share them on the video because don't even know if I'm supposed to even still have them. I'm supposed to kind of turn all that stuff into NASA when you retire and everything. So,
well, Tony, do you want to go to Q&A? Does anyone have questions? If you're open to it.
Yeah.
Oh, okay. Yeah, and actually, I had someone before the conference, and I forgot who had asked. Let me scroll down the list and see if he's still here. I think it was William Schramm. William, you had some questions about superconductors before the conference, right?
Hey, let me bring the video online. Yeah, so my questions were really, can this physics be evaluated with Gen 1 superconductors? Is it possible to use niobium instead of yttrium barium copper oxide?
I don't know that anybody can answer that because no experiments have been done. Even on the YBCO, no one has really ever repeated what Pekletnov did. Anybody who claims they have are lying or stretching the truth a little bit. I can't speak to what might have happened in projects that were classified, but I really don't think anything was done there either. But it's hard to say. If you read my paper in that gravity book that we did, then I tell you why a superconductor could create a gravity wave. But it could be any superconductor. It doesn't necessarily have to be. Well, I'll take that back. It probably has to be a type 2 superconductor, and the reason for that because of the flux pinning that goes through the superconductor. Those pinning sites are actually they're more superconductive actually than the superconductor itself. In fact, electrons can move through these pinning sites faster than the speed of light theoretically. So it may need to be a type 2 superconductor for this effect to occur.
Okay. And then the follow-on question to that is, well, what vendor do we go to for a disk like this, or do we have to make it ourselves?
The last time I looked, there wasn't hardly any YBCO superconductor manufacturers in the US. They were all over Europe, but it's not hard to make a YBCO superconductor. In fact, I came up with a formula for making the superconductors from the powders that was different than what you read online, read about in other literature, because the barium oxide, first bottle of barium oxide I bought, I opened the thing up and began choking immediately because that barium oxide wants to turn to turn into a hydrate, so it sucks the oxygen out of your nose and everything. So I immediately said, I'm not using that. And so I went and started using the barium hydrates. It's a different formula, but it came out very well using it. In fact, you could, once you do use the hydrates, you can actually mix it with water. Where if you I took some barium oxide and put it in a glass beaker and poured water in there, and it almost melted the darn glass at the bottom because the heat it created from absorbing the water and turning into the hydrate was so hot. But anyway, it's not hard. I can do it at home. I can get a little furnace here. I've made superconductor powder here at home.
Okay.
Yeah. Now, so if I could jump in really quick, William, one of the things that I'd mentioned to you, and this goes back to before the call because you were asking about superconductors then. Tony, as I recall, and I might be mistaken, but hadn't you said that there was a a skin that the crystal inside of the bulk of the superconductor is different than the crystal along the skin. And there was something about, if I remember right, there was something about the construction process that made that skin more important.
Well, Knuth supposedly did the two layer where the bottom layer was not superconductive at the 77 degrees of liquid nitrogen, where the top layer was. It was so if you dope the bottom layer with say YBCO instead of yttrium with a Y, dope it with like praseodymium or something, then it drops the superconducting temperature lower than the 77 Kelvin. And the top layer would be YBCO, but then it was supposedly melt textured, where they actually put little seeds of a different type of superconductor on it, usually where they're yttrium replaced with samarium, I guess, on top. And then what they did the melt grows, and so that crystallization should form across not only the YBCO top layer, but also the non-superconducting second layer. So the crystal growth through the whole body was not just centered superconductor, but a crystallized superconductor, and that can be important because in this crystal, it actually the crystal forms layers of these Josephson junctions throughout this crystal growth, and I think why those Josephson junctions are important to get the rapid electron motion to the superconductor.
Awesome, thank you, William. Did you have any other questions, sir?
I guess my question was, my experience is working with a German vendor on wire, and so they actually strained the wire in order to create the crystal boundaries. Is there any research into when you're making a disk, manipulating it in a way that creates those crystal grain boundaries?
Well, the only thing I know about crystal growth is that melt texture crystal growth. I mean, this was back in the late 1990s. There should have been a lot more research done since then, in the way they're doing everything. But as far as the experiment Knuth did, it was just simple YBCO melt textured with two layers, that one superconductive at 77 and one not. So.
Okay, great, thank you.
Wonderful, thank you, William. Gary, let me go to you next, sir.
Sure, yeah, I was wondering, Tony, if you've had any contact at all with George Hathaway. My understanding was he was trying to replicate the same experiment a number of years ago in Canada.
Well, I don't think he did the rotating one, but he did attempt the impulse one. And it's my understanding that the disk he used for the impulse was not two layered. It was not I don't know if it was the same size or not, but it's been a long time ago, so but what I remember is that he didn't do the experiment to the degree that Knuth did.
He never did the spinning one.
Huh?
To your knowledge, he never tried to replicate the spinning superconductor.
No, making a 12-inch superconductor disk is quite difficult, and which we learned, and making it two layer is even more difficult. And then putting it in a furnace and doing it. We never got to the melt texture. We never got to two layers. The group down to the SBIR did, but we never did. And so making something that large that comes out of furnace that's not cracked is just a miracle.
To your knowledge, George never got that far.
No, but he did do a version of the impulse experiment and didn't see anything, but I don't believe the superconducting disk was the same as that Knuth reported using.
Okay, thanks.
Okay, thanks, Gary. Let me go to Harold next, sir.
Yes, Tony, thank you for that explanation. That clears up a lot of things, because I know that Ningley got a lot of publicity, but you make a lot of things clear now. And my question for you is this, that experiment that Ningley was supposed to do, if it would have been you that had to do it, how would you have done it? And the other part of the question is, do you have a theory, a proportion theory, on how to use a superconductor to create, for example, artificial gravity waves, or a propulsion system? What are your thoughts on that?
You're asking a lot of questions that I don't think I can answer in this time frame. But first off, the experiment that everybody says it was Ning Lee's was not Ning Lee's. It was NASA's, Marshall Space Flight Center. She was part of that team. In fact, like I said, the experiment she brought to Marshall Space Flight Center wasn't even her experiment. It was Robert Becker's experiment, and actually a UAH student who did it as a thesis project. So when people say it's her experiment, it wasn't. She was just part of the team to do this. She was tasked basically in the first part in the Senator Greshner Fund projects, which I support her on that. She didn't do much of anything. I did most all of that stuff. And then when we went to the Pokletnov experiment, she was just tasked to actually take the disk we pressed for her at Marshall with using the disc that we bought under the project. And she took those discs back to UAH and fired those discs. And then she was supposed to give those discs to us so we could analyze it using, NASA's expensive technology they had there and see what the structure was. And so we can determine if we were actually making something correctly, but she would not give us anything she fired. So we couldn't do anything. Money ran out. We didn't have discs for her. We made some ourselves and played and stuff, but we never could. Like I said, once that team was formed, there was no accountability. You had 5 people going in 5 different directions and with no clear path on where we were going. And so that just failed. And then the SBR one had a clear path, but they got so focused on spending their money off, and then they, like I said, they bought a $60,000 doer that was just terrible, and they wasted a lot of money and couldn't finish the project. They helped Pokletnov out, but they didn't help us out. So, but as far as the theory, I've sent you my papers, but on A theory, but that one doesn't really talk about superconductors. But if you read my paper that's in that superconductor gravity book, it tells you why a superconductor could give you a gravitational wave. What else did you ask?
Actually, Harold, if it's okay, let me jump in really quick. Tony, can I put your book up on the screen? Can you tell me what the title of your book is?
Yes, yes.
Superconductor, crap, I don't even remember what the title is myself. Gravity interactions, superconductor gravity interactions, something like that.
It's available in Amazon.
Yeah, I can send you.
Here we go. Okay, and let me see. And you know what I will do? Okay, give me 2 seconds. I will share I'll share my screen again. And my apologies for jumping in and distracting. Okay, so here it is. I will paste this into chat, but for anybody who's watching this in replay or can't see it, it's Superconductor Gravity Interactions, published February 12th, 2018. I will maximize that there.
They were supposed to send me money when they sold this. I haven't made a dime off of it. This was published in 2012.
Yeah, so that is up here. I found it on Amazon, and let me see. The authors are Giovanni Modenese and then of course Glenn A. Robertson. So okay, and again, my apologies for disrupting things. Harold, did you have any more questions, or should we go to Jeremy next?
Hey, thank you for the explanation. That clears up a lot of things.
Okay, wonderful. Well, thank you as well, Harold. Jeremy, would you like to go, sir?
The pressure that you have to press these two is like 20,000 pounds per square inch. So we were using like a 1,000,000-ton press that NASA that actually were used to test some piece of the launch system for the shuttle. and if you don't press it to this, then it's not as dense when you put it in the furnace, so it wants to shrink, and so when it shrinks, it cracks. Even a lot of the smaller ones I made, rather than being flat on both surfaces, would be curved on the top, because the heat would be hot around the outside, so it would harden first on the outside and then sink in the middle on the smaller ones. So pressing is a key issue, and a press that big is not available to everybody.
Okay. Okay, Jeremy, thank you. I think Jeremy just dropped off the call. Let me go. We'll probably try and do 2 more questions if that's okay. Let me go to Michael Boyd next. Michael, sir.
Hey, so I have a couple of questions. One is that I'm curious. You talk about pressing it, and my understanding is there should be a relationship between the amount of pressure that's put on the superconductor and the properties of superconductivity. I think there's been some recent research where they've actually achieved like room temperature superconductivity, but only under high pressure. Do you have any thoughts on that? And then the other thing I'm curious about is as far as it relates to the gravitational field, my understanding has superconductivity, the way it works is it's kind of like antiferromagnetic. So it's only on the outside of the superconductor. It's a surface phenomena. It's nothing in the there's basically no magnetic field inside the superconductor. So I'm just curious what your thoughts are about that.
There's 2 different types of superconductor. One's a type 1, which exhibits the Meissner effects and excludes all magnetic fields. And then there's a type 2, which is what the YBCO is, that actually pins the fields inside of it. In fact, you can take a type 2 superconductor and cool it under a magnetic field, and then take the field away, and it'll still act like a permanent magnet, even though
so it's kind of like a dielectric. You know how, like with a capacitor, if you have like a dielectric material, you can charge it up and move it around and like plug it in.
Yeah, you can.
Kind of like that.
Yeah, I actually did experiments where I pinned the fields in the superconductor and then mapped the field that was on top of inside the superconductor. I actually did those experiments to show that. And this pressure you're talking about, it sounds like what you're talking about is not a pressure to press the material into making it, but to the pressure in a chamber, where they're testing it in a chamber pressure. So
it's in a pressure environment. Physical pressure during the when you're measuring the superconductivity.
Right. Yeah. Mm-hmm. It's 2 different things. So.
Okay. Thank you.
Wonderful. Okay, well, let's go to William Schramm, and then after that, we'll wrap up questions. But so William, why don't you go ahead, sir? And then after that, we'll go to Mark.
Just one more question. So instead of a disk, could you have just replicated this using a loop of wire? If you could anneal a length of wire to make the loop instead of a slice of a cylinder, would that generate the same effects, or does it have to be a 3-dimensional, have some depth to that plane?
Well, according to the paper I wrote that's in the book, it'd have to be a solid disk, because from my perspective of the paper is that you have to have these Josephson junctions. That's what's important, because the electrons can move across these junctions at very fast speeds. And in a wire, you wouldn't have that. And the currents you would be putting in that, if you're talking about a wire, going totally different directions. So, but it's not to say it wouldn't show some kind of effect. I just don't know.
Okay.
Wonderful. Okay, so let me go to Steve Lutz really quick, and then after that, and again, my apologies, I'm trying to juggle time here a little bit. Steve, why don't you go for it, and then after that, we'll go to Mark Sokol.
Yeah, sure. I just have two questions. One, do you know who the program director was for this this SBR?
For the SBIR, Ron Kozar from NASA was the one who initiated it. So I would say he was the NASA manager part. But the SBR program itself has a manager at a headquarters.
Right.
So who's actually in control? I couldn't tell you.
yeah, that's a lot of these programs. It's the money goes out the door, right? So you were peripherally involved, like in a support capacity, or directly involved with this whole thing that we're doing here?
When Ingley came to Marshall, I was the one who wrote all the proposals for going to NASA management, but I wasn't at that time part of preliminary design. I was still in the propulsion lab at that time. So Howell was actually the guy put on as the PI. For those Senator discretionary funds, but I'm the one that actually wrote the proposals and did most of the work. Joe Howell was the one who found the manufacturer for the die.
The YBCO?
Yeah.
I mean, I started my career as a specs writer and the proposal writer, so I know exactly what you're talking about. Yeah. You're just cranking paper.
Right, but by the time I moved to preliminary design, we had already formed this team and gave basically the lead to the science directorate. And once that happened, like I said, it was just 5 people going in 5 different directions.
Right. So no EDR, no engineering design review kind of thing. It was just sort of go for it, right?
If there was any, if there was anybody reporting to management, they didn't invite me.
Yeah, I'm in the same club. I never got invited to like once or twice, and they said, shut up and don't talk,
But we spent so much money on it that no one wanted to ask for any more to continue going.
It's embarrassing, right? Because you blow out that money and no results, and then it's the blame game, right?
Yeah.
We used to have the wall of blame and the wall of shame. The pictures of the people. So my other question is this: the YBCO, are you privy to the crystallinity of it? I mean, the manufacturing process, would they cook it slow and then hydraulic press it? Was it polycrystalline? Was it high order poly? Was it near mono? Do you know any of that stuff?
I know how to make the superconductor. I know how to press it. I know how to melt texture. I've done all of that. The disk that Kletnoff actually had, from my understanding, he did not make the disk. He borrowed it from somebody else. Correct. Who made the disk and literally didn't know much about the disk at all. That's the reason why when they went to the SBR and hired him, he kept having them do this and that and was wasting a lot of money for him basically to learn how to make a disk for himself. But the disk basically, making the powder is you just take the raw materials, you mix them together in the right in your furnace. There's a heat profile you go through, and then it comes out and it's centered a bit. You have to crunch that up into a powder. Then you take that powder, put it into your die, press it, like I said, to 20,000 pounds per square inch, and then you take it out of your die and you take that and put it in your furnace and heat it through a temperature profile. And if you want to melt texture it, you have to go redo that with these little seeds of a different type of superconductor on it.
That's all correct.
Crystalline growth, and the crystalline growth is actually the 8-sided
Yeah, it's hexagonal. That's correct.
Hexagonal, and it starts out like a pyramid and goes down through the materials.
Yeah.
So,
and one of the things you got to do is mill it for like a day or two, right? So when you get the powders and everything, you got to mix them. Just keep it going.
That's the way you normally do it, but that's not the way I did it. I just grounded it up till it looked like a nice powder and shifted it through some sieves. And when I got enough that went through the sieves that looked okay, I forget what size, but very small grain sieves.
Right.
I think it's micrometers that you had to take it down to.
You get these micrometer crystals, and then you grow it low and slow in the centering.
Yeah, It takes days, even
Days,
weeks if
yeah.
you do the.
That's right.
Put it under oxygen to oxygenate it can take you a week long to do that.
Yeah. So what I've seen is that if you can get the crystallinity up instead of like polycrystalline, if you can get the crystallinity to be more organized, you can get some more interesting effects out of the material. And spinning is not a thing. It's not. I know Podkletnov thought it was a thing. You know, spinning is critical. It's actually turns out not to be the case.
I don't think Podkletnov was originally doing this experiment as a superconducting gravity experiment.
No.
From my view, this is just my view of it. I think he was actually trying to do an experiment to see if superconductors could be used as a radar deterrent type of material.
Yeah, it was a military thing. That's right.
That's the reason why he was hitting it with RFs, is to see how the signals would come back. And what had happened was a professor had come in there smoking or something, and the smoke.
That's all correct. That's 100% right.
In the air. So his initial experiment was not a gravity experiment; it was something totally different.
Yeah, he told me directly what happened. It was exactly what you say. It was a military thing, you know, for the anti-radar, low observable stuff. The guy came in smoking. As you know, if you work in these labs in Russia, and I have, and in the former Soviet, everybody comes in smoking and drinking after hours. Everybody, you know, it's cognac, it's smoking. Yeah, it's hilarious.
Play smokes.
And they noticed the smoke drifting up, and then they went upstairs and they saw it was still going on, and they went up to the roof and they saw the effect was still there. So in the end, yeah, I mean, he's a metallurgist kind of guy. He's a master's guy, right? So the guys that made the actual disc he was playing with were another group altogether that knew what they were doing. But I'm always fascinated and interested in the crystallinity, because when I looked at something that, for example, Claude Poher was doing over in France with this YBCO, he had even worse crystallinity, but he did multi-layer. You know, he did like 12 layers, I think, when I was there.
I've been to Poher's house in Spain.
Yep. And some interesting effects came out of it. But they're all using pulse Marx generators.
No.
Everybody, right? So Marx generator, they do a pulse. It's 100 milliseconds or so, tenth of a second.
That was the impulse experiment he did, not the rotating one. Yeah. And Poher's experiment, like I said, I've been to Poher's house in Spain. I saw his experiment there. And he basically was just making a big arc in liquid nitrogen that was blowing the liquid nitrogen around. And some guys at Marshall actually repeated the experiment, and that's the same conclusion they did. And that was the conclusion I came out of Poher's house with, is that it was just an arcing effect.
Right. My thinking is that a sustained DC with an AC ripple and the AC ripple being at a high frequency, perhaps terahertz range, something like that, might yield some, I don't know, interesting results if we were to try it.
Yeah, terahertz is an interesting range to be in, and it's just relatively new as far as being able to do that. So
you can get the terahertz generators right now. I looked it up, but it's just a handful. They're very expensive, and you have to know what you want. You know, you talk to the manufacturer. You say, I want something that does this, and they give it to you. Mm-hmm. But I say, if you want, I want something in a range. Well, no, we can't do that.
It's still relatively new technology. They were developing it years ago. I was reading articles where they're trying to develop terahertz sensors to penetrate the ground to find tunnels.
I saw that. Yeah, I was looking at indium phosphide as a possible candidate to do that. But again, I talked to a manufacturer about it, and they're like, "Yeah, we're doing it for high-speed switching. That's it. Yeah. Where's the money, right?" All right, thanks. Appreciate your answers.
Okay, thanks, Steve. So let me see, Mark. Are you ready? Or let me ask Mark.
Yeah, so I'm trying, I have a little surprise for you guys here. I'm trying a replication.
Let me, we should say thank you to Tony first, and I should apologize for that.
Thank you.
Yes,
okay, yes. So let me do that then. Let me do that, and we will come right back to you, sir. And again, okay, so what I'm going to do is, before we do anything else, let me go to gallery view, and everyone, please put your hands together and give Tony an enormous hand. Thank you. Tony, thank you very much. It's wonderful to have historical insights into the past research that's been done, and actually I'm really excited. So let me put, and I should apologize that we kind of ran out of time there. Let me put the hands down there, and I'm going to go over to Mark, and I will spotlight Mark for everyone. Okay, go for it, sir.
Okay, so we're actually going to try some sort of spinning superconductor experiment over here, and if I can get the scale to run, we'll actually be able to see if there's anything going on. I got some liquid nitrogen here at the lab, so start off with just a simple demonstration of superconductors. In here we have a small YCBO superconductor. And many of you have probably seen this presentation before. Let me go a glove or something. It is kind of cold. I almost got a burn before. That's better than nothing. And the superconductor over here, the YCBO, which is type 2, actually got quantumly locked to the magnets, and it's kind of floating around. Not doing that great of a job because of the foam is locking it in place. Over there you can see it floating. The next thing we have here, which is basically magnets with opposing magnetic field.
And Mark, I should mention that we can't hear you. I'm not sure what might be going on there.
Okay, is that better? Can you hear me now? Okay, perfect. Okay. Just hold on one second. We're still getting there with the the liquid nitrogen. This is going to take a couple of minutes. It's a pretty large disk. So I have it inside of like a foam cup here. And I'm not sure if you heard this earlier, but the magnetic field lines, in order to hold this disk in place, we got north in and then south in. It's basically alternating. This was a design that Jeremiah Pop suggested the other night. For a scale measurement, I actually have a NASA Huntsville mug that I got when I was down there. And I'm going to try sharing screen and getting the weight measurement of that mug on the screen. I had it up a moment ago, but it was we were running into technical difficulties when the measurement wouldn't really change much. Logger light, here it is. Tim, if you could unmute everyone or let people unmute, that will be helpful, because like if anyone has any questions, I can answer them in real time while the superconductor cools
Okay.
down.
Yeah, so I just enabled it to allow people to unmute themselves. And let me see. It looks like Remy had some questions. And I guess, guys, just try to, oh, no, Remy, go for it, sir. Go for it.
Mark, how you doing, Mark?
Hey, I'm okay.
Yeah, we lost your sound just as you got out of the chair to do the second video. You lost all your description of what you were doing. Can you run it by us
Okay.
again?
So what we're doing before is just giving you a that was a proof of concept of the Meissner effect, and we had the superconductor running along a little track. So it gets locked in.
Yeah, not that one. The second, we saw this one. You had sound up to this.
Oh, okay.
One. It's the
Okay,
second
great.
one. Yeah, the second one. We lost all description of what you were doing.
Oh, okay. So I'm still cooling off a superconductor over here. We're trying some sort of replication of the spinning disk experiment. There's 6 bar magnets printed inside of it. The bar magnets are polarized axially, and it's attached to a motor base over here. This thing can spin pretty fast, faster than I would want it to spin. The mug over here is hooked up to a scale that is actually connected via USB back to the laptop. And I'm going to try to do a share screen so I can give you the live data from my laptop. Let me see. There we go. Share screen. Okay, so you can see. Now you should be able to see both the experiment going on and the sample measurement. Now I was having trouble before that that it wouldn't zero. Like it seems to be frozen. Yeah, and it seems like it's doing it again. This is an issue I was having earlier. Resetting it. Can't get a measurement. Yeah, it's moving a little bit now. Let's see if I. Nope. Nope, I got nothing. It like works for a couple of seconds and then it stops working. Anyways, I don't want to keep you guys waiting too long. I'll just power it up and we'll see what happens. And
Mark, are you going to be okay spinning that? I don't want that nitrogen to fly out and get you.
I'm not worried about the nitrogen. I'm worried about the magnets, actually.
With them too.
I mean, yeah, this shit can really hurt me. The magnets can hurt me, not the liquid nitrogen. Oops. Okay. It needs like a little bit of a startup. That's on Tim. That's not on me. The forceometer's not working. Not changing at all. I can blow some smoke over it, see if there's any upward smoke.
So, Mark, if the forceometer isn't working, why don't I just unshare screen then?
Yeah, stop sharing. No, the forceometer's not working at all. It's showing the exact same number even when I lift the cup up completely. So it's obviously not working. I'm curious what Tony thinks of this this replication. Is Tony still there?
I'm here, being quiet. I think the superconductor's too small to see an effect.
One thing that's kind of interesting is we got the superconductor locked into the fields, and every time you turn it, like you see when I get the magnets over 60 degrees to the next polarization point, the superconductor wants to float up.
Yeah, it's acting like a magnet because it's pinned the flux in it.
Right. So I wonder what would happen if I got all the magnets spinning and held the superconductor in place. 1 second. Oh shit, this is cold. They get a better glove. 1 second. Yeah, we have them for a reason. It feels really weird.
Well, the superconductor is acting like a magnet, so every time it magnet field, you should feel it like going up and down as the field's changing.
Yeah, that's what it's doing. Pretty strong.
Yeah. It traps the field pretty well. Like I said, I mapped the field after trapping it once, and it's pretty strong.
Oh, it's vibrating pretty nicely.
Mm-hmm. You're doing something a little differently.
Sounds like those the female massage toys. You can really get up there with the frequency as the RPM rises. Wow, it's a very interesting toy to play with. I think the scale measurement might be broken, so maybe later in the second half of the presentation, if I get that fixed by then, I'll do a rerun on it or just try a new scale. Because I do have a backup unit, so yes, yeah, because that's how Podklenev claimed there was weight loss. It was measured above it. So I had the mug over there, but the scale is not working correctly right now. And
you know, Mark, Remy put this in chat. He was wondering if you could improvise a balance with a stick and a lightweight.
There was nothing in the mug. No, just a piece of ceramic.
Yeah. We did a lot of this stuff with rotating small discs. We never saw anything.
I mean, I could figure something out. It's going to take at least a half an hour. So
yeah, well, we could try it later during open session.
Yeah, we could try it again during open session. And by the way, I'm wearing the glasses again, not for the liquid nitrogen. This thing is 3D printed, and at the speed it's rotating, I've seen things fly off it that can possibly even like break skin. So it's pretty Yeah, rotating large masses is dangerous.
Especially when they're cold. Because
Yes.
it's more brittle. So
Yes, that
yeah.
is true. That's why I have
okay.
it.
Well, should we do you want to go to while you're working on this then? And Mark, thank you for the
I mean, if
presentation.
anyone has any suggestions or questions about the setup, I would love to hear them right now. This way we can work on it.
Okay, yeah, let's do that then. Let's do that. So here, I'm going to remove Spotlight. Let's do Q&A then. And anybody who has questions, go for it.
Suggestions, yeah. Oh, we got one right here. That's a great idea. I could put that on the lab to-do list. Also, while you're down here, we need there's like a faucet connection behind the CNC machine that needs to get hooked up.
The nitrogen tends to go to the floor because it's cold. So,
yeah, I have it.
So just be careful that if your room's closed too much, you can fill up with nitrogen and you suffocate. But it does tend to go to the floor instead of up because of it's cold. I think nitrogen may be actually heavier than air too, as it goes down. We never had a problem suffocating or anything in a room like you have, but you just have to be aware that you can.
Right, we have an oxygen sensor to measure the oxygen levels in the room. We check that out every once in a while. I do like to air out the room a lot, and I'm particularly sensitive to very high levels of CO2. So, but I think this is different because this would be suffocation, lack of oxygen.
Yeah. Just be careful.
Okay. Yeah. Does anybody else have questions for Mark?
I have a question.
Yeah, go for it.
What did you expect to see from the meter? And is it something that you did before?
No, this is the first time I did it. I was literally epoxying the magnets onto this disc at the beginning of the session. No, it's not something I've actually tried before, and we try live experiments here for the first time. Everyone can see the results. But we were hoping to see weight loss. I wasn't expecting to see weight loss. I would have been shocked if I saw weight loss. And yeah, that's pretty much it. One note, though, is that the superconductor disk over here is not very well built. I think it was like a homemade project or something. It's covered in like tape. Here's a second one that I got from them. It's covered in this like tape, electric tape kind of material. And when I opened that up, I saw it was full of cracks. So it's not a single domain. There's a lot of domains in there. I don't know if that's good or bad for this experiment. Tony, was the disk made by NASA single domain or multiple domains?
The large ones we made, we never made one that wasn't single layered, so we didn't do a melt textured on this. But I did some small ones that were melt textured that were quite well. We also acquired about a 4-inch disc from Oak Ridge that was melt textured, and it was very, very good superconductor, but exposing it to the liquid nitrogen and the moisture that it collected, it just deteriorated over time, fell apart.
Okay.
Mark, another thing I think we should do is get a data acquisition device and find a way to actively measure the temperature of our superconductor disk with like a laser, or some other device that I can take that data and put it into a computer, and I'll build a LabVIEW program, and we can actually take live data on both the weight loss and the temperature and all these other factors.
That would be a great idea. If we're getting weight loss, to definitely take all those measurements.
Yeah, we're just messing around until we get something. Then once we're ready.
Yeah, we want to see a result first before we start, going crazy for every single last bit of data. You want to see that there's something there before you start looking at every single leaf of the tree,
but Knuth used a frequency around 3 megahertz, and that seems to be a magic number for this YBCO. We did some experiments that actually showed that the 6 megahertz cosmic radiation going through the superconductor actually turned into 3 megahertz radiation. So spinning this this slow may not ever see an effect from it. You need something that's going to give you some.
What kind of RPM would be looking for?
Go figure out what 3 megahertz would be with your magnets passing by it. It'd be pretty fast.
Oh, okay. So that would be 6 times the. Oh my God, yeah.
Well, what if you could put a 3 megahertz signal on it, right? Maybe you don't necessarily need to. In fact, I've been seeing stuff in chat where they're saying, and I think Knuth might have suggested this himself. Maybe rotation isn't required at all. Maybe just try putting a 3 megahertz signal on it and see if that does anything.
I would agree with that. I don't think rotation is that important. It's the flux pinning, the superconducting junctions, and the frequency that you put on are probably the 3 important things. And
One thing that I remember that Knuth said that the effect was greatest as it was slowing down or something like that, between 3,000 and 2,000 RPM.
I could agree with that because such changes tend to give you effects you don't see in a steady state.
That's pretty interesting. Yeah. So another experiment I wanted to try was to have the superconductor being held in place while just the magnets that it's flux pinned to are spinning. Like we saw before, just if we can get that weight measurement in as well, and see if there's any weight loss.
The magnetic fields, when they're locked into the superconductor, in fact, the magnetic fields are locked into a magnet. Even though we rotate them, the fields in the superconductor or the field of the magnet won't rotate. It's the field outside it that rotates.
Right.
Okay, well, so let me go to Michael. Michael has a question, and then after that, let's go to Ken Griggs, our next guest. But let me go to Michael first for a question.
Okay, I'm waiting for him to come back. He's a mad scientist.
What's up, Michael?
Oh, not too much. So, first question. Maybe you need one of those $50,000 doers.
The one I got on Amazon for $1.99 is working just fine.
Okay. So my one question I have is maybe if you could design a kind of like a thermos jar which had a cold finger. You know, when I used to work on these, they used them a lot in the AR detector world, and basically you had this fancy doer, and it had a cold finger, a piece of metal, non-ferromagnetic metal that would sit. So you fill up you fill it up on the side, and then this thing you would be able to like clamp it in there, and you wouldn't have to worry about filling it with the liquid nitrogen and the nitrogen being thrown around, because it's contained in this cavity, and the metal plug that the superconductor is in thermal contact with it. We used to use a piece of indium metal to stick it to it, and that way you could rotate it around and you wouldn't have to worry about it. And then the other idea I thought you might consider is, instead of having a cup, you have something that has a low gravity compared to the ambient environment, like a balloon, for example. A balloon, like a Mylar balloon or something, that basically it's sitting there. It doesn't take a lot of change in mass for it to move. Follow? That big hunk of ceramic that you're hanging over there, it's got a lot of mass in it, and if there is any effect there, you won't see it.
The issue with a Mylar balloon is you're looking at airflows at that point. They're very heavily affected by airflow.
Well, it depends on how far away it is, I imagine.
Yeah, well, also there, do you think that could work the other way too? Because you've got more mass there. So if you have a gravity effect, it has more to affect as opposed to Mylar where it's so lightweight that maybe it's reducing the gravity, but you know what I mean?
Right. Well,
Yeah,
maybe
good point.
my point is maybe something different, like a metal balloon or something, like a sphere, a hollow sphere or something like that. Just my idea is that you have too much mass there. You have a little tiny superconductor puck and you got this big mass that you're trying to move. Make the mass relatively the same magnitude, and then I think you can see the effect.
I mean, if it is a gravity shielding effect, you'd want the mass, and you're only looking at like 1% gravity weight loss or gravity shielding. You'd want your sample to be as heavy as possible so that you can see that, get better resolution on it.
It's just an idea.
Yeah, something to try.
I'm guessing.
Okay, well, so let's go. Let me see. I think William Schramm had a question. So let's go to William, and then after that we will go to Ken Griggs.
Oh, I guess I just had a suggestion. Maybe we get Cryomech to sponsor this experiment so they can actually like put a cryo cooler in there instead of liquid nitrogen. So you instead of asphyxiating yourself, you might just try putting a refrigeration unit there.
I don't know. This thing weighs a couple of ounces. How heavy is the refrigeration unit?
It's quite heavy, but nevertheless.
I guess there's your answer.
Something that you could operate. That's another core skill.
Yeah, okay. You gotta weight light and small.
So let's do this then. Let's go to let me put it back on. So first of all, everybody, let's give Mark an enormous hand for his demo so far. Mark, that's an awesome demo, and it's wonderful to be able to follow up Tony's presentation by talking about that as well. So let me do this. I'm going to mute everybody out really quick. So if possible, I would like to get Ken Griggs in. So I want to do an introduction. Ken Griggs, he's been here before. He has a bachelor's in theoretical physics and aerospace mechanical engineering from Princeton University, master's in theoretical physics from University of Maryland, mentored by Jim Gates in superstring theory and Sasha Migdal in simplicial quantum gravity. He's also a former software engineer for the DoD via GE Aerospace, Martin Marietta, and Lockheed Martin, former patent examiner for the USPTO, former CEO of Imagine Studios, co-inventor with Jeremy Reese of Huther Brothers, and the inventor of Phoenix Theory for 31 plus exciting years. Now, so Ken is joined today. He has a co-presenter, Drew O'Meara. Drew is a Cornell grad in computer science, former U.S. Navy 688I nuclear submarine officer, former CTO of Sound Spectrum and now Plan Systems, veteran software developer, building software platforms for over 25 years, and an inventor with licensed software to Apple, as well as a specialist in 3D technology, information visualization, and distributed systems. So Ken, I would like to introduce you. Let me hand things over to you now, sir.
Thanks, Tim. I really, really appreciate you guys inviting me back again. This time we've come with my friend Drew, who is for Phoenix, our Grand Wizard software engineer. And what we really wanted to do today was to take a step back a little bit with Phoenix and introduce it in a way that it's usable for everybody. I think the last time that we actually talked about Phoenix, it was a little bit over the edge. So Drew had a fantastic idea to make it actually something that people can use and work with. I can't see Drew, but Drew, if you're there, can you just
hello. Hi everyone, Drew here.
Okay. And so we're going to start the presentation and share the screen. Yeah. Okay. There we go. Are you guys looking at my screen or? Try that again.
Yeah, so it doesn't look like it's shared yet.
Yeah. This is still new technology for me. So
While Ken's lining that up. Oh, here we go.
we got it. So welcome back to Phoenix, except this time we're going to do a 101 on it. So thank you, Tim, again, for giving a little bit of an introduction to who I am. So I've been doing Phoenix for 31 years.
Ken, sorry. So you're in screen sharing mode, but it looks like you need to click OK and select the screen. It's not quite there yet. It says you've started screen sharing, double click to enter full screen mode. And my apologies for interrupting you, sir.
That's all right. That's all right. Okay. Yeah, let's try that again. Still no?
Nope, it looks like it's still waiting. Again, it looks like it's kind of halfway there. You've started screen sharing. It's got the split screen on mine, but it's not. There we go. There we go.
That's it?
Yeah.
Yeah. Desktop. We're getting closer, Ken. I can feel it.
Okay, I will mute myself out now. And thank you again, gentlemen.
Yeah. There we go.
Okay. Yay. Okay, so again, sorry to kind of waste your time with a little bit of that stupidity there, but so we're Drew and I are going to be co-hosting this presentation, and we want to take you from really a workable beginning. Last time we kind of got really deep into how Phoenix works without maybe helping you to understand how to really assemble the pieces. So we've already gone through an introduction to me and Drew a little bit, but we certainly wanted you to be able to read these slides at some future point. So I'm very happy to have Drew on the team because he's such a wonderful computer scientist, and he's given Phoenix all new insights into how to actually build up a workable algorithm for anybody in the future to be able to do particle physics using the algorithm. So Phoenix technically is a theory of everything. And that's a really big statement, you know, everyone knows, but what we want to do, at least in this presentation, is to help you to understand how do we get to that kind of a statement by showing at least how we get a standard model a little bit out of Phoenix. So what we're able to explain in Phoenix very simply are things like lepton flavor universality, which is a very big deal right now at the our CERN collider. Also, in the future, we'll talk about dark matter. We'll explain why there's an asymmetry between matter and antimatter, which is still a very hot topic in physics. We'll demonstrate why general theory of relativity is really an emergent theory and not simply a ground, you know, sort of at the same level of quantum mechanics. We'll then engage later on, not today, but later on to demonstrate how do you get quantum gravity out of all of this stuff. We'll be able to simply talk about why the proton is actually what one might call a fundamental particle, as opposed to a particle that actually breaks apart. And we'll also be able to explain today the number of quark generations. And you guys might be aware that there are 3 quark generations, but we'll be able to assemble that from what we talk about today. So the standard model presents physics as a set of continuous particle fields that interact on a flat space-time background. So Phoenix presents physics basically using graph theory. And what's important about it is that there are very simple construction rules about how do you assemble particles and what constitutes a particle, and also what constitutes how particles interact and how they transform. So Phoenix very basically uses vertices and edges in order to combine these vertices that we'll talk about into particles. So in this assemblage technique, one often finds that there are many particle types that are very much not interacting. And what we demonstrate is that these particle types actually constitute what we want to call dark matter. And so the complexities of how particles actually interact and how particles are assembled and how particles degenerate is very simply explained in this framework. So, okay. There we go. So these are some examples of actual legitimate graphs. These graphs actually constitute what we want to call particles, but again, we'll get into that. Let me go back one. My apologies. Sorry about that. Okay. So again, these are actual graphs. These are legitimate. These are particles, but we're going to explain how do you actually see particles from this stuff. So here we are. What the heck is a particle? So in Phoenix, particles are simply constructions of attaching various vertex types. Right here, we're showing on the right-hand side that there are 4 basic types of vertices. The first one we call a gamma vertex. We'll find out later on that it really describes a chunk of energy. The second one we call a down vertex, which obviously we're naming because it really is the down quark. The third one is an up vertex, the up quark, and the final one is an electron. Now, what you'll certainly notice is that each one of these vertices has 3 connections associated with it. Those 3 connections allow this vertex to either be connected to itself. When you see a loop, that's a vertex connected to itself, or it can be connected to another vertex. But in Phoenix, every vertex has to be connected in 3 different ways, and these are the 3 ways. Now, when one is trying to understand what the heck is a particle versus what is not a particle in Phoenix, again, we just showed you 3 different building blocks, vertex building blocks. But as you notice in the middle there, these are 3 particles. These particles are obviously constructed from building blocks. But if one is looking at what's not a particle, we have that on the right-hand side. And what we're trying to show is that a particle must always have vertices that are all connected in this way that you see in the middle. That is, that every vertex is really directly connected to other vertices in 3 different ways. And that constitutes a real measurable particle. Now, one asks, well, okay, so what are these building blocks if they're not real particles? And we actually just said to you in the prior slide that, like with the down quark and the up quark, that's why they constitute quarks. Quarks are not particles that you can actually measure in and of themselves, if you know much about particle theory. And the question has always been, well, why is that? And what we're demonstrating here in the middle, for example, is that they always have to be connected. That's what constitutes an actual graph in Phoenix. So it does help to resolve one of the critical questions of quark theory, which is why you can never actually observe an up quark or a down quark or a strange quark or a charm quark all by themselves. These graphs constitute that reason. So here we have actually examples of fundamental particles that actually are these constructions. So we've got the electron, which is a beautiful particle simply because it does not require being connected to other vertices. And in that way, we begin to understand why the electron shows itself in our measurements as a point particle. However, these other systems do not exhibit that point particle consequence. So the muon and the proton and the neutron, et cetera, Now, when we get back to the muon, we'll demonstrate eventually why it seems to also have this point particle measurement property, even though it looks like there are 3 vertices. Okay. Now, when we were just talking about these up quark and down quark and pieces of energy, or these gamma vertices, what we didn't talk about is that how a vertex actually connects to itself. It can take on 2 forms. When a vertex connects to itself in a positive way, we call that a loop. However, a vertex can also connect to itself in a negative way. Now, this kind of a construction allows Phoenix to accommodate a new concept, which is antimatter. But it is very consistent with graph theory that you allow for these 2 different types of connections. So in the end, we go from what we thought were simply 4 vertices to now actually having 10 vertices. And these are the building blocks of Phoenix. Now, there was a long time ago when I was working with Jeremy that he actually gave a great word to these building blocks, and he called them the atmos, which I'll let Jeremy explain if he wants to a little bit. But this atmos concept allows us to think about the building blocks in terms of how we see quarks and how we see matter. That there are really, normally there are 3 types of matter. There's energy, there's matter, and there's antimatter. However, in this conceptualization, we have a 4th type, and we call it queer matter because I happen to be gay. But it's also because this type of matter is almost a hybrid between matter, antimatter, and energy. And this hybrid type of matter, this queer matter, actually has some very important properties in particle physics. And in fact, one of the most important properties is that it constitutes the weak nuclear force, that trilogy in the bottom. And so the weak nuclear force comes about because we have this pi plus and this pi minus, which are actually, in this case, acting like W plus and W minus vector bosons. And then this queer quark, which is a very interesting particle, because it doesn't actually have a measurable electromagnetic effect. In other words, when you actually see this particle, it's really difficult to measure it. And one of the ways that we can see it is that it appears when it binds to itself as a Z0 particle, which happens to be the 3rd vector boson that's associated with the weak nuclear force. But the beauty about these 10 vertices is that they nicely partition themselves into the things that we call matter and antimatter and energy. So here, what we want to show is a simple assemblage of these various vertex types that give rise to the particles that we can measure and call particles. So in the first case, we find that an up quark can be assembled into with an anti-up quark to form what we would normally call a neutral pi meson. In the second case, we're going to take a d quark and assemble to it an up quark and another up quark, and thus create a proton. And in the final case, we're going to take a chunk of energy and assemble onto it an up quark and then 2 down quarks. And that is what constitutes a neutron. Now, how one actually works mathematically with these structures is using matrices. So every one of these wonderful graphs actually has a corresponding matrix. The matrix approach is really the essence of how you, again, work with Phoenix. We will demonstrate much later on, and hopefully in future presentations, how you get to use these matrices to see all of the defining properties of these particles, but also how they interact with each other. So in the first case, this very, very simple one vertex particle is what we call the electron. It's very simple. It only has one element in its matrix. However, in the second case, we have a photon, which has two vertices to it. And as we'll notice on its matrix representation, the off-diagonal elements are actually composed of threes. We'll get to that in a moment, but the on-diagonal elements are actually composed of zeros. And that's simply because there's nothing on each one of the vertices is not self-connected. Now, in the third case, we have an electron that's being added to or interacting with a positron. And as you can see with the matrix form, the electron takes on the +3, the positron takes on the -3. And then in the final case, we have a proton that we were talking about before that has two up quarks and one down quark. Now, how one builds a matrix from these quarks is not actually that difficult. The first thing you want to do is to identify with a label, namely number 1, number 2, number 3, what the vertices are. And so this particular mapping here tells you how to take what's happening to a single vertex and give it a value inside of the matrix. So for example, if we're dealing with edges, then if two vertices are not connected by an edge, then in the matrix representation, there's a 0, an off-diagonal 0. If there is an edge between two vertices, then the off-diagonal element has a 1 if there's a single edge connecting it. If there are two edges connecting the vertices, then there's a 2. If there are 3 connecting the vertices, then there's a 3. And because every vertex exactly has 3 things on it, there can at most be 3 edges. So if we go to how a vertex connects to itself, we find the same thing, which is a vertex cannot have something on it. And on the diagonal part of the matrix, it will have a 0. It can have one thing on it, in particular, let's say a loop, then you put a +1 in that space. If it is a arrow, we call it, you put a minus in that space. If there are 2 loops, you put a 2 in that space. If there are 2 arrows, you put a -2. And if you have an arrow and a loop, you add their values together. So a 1 and a -1 gives you 0, and you put a 0 in that space. So again, that's just matrix construction. So let's show you what can happen when you're actually using this matrix representation. In this particular case, we can explain pair production, which is very simply, how does a photon actually spontaneously become an electron and a positron? The way that's represented here is that the actual matrix for the photon has 2 zeros on the diagonal, 3s on the off diagonal. But strangely enough, there's a transformation, what we call a similarity transformation, that will take that matrix representation and turn it into an electron and a positron, which is what we've been talking about all along in terms of the types of particle graphs that can spin off here. So we have a photon becoming an electron and a positron, and we can also show that you can have an electron and a positron that can be combined to show the same photon. And again, all of this can be performed with the matrices. And so in the end, how Phoenix represents this back and forth transformation between a photonic system and an electron and positron is just with a nice double arrow at the bottom. So we have an electron and a positron that can equally become a photon, and a photon system that can become an electron and a positron. So it's very nicely, quickly, neatly represented. Something a little bit more detailed would be, what the heck happens when we have a neutron? So what we're representing here is a free neutron. In other words, there's nothing really happening to it. If you look on the left of that neutron, we have its matrix representation. And what we can demonstrate in Phoenix is that through this, you can have 2 possible transformations. In the first case, we have a proton and pi meson that spins off. And in the second case, we have a very, very, very rare phenomenon where you can actually spit out an electron and a very strange particle that comes along with it for the ride. We'll be talking about that in a much further lecture if you guys are interested. But this is what happens to a free neutron in Phoenix. Now we can make that a little bit more complicated if the neutron, it might be in association with the photon anywhere in the vicinity. And in that case, we have a secondary thing that happens to a neutron when it decays. That secondary effect can actually be seen in the 1, 2, 3, 4, 5th line here, where we see that the neutron in that photonic interaction can actually spin off an electron, an anti-electron neutrino, and a proton. And so what we're demonstrating here is that how the neutron interacts as it's just sitting around in space can actually spin off what we really do know as the second type of a particle reaction dealing with the neutron decay. That is that it turns into a proton, an anti-electron, neutrino, and an electron. But there's a lot of other stuff that can happen too. So the standard model, which is really the essence of what we're trying to demonstrate Phoenix can actually create. So this way of constructing particles using these various vertex types does simplify the standard model. In other words, we can produce the standard model with a much smaller building block system. In other words, the standard model as it exists today has about 61 particles to it, 61 fundamental objects. And that's a hefty set to deal with. However, Phoenix, as we've just seen, actually only has 10 actual building blocks to give you all of the particles that we can observe, and even dark matter that we haven't observed, but we know exists because of its gravity. So in this way, Phoenix names every possible particle in the way that the periodic table of elements names every possible element and the properties before the samples were ever obtained. In other words, this is basically a periodic table of fundamental particles. So you already know the standard model periodic table, and this is it. And what we want to represent here is how do you designate the down, the strange, the bottom, which are these -1/3 quarks, and the up and the charm and the top, which are the +2/3 quarks, and the the electron neutrino, the muon neutrino, the tau neutrino, as well as the electron, the muon, and the tau, and this wonderful inner circle of the photon, the gluons, the Z vector weak particles of the Z naught and the W plus and the W minus, and most of all, the Higgs particle. So we've overlaid here the systems or the graphs that actually constitute these particles. And what you'll notice, for example, when we go through the quarks, is that what allows a quark, in our case, our graphs, to actually constitute a quark are the number of vertices that are associated with it and the type of loops that are actually on the vertex. So for the down quark, there's only one loop. For the up quark, there are two loops. And what makes these higher generation quarks is very simply how those original single vertex systems like the down and the up connected to other vertices. And when we look at the neutrinos, we find that those actually constitute entirely measurable real particles. But what allows you to have higher order neutrinos is that they're connected to more and more what we call gamma vertices. And the same thing with the muons and the tau and the electron. And as we notice in the middle, the same thing with these force particles. That what makes the force particles either different from each other or bigger versions of each other are the number of gammas, these vertices that connect in three ways that are attached, or how the loops and the arrows are actually differently attached to each other. So, and then the final representation, the Higgs, is this wonderful photonic-like structure that actually has a very interesting quirk to it that we'll get to later on when we talk about gravity. But the idea is that that particle is what allows these particles to actually have something we call mass. And again, that's just them purely on their own. So we can represent the standard model very nicely, very easily, and with all of the right features. So that's what brings all of this together. So Phoenix shifts how we look at fundamental particles. It constitutes, this idea that particles are really building blocks, which we are all very familiar with. However, the building blocks are actually a lot easier than anyone has ever represented before. And that ease of these particles being represented allows us to do some very simple graphical representations and matrix representations that we will basically show in later presentations. You'll be able to calculate all of the characteristics of these particles. But the idea is that these particles actually show not only the same notion that we understand with the standard model, but they also show how these particles that are built from them give rise to the same transformations of particles in nature. Let's see. An important artifact here as well, and we've been saying it from the beginning, is that we can demonstrate why dark matter is such an overwhelming feature of the universe. One of the simplest ways of saying it is that in our construction of particles using these vertex types, when you create asymmetric graphs, those asymmetric graphs tend to be not very reactive. And because of that, they constitute dark matter. But we will go into showing how we can actually reconstruct why only 5% of the universe constitutes visible matter and why 25% of the universe constitutes dark matter. And then inevitably, we'll talk about what dark energy is all about on top of all of this. And that's really what's next in terms of presenting to you guys what Phoenix is. I think that, so we've covered dark matter, but one of the funny things that we haven't talked about, it hasn't been enough time, is that there's also something called dark photons. And what a dark photon represents is what happens when dark matter meets dark antimatter. So you would expect that since everything's dark, whatever photonic system it actually produces is equally dark, which seems to be a little bit of a controversy, but we're not the first ones to actually present something called dark photons. There have been various physicists, and we'll present that hopefully in the next presentation, who have come up with a whole, what you might call, periodic table of dark photons and dark matter systems. But what's also equally important to us is that we have an ability to map out antimatter and then something else called negative energy. Now, of course, what's important in this conference is not just what constitutes matter, but one of the critical questions coming from, for example, the Alcubierre warp drive is the idea of how does one make negative energy? And so we will talk about that hopefully in the future if you guys invite us back, because I do understand how critical it is to the understanding of at least the Alcubierre warp drive. And then something that's also fundamentally important is this idea of neutrino oscillations. And it's one of the sort of big modes of understanding when it comes to particle physics, because it's still, we can measure it, but we're not exactly sure where in the standard model it's really emanating from. It's still a very big question, just like antimatter on some level. And so we always offer the idea that we need help. There's still a lot of work to be done, and also monetary help. The idea is that a lot of this stuff is done on a volunteer level. And so our doors are open for anybody who wants to volunteer time, and we can sort of walk through and teach these fundamental ideas and raise you to where we are currently with Phoenix. There's still quite a need for help in moving our project forward. And we'll be forming a new website. We already have the website, but we're still building it. And it's called phoenixtheory.tech. So hopefully by fall, we will have a construction out there so that everyone can come in, dig in, find out some stuff, learn a little, and hopefully want to contribute a lot. So without further ado, we're up for questions, and hopefully we have some substantial answers. So let's just open it up.
Wonderful. Well, before we do that, so Ken, thank you again. Let me stop your share here real quick. And I want to put this on gallery view. Everyone, please put your hands together for Mr. Kenneth Briggs. And we also have Drew here with us. Thank you, sir. Thank you very much. And actually, so Jeremy has his hand raised first. Jeremy, go for it, sir.
Please.
Hey, Ken, thanks for that presentation. I had a couple questions.
Yes, please.
It was great that you showed the standard model and, a little bit about, the particle, some more particles, what the graphs look like, then showed how to take the graphs and put them into the matrix form, and then showed kind of how you get these particle interactions that we get, we see in the typical particle accelerator experiments from these matrices that you get with this whole graph formalism. But I'm still unsure how you get things like charge, like where does particles charge come from? Also mass, where does the mass factor into the picture? Like charge and mass. Why don't you start there?
Okay, great. Those are fantastic questions. So generally in Phoenix, the way that we talk about charge is using the loops and the arrows, right? So the idea is that every vertex either has, loops, arrows, or some attachment to another vertex. And so what we call the tadpoles, the loops and the arrows, how you count them, that's what constitutes charge. So now the question becomes, how is it that 3 loops somehow is magically a -1 electrical charge? Or for that matter, why 5 loops actually constitutes a +1 charge? So there's a linear relationship between the charge of a particle, how we constitute charge in regular modern physics, and the number of tadpoles that our graph has. So that's a linear relationship. So that linear relationship is how we get there. So the question is, okay, so what is this other thing where you're using tadpoles and loops? That actually is called hypercharge. So there's a construction of the weak nuclear theory that uses this idea called hypercharge and relates it to something we call charge, how we measure charge. And so what we show in Phoenix is that the hypercharge mechanism is what Phoenix is actually using as tadpoles and arrows, but there's a direct linear relationship to regular charge. So again, if every particle or graph that has 3 loops on it always has a -1 charge. Every graph that has 5 loops on it, so no matter what it is, if it has 5 loops on it, it is always a +1 charge, right? Same thing with the antiparticle. So if it had 3 arrows on it, that would be a +1 charge. If it had 3 or 5 arrows on it, it would be a -1 charge, etc. So we're showing that there's a linear relationship between something we call, physics calls hypercharge, and the charge that you expect these particles to have. So that's the relationship between charge. Now, when it comes to the mass, The way Phoenix talks about mass is that we talk, and something we talked about actually in the prior presentation. In that prior presentation, we talk about cyclic charges. And what that is if you take the matrix, right, the matrix construction, and you take its trace, which is you just add up the diagonal of that matrix, then that thing that you've just calculated is what we call a charge. That's the number of tadpoles and arrows that are associated with that graph, right? So if I take the matrix and I just add up its diagonal, the diagonal itself of that matrix is telling you all about the number of loops and the number of arrows. And so adding all of those together gives you the total number of loops and arrows sitting on a graph. And that's what we call the charge, right? The electric charge or the hypercharge. If I take that same matrix and I square it, and then I take its trace, I get another conserved quantity about that system. We call that the spin. If I take that same matrix and I cube it, and then I take its trace, I get another conserved property. And that's what we call the mass. So the idea of what constitutes these other conserved properties of a particle are very simply stated in Phoenix as taking the matrix of that graph and then finding these higher order powers of it and then tracing them out.
Okay.
And yeah.
Drew here. Hey everyone. If I may, we can say these graphs we're looking at essentially contain this connectivity and information and the signs of what we saw, the loops and arrows. We know, as we saw from the presentation, we can represent that as a matrix. Essentially, a transformation on that matrix and successive transformations essentially yield these integer characteristics, which are lockstep with the characteristics of the physical particle. Is there's probably the way to wrap that all up, I would say.
Thank you, Drew. I appreciate that. Yeah.
Drew, if you want to keep going, that's good, or I can skip through a couple of questions I'm seeing in the room.
Yeah, well, and Drew, I would love to have you share. You've been relatively quiet, and that's totally fine. But yeah, I would love to have you share more.
Yeah, Ken, it looks like we've someone kind of made a reference to, oh look, this is the hieroglyphics, which we can presume that this is, people can look at this and say, oh, interesting. It seems like this is we're just naming particles, and that kind of makes sense. But we can also share and go into what's going on more deeply. And I can tell you as a computer scientist, when you can represent a framework with a fewer lexicons, smaller pieces, and have it cover more and say more, that's not a rewriting of it. That's a profound re-expression of it in a fundamental way that informs on new things. Sure enough, this same, we went through kind of fast in the beginning, but the implications of being able to enumerate and express different kinds of particles other than the natural ones that we see certainly has profound implications. And Ken can go into that more on specifics.
Well, now, if I could interject, and so Avatar Ang just pasted this into chat, and this is what folks had asked. A few folks had asked this the last time. He was wondering about predictions, and I think predicting new phenomena would be the best, or leverage would be amazing.
Yeah. Ken, would you mind if I went into? I could go into the muon electron. We would go into that on a surface level.
Sure.
And then there's the dark matter part, which we were sort of been teasing around here in this, which is appropriate for subsequent ones. But I'll do both of those briefly. So the first one is, as some may or may not know, in the LHCb, right, there's an open discrepancy right now. There's the ratio of electrons produced versus the ones a muon produce. The standard model predicts a 1-to-1 ratio. Yet what's coming out is around 0.75, 0.8 kind of ballpark, and there's been increasingly convergence in that kind of neighborhood of that ratio. Well, Phoenix can actually explain that precisely in that exact neighborhood. And that's basically a product. If you look at the muon particle and the electron, and you saw some of those reaction diagrams, if you look at the particle, what's going in the experiment, and you perform the sort of numerical permutation of all the possible constituents of this thing that they put in, and you come out with all the possible products, and then in two of those bands of products happen to be where you're creating an electron positron, and then muon anti-muon. And so the ones in the experiment, they're measuring the outcomes of those two particular reactions. However, in Phoenix, the ratio of those two products are lockstep with the combinatorial probabilities or the numerics of what is producible. So the ratio of those turns out to be around 0.8 in Phoenix. And the software utilities that we're building around this demonstrates that, and that's sort of in a forthcoming presentation, a lab presentation where we can do this stuff. So that's really quick. That's the Lepton universality one. And then briefly, we'll cover in more in the subsequent ones. The dark matter issue is, dark matter does not interact. But what's really happening, if you really think of these particles as numbers, and that prime numbers correspond to particles that can't be decomposed into other numbers, like by definition of prime, you can start to imagine that the set of numbers or particles that are larger that do not interact with the smaller ones, you can start to see how some of that makes sense, and that the statistics of that, we're working on this model, but the statistics that reflect the ratio of dark matter to visible matter that we see.
That was well said. So with respect to the dark matter stuff, with how we like to represent it, as Drew was saying, is that there are particles that can decompose. There are graphs or particles that can decompose in Phoenix, and then there are graphs that don't decompose at all. And then those graphs that don't decompose, we call them primes. And those prime graphs actually represent fundamental particles. So for example, in Phoenix, a proton is a not decomposable graph, which means that it represents a particle that itself cannot fall apart once it's been created. And what that means is that the proton doesn't decay. And then what that means is that we treat the proton as a prime.
Yeah, and really quick, combinatorically, if you look at the graph of the proton, there's no other way to construct a graph with constituent parts such that you can interchange the pieces and still have all the characteristic traces that you heard about stay the same. Mm-hmm. So this is really the exciting things that we're seeing in this is that the implications of the math and the combinatorics are this beautiful reflection and expression of what we see out there. In the chat, I'm seeing peer review things, and we're absolutely excited to move that along further, and where you're hearing it now. And what helps accelerate that progress is people who want to deal into the project and sponsorships and so on. So if you like it and want to hear more, by all means, please reach out to us. But we're happy to take the toughest questions because it's pretty exciting stuff.
Well, yeah. Now, do you think I think Remy had a question. Can I put Remy on?
Yeah.
Hey, Remy.
Hi Ken and hi Drew. That's a great presentation. What I'm seeing here, first of all, the first impression I'm getting, you've got a much better organizational system for the fundamental particle zoo. I very much like all this graph theory.
Yeah, right.
It's brilliant. And what Drew said as well about what you said it too, Ken, about the conservation laws and how you're taking the trace of progressively higher matrices. I mean, that is so fundamental, and that is so neat.
Thank you.
Yeah?
Oh, by the way, just as an aside, that technique is being used currently with string theory. So if you were to do a little research with first of all, the string theory in the 90s and the string theory today, I'm sorry to interrupt you, Remy, but that technique of taking the matrix and squaring it and cubing it and taking it to higher orders and then tracing it out is a actual technique that we're using in string theory as well.
In that case,
Mhm.
in that case, have you spoken to people like Michio Kaku? I think that's how you pronounce it. You know,
Yeah.
one of the founders of string theory. Have you
Not-
got any sort of synergy, bounced anything off him? Is he picking this up and seeing any parallels?
Actually, no, we haven't communicated with Michio. I think that the core of the sort of the people that we've been looking at with string theory have been people like Douglas Stanford and people out at Stanford University, as well as there's a whole other group out at Harvard University, which are working with the ADS-CFT conjecture. Sorry.
It's about the only useful thing that's come out of string theory, ADS-CFT. It's not a lot there otherwise. There's bits of pure mathematics, bits of group theory, but it
That's
hasn't
right.
made any predictions. So
That's
they're
right.
tending to just protect their field. Keeping outsiders out.
Well,
But,
on some level, what they've allowed to happen is for a whole new, younger stream of researchers to have at it. So, for example, sorry.
No, sorry, I just realised I haven't got my screen on. I'm going to get nagged by Tim in a second.
Yeah, I was waiting to, yeah. Well, because if you don't have your camera on, I get nagged by Mark Sokol. He said, Tim, get that camera on. I'm like,
I already did that in the chat.
see, it's, yeah.
I just wanted to ask you, what you might need is a monograph.
Okay.
Have you? I was given the example with Dirac with his principles of quantum mechanics in about 1928, and it was all very new then, and people were going, "Oh, matrix mechanics, I can't see how it connects with the real world," and now it's so standard. If you could get a monograph together, get it through a good publishing house, yeah. But obviously the peer-reviewed papers as well.
Yes.
Are important. But I'm seeing this is like a Solvay moment. This is something really important. What you're doing, what you and Drew are doing, is really important.
Thank you.
It's just so damn neat. It's really, really neat.
You know, if I could jump in really quickly, and I hope I don't sound, I feel ignorant saying this, but
No.
I know you guys both are from the information technology. When you present this, you are way above my head, but it almost reminds me of it seems like you're applying a form of algorithmic compression to physics. Would that be? And so, but that in some ways, I think that might tend to confuse traditional physicists because they kind of come up with a model and they're like, this is the way things are. But one of the ideas with algorithmic compression is that you're replacing, complex instruction sets with reduced instruction sets.
Yeah.
So.
Yeah. If I may, what really cool thing about this is that we talked about in the muon versus electron. When you look at these graphs, and I've been doing a lot of work lately on encoding and canonicalization. What that means is being able to name a graph as unique versus others. And so a graph that has more sort of symmetry is going to have a lot more sort of group symmetry than others. And it turns out that ties in very intimately with the counting and combinatorics of how these pieces can fit together probabilistically. And the beautiful thing about this model is it turns into this game of numbers and combinatorics and statistics, all with integers. And so that the things that we measure and see are just these probabilistic outcomes out of all the possibilities. And anyone who's in, physics this already rhymes with what we already know. It's just that now this is a way of shifting it into this graph domain instead of the field domain. And a lot of these, like I said, these complexities kind of drop out into a way that things can make a lot of sense. And it's almost as an outsider coming in, a year, 2 years plus ago, as a computer scientist, I remember when I saw the beta minus decay, and I'm like, well, that's just, it was more than just the renaming. Like, this is a renaming. This is a profound statement on the combinations of how things can go together. right? And it's like, oh, that's interesting. And that because, you know, there's just a really cool natural expression, as you're saying, Tim, of encoding and degrees of symmetry, things that are very sort of lockstep and fundamental to the core of discrete math.
Mm-hmm. Yeah, and the idea that a graph that, you know, when you go, okay, that's this particular particle, it's not simply a naming system, because what we can show is that within a very discrete transformation, what we call an orthogonal transformation, that particular graph becomes other graphs. And it just so happens that the other graphs that it becomes meet up with the electron or the proton or these other things. And then when you ask, well, my God, that was a neutron, we could classify that original graph as a neutron because it had two down quarks, one up quark. And then what it transformed into had two up quarks and one down quark, and that's what we call the proton. And somehow these two graphs are actually giving rise to each other. That's not a naming quality, right?
Well,
so when we
it seems in some ways too that this might almost, I mean, it seems like this is the kind of thing that might scare a lot of traditional physicists, and I think they're used to kind of being on the top of the pile in terms of complexity and stuff like that. And the impression that I get, again, as a layperson, the impression I get is you're taking that top of the pile, right, where it's super complex, and you're saying, okay, now we're going to do meta-analysis on it, you know, and which takes it to kind of a whole nother level.
That's right. That's right.
But you know, I should apologize for interrupting Remy earlier. Also, I think he had more questions. If it's okay to put him back on.
Absolutely. Yeah, thanks a lot. Jeremy's put his hand up as well. Oh God, what was I thinking now? Yeah, the first one was the photon. You have two vertices.
Yes.
Electron has one. The electron seems to come out as very, very simple in your theory.
That's
with just the three loopbacks. Photon has two vertices. Why is that, please?
Well, the reason why is because in this particular graph construction, the two vertices, and we'll learn this later on, but these two vertices actually, okay, so the construction element, when one says, well, how do you define the state of this particle? The way you do it is through something we call a cyclic generating function. And the elements of that generating function, it's a polynomial, right? You've got a z squared, z cubed, z to the fourth. It's a polynomial. And the coefficient in front of that polynomial is the trace of the matrix, or the trace of the matrix squared, or the trace of the matrix cubed, or the trace of the matrix to the fourth power. But that's what sits in front of the z squared, the z cubed, and the z fourth, polynomial. Okay, so what's important?
To be frank, I'm not really seeing that, but I'm sort of thinking, what does it mean? The photon is an absolutely fundamental particle, as is the electron. I would have expected it to be very simple in its description, and I would have expected, if I'm getting this all wrong, I would have expected the vertices to somehow be related to the spin. So you would have, the spin is related to polarization.
Yes.
So you would have had, say, for two polarization states of a real photon, you would have had, say, two vertices on, say, a virtual photon. You would have had four vertices.
Yes.
And for a graviton and so forth. But I think I've got the wrong end of the stick on that. I don't think I understand in that.
Okay, so sorry. So the polarization of the photon, if we go to what we call the gamma vertex, it's a single vertex that has three connections coming off of it. And those three connections can, connect obviously to other vertices, but there's no loops or arrows on this thing we're calling the gamma vertex, right? And what we find is that there are four different polarizations of that gamma vertex. And the polarizations in this case is how are they connected to the other vertices. So So it can be connected. One might represent the connection as, maybe information coming out of a vertex or information going into a vertex. And so when you look at the 4 different ways that you can adjust for information flowing in or information flowing in, or
sorry to cut in, but are you saying that by having this connection between the vertices, these gammas between the vertices, you're deriving your spin? Because my question, Ben, is that the electron is just this point vertex with these loop backs. How does that get its spin?
Well, the way we characterize spin is we look at the matrix squared. Okay, so how do we characterize conserved charges for a particle? That's the first kind of a question that you're really asking. That system of conserved charges lives on this thing we're calling the cyclic generating function. It's really a polynomial where the coefficients of the polynomial are simply the matrix, the trace of the matrix for the first coefficient. The second coefficient is the matrix squared and its trace. The third coefficient is the matrix cubed and its trace, etc.
And I can jump in too.
Yeah.
Yeah, and I think what Ken's going towards is we were talking about, and to Jeremy's question, the characteristics of a given graph or a particle are really are one-to-one with this traces integer vector, right? Which is essentially this output of this series or sequence of matrix transformations. And it's that integer vector which is really associated with the physical properties of the particles. And it turns out that graphs that don't have any loops or arrows, i.e. graphs with 0 down that whole diagonal, those have properties that we recognize as conventional electromagnetic energy.
Yes.
And that the easiest formed one is a 2-vertex with 3 edges that obeys all the rules.
That's
and
right.
the fun part that we want to get to later is that, the dark photons and all that stuff is the ability to construct other particles which have photon-like properties because they don't have loops and arrows, but it's because they are not this 2-vertex thing, right? So hopefully that makes a little more sense.
It's beginning to make sense. And just I want to yield for Jeremy, but just finally, just really 3 kind of related questions, if I can remember them. Like 3 related questions. Things like, someone said calculations. Can you predict things like branching ratios and decays?
Yes.
Straight from your graph?
Yes.
Okay. What about a correspondence principle? Can you make a megagraph and say that approximates a classical particle?
Oh,
Could
you,
in principle, do something like that, and then it would then move into the classical world? Can you do something like that?
So the classical particle construct is normally what we would call the field, right? So in particle physics today, we're not really talking about particles, we're talking about fields. And so the question is, how does one construct a field from these discrete things that we're calling particles? And so we demonstrate, in fact, we talked about it the last time when we were talking about integration techniques. The integration technique takes a chunky particle and turns it into a field, right? And that's really what you're talking about. So there's a technique that we would normally call integration that can take this alphabet of particles and turn them into the fields, as well as the field dynamics that we normally talk about in particle field theory. I hope that
would be, excuse the terminology, sort of paradoxical terminology, but that would be a classical quantum field.
Yeah, that would be that would be what I would understand that you're saying is the classical way of talking about particle physics, right?
Yeah.
Or are you saying something?
One step back, because it was quantum field theory with second quantization that made no distinction between particles and fields. They were one and the same.
Right.
Whereas in classical physics, you have fields and you have particles. Yes. So one step back even to that, can you get a correspondence principle to say in the limit this all goes over to conventional classical physics? Can you do such a thing in principle?
Yes, and by virtue, again, for what you're talking about with classical, what we're really talking about are fields, and the fields in particular are sort of our size, sort of gravitational, suns and people, etc. And so I hope I'm understanding that correctly. Versus when we're talking about quantum fields, we're talking about some other set of fields that are a lot smaller. Okay, and then when we talk about our particles, we're talking about these chunky things that don't even exist in terms of what we talk about with quantum fields. But normally the fields that you're talking about are, size us, where we're talking about temperature versus talking about, kinetic energy of a particle, right? So let me just make sure I'm understanding, but by classical, you mean macroscopic?
Not necessarily. It's the
Not
idea
necessarily,
of,
okay.
So like a quantum of action. I mean, you could talk.
Okay.
You could talk
Okay.
about, say, like the Schwinger limit with
Yes.
paired curation.
Okay, so
that's
right,
massive.
so-
That's sort of a massive field, isn't it? It's something like
Right,
10 to the 16 volts per meter.
that's right.
So
That's right.
it's not to do with the size of the thing. It's to do with like the quantum of action, isn't it?
Yeah,
think.
it is. Or the quantum of action, which we can also talk about here, which is what we call our transformation matrix, or the Hamiltonian. But the idea, at least, is that there are, I guess, levels or size scales. So what we're doing here when we're talking about these particular graphs is we're talking about a size scale that is not what we talk about in normal quantum field theory. And so what we're saying is that there's this substrate of pieces that can be assembled as virtual discrete chunks that give rise eventually to field theories that we talk about in quantum mechanics, which then give rise to these higher order fields that we're talking about when it comes to molecules and atoms, etc.
I'm just going to, one more thing, then I'll yield to Jeremy. But
Sure.
People are probably going with the notion, thinking that an electron is made of some loops and stuff like that. It's purely a description. It's a mathematical description.
That's right.
People also think Feynman diagrams no, it's a graph. The Feynman
That's
diagram
right.
is a graph.
It's a graph.
It's a summation of processes to get
That's
from
right.
one point to another. So it's not literally. It doesn't literally mean that, say, you had a rather complicated diagram for a neutron. Say, doesn't mean that somehow in the neutron it's some stick diagram. It's not that.
No.
Thank you for raising that. I want to make that point really quick. That, like someone had mentioned, are these Feynman diagrams? Like, yeah, Feynman diagrams are associated with a process and time and space. Remember that when we introduced it in the beginning, this is a different domain. This is essentially a conceptual, not a conceptual, but a different domain of relationships, and so that the mapping onto the field domain, the time and space, as we're more used to it, is not trivial, but is definitely available and is a process.
Thank you, Drew.
Okay. Well, now if it's okay, so let me go to Jeremy Reese, and then let me go to Will after that. And I'm not sure how we're doing on time.
I've got a quick question too in chat. I can introduce that.
My question's real quick. It's a two-part question.
Sure.
I thought we had mentioned something when you were talking to me before about Phoenix theory, about the loops and arrows being actions or entanglement forward or backward in time. And I wanted to talk more about what Phoenix said about quantum entanglement, the quantum eraser experiment, and what's it called, retrocausality, things of that nature. And then my other question was about dark photons, and whether or not we could make dark photon torpedoes, and whether those would be better than regular photon torpedoes.
Birthday cake.
I love the technology here. That's awesome. Okay, so let me do this. Let me talk about dark photons. torpedoes.
They
That's
would be
really excellent.
invisible. A dark photon torpedo would be invisible, right? So it's a
That's right,
stealth.
that's right.
It's a stealth photon torpedo. And that right there, Jeremy, that's why you want it. It's stealthy,
That's right,
Because
yes.
the regular ones, you can see this coming from like light years away.
That was brilliant. Thank you, Jeremy. So the idea about the dark photons is that, look, we're basically expressing that that these different matter types, in particular, these different graphs that you can construct, some of them are so weirdly asymmetric that they don't break down. And we already know that in Phoenix, they have a counterpart, an anti-particle counterpart. And so when that particular asymmetric graph comes into contact with its antiparticle, of course, it forms a photon. But what that means is that that photon itself is not visible to these other smaller types of particles like electrons or protons or neutrons or whatever. And so, so we know they're dark, right? They don't generally interact with things that are smaller than them or with other types of photons, et cetera. What they do all have in common, the beautiful thing about Phoenix is that everything has gravity. So no matter what type of construction you want to have, it will always yield a gravitational presence. So with respect to your dark photon bomb, the way that you make that bomb really work so that everybody knows that it exploded is that what it would send out is a gravitational presence. You wouldn't see it, but it would rip you apart gravitationally. But the idea there is that it would hold so much gravitational energy, even though you didn't know it was coming, right? And then once it lets loose, it's a ripple of gravity that really distorts all of the other gravitational things with all of the other graphs into, other nonsensical shapes, you might say. So it's a very interestingly brilliant idea. I have to give you credit for that one, Jeremy. Now, with respect to the other questions that you had about time and about going backwards in time or time asymmetry, did I get that correctly, Jeremy? And entangle, thank you. Right, so generally speaking, when we're talking about vertices being connected to other vertices, that's our definition of quantum mechanical entanglement. And we can reveal that at some other point, but what we're saying is that systems of particles like two photons or an electron or two electrons can actually be fundamentally entangled. So what we demonstrate is that this entanglement is actually a property of time. Now, we don't talk about it, we haven't talked about that yet, but what we'll show later on is that there are two types of time that are associated with this entanglement. One is a forward motion in time, and one is a backward motion in time. But what we're saying is that that notion of entanglement being a time-oriented notion also allows us inevitably to make systems go backward in time. So for example, when we talk about a space-time diagram, we've got 4 zones, right? In one zone, you've got matter that's moving in one direction in space and in one direction in time, let's say forward in time. But in another zone, you'll have that same matter moving backwards in time. So we can demonstrate all 4 of these special relativity zones where space and time are distinct from each other by virtue of how they're entangled to each other. And what that allows us to do is to demonstrate how particles can actually move through these different domains of space and time that normally have been separated in a space-time diagram. In other words, in order for you to get from this light cone over here to a backwards flowing light cone, you got to go faster than the speed of light. And what we can demonstrate in Phoenix is that's actually not true. There are many particles that live in those other arenas that we interact with all the time. In fact, we create them in the laboratory all the time. So no pun intended on the time. But the idea is that that Phoenix demonstrates that these various points of normally of a space-time diagram are not actually separated in the way that we normally would like to think that that we're being told that they are, that there's matter types that we're already producing in the laboratory that really live in those other genres of space-time, or in those other quadrants of a space-time diagram. So in other words, there's a lot more that we can do just with the matter that we're dealing with right in front of us, or the matter that we create in our laboratories, like traveling backwards in time. So did I kind of hit an answer to your question there, Jeremy?
Retrocausality.
Retrocausality, right. So the retrocausality is actually a slightly separate thing. So what we demonstrate is that, remember we were talking about in the last presentation, commutators and commutator algebras and all of that stuff? Built into that is a way of talking about how particles either can be seen as I'm the particle and I'm moving, or can be seen as everybody else observing you as the particle moving. It's what we call the swarm, like a swarm of bees that you see from a distance, or how the swarm itself sees itself. Like you're one of the 50 million people in the swarm. The idea is that there are two different ways of doing time in Phoenix. In one of those ways of doing time, we see that things seem to be moving forward or backward according to your perspective alone. In another way of doing time, we see it from everybody else's perspective. And the reason why I say this is because retrocausality is the idea of where that swarm is not looking at time in the same way as you would see time. You're moving through time in one way. The swarm is seeing all of the versions of time. So for it, time isn't just moving in one direction, okay? So the idea is that retrocausality is a technique that we actually use in Phoenix in order to demonstrate why information does come from the future and go back into the past. So the present thing that you're saying, okay, I'm in the present time here, that's not actually, you can describe it that way, but there's a whole other way of describing it where the future and the past are actually influencing you in the now, okay? Where we actually take into account a future thing that's actually penetrating back into the present. And that's the retrocausality that you're talking about. But we haven't given you that complete description yet here.
Yeah. So if it's okay, let me jump in and take it to Will. Where's Will at? Oops. And if he is, there we go. Will?
I will.
And where'd he go? Oh, there we go. Oh, Will, you're really super faint. And there's an echo. No, I can see you, but yeah, it looks like, I think maybe, is your mic muted, maybe? Okay, and I can ask your question for you if you're having trouble with. Oh, okay. So let me mute him back out then again.
Okay.
Okay, I'm sorry about that. Yeah, Will's actually in Japan, so his time zone is way off from ours. Also, I always try and keep that in mind. It's sometime early morning tomorrow his time. So.
Wow.
Yeah, so it's like the middle of his night. So yeah, Will was just asking again, and a couple others had asked also about, again, just drilling down on the practical applications. Like,
yes.
what can we use Phoenix theory to build? How can we use this to modify gravity, create propulsion, things like that? And I know that's difficult because you guys you're dealing with really big ideas, right? And so it's difficult to bring that back down. I think Todd Desiato, he put this in chat. He said engineers like something they can put a wrench around, right? So I think that's part of it. Is part of the audience is saying, how can we put a wrench on this?
Okay,
I thought it was interesting. I just want to cut in real quick. They said the second you square the matrix and take the trace, and that gives you the spin. And then if you cube the matrix and take the trace, that's when you get the mass.
You got it.
So I thought that was super interesting because we have all these experiments like Alzafon and stuff that are telling us that spin is definitely something to do with you know, how to get the gravity effect, and if the gravity is the third order of that, then obviously doing something in the second order is going to, you know, influence what that third order trace comes out to. So I don't know if that has anything to do with it, or am I wrong here?
No, you're not wrong at all. The idea is that that each of these different powers of the matrix, I mean, they're all connected to the exact same matrix, but the idea is that how one sees the interaction of spin able to lessen the effect of the mass, et cetera, et cetera, et cetera. They're completely combined. The best way of well, I'm almost a little, because we haven't gotten to quantum gravity yet, and that's where all of these things get linked. Okay, so in the one case, we're looking at the charges almost existing on their own, meaning the charge and the mass and the spin. They're like, okay, these are just properties of a particle. But when it comes to gravity, gravity has this unbelievable thing where it couples these things together, right? So in one case, you might have the spin being coupled to the mass, being coupled to a Higgs interaction, that all of these things are actually coupled in a very a strange way. But if you know what all of those couplings are, then you have your way of determining what the heck is gravity doing. So the idea is, yes, when you are not just looking at the third order thing, or not just looking at the second order thing, there's a technique in Phoenix for being able to weed each one of these elements out and determine which of the elements you really want to preserve by virtue of a matter type. So you might be using a photon, you might be using an electron, you might be using a proton, et cetera. That each one of these things can be combined in a very how can I say this? In a very particular way, in order to get gravity to do what you're trying to get gravity to do. Yeah, I know it's reaching far ahead into quantum gravity in order to give you this perspective where we actually haven't given you quantum gravity yet, but that's how they're interrelated. Thank you. That was a great question, Jeremy. So hold on. I know that. Hold on.
Yeah, and that goes to the practical aspects too. And so you were talking about, and I know quantum gravity is something that you're hoping to present in the future, right? So
yes, absolutely.
Yeah, I know that we're either jumping the gun or jumping the shark. It go either way at this point. But
I kind of can speak to the turn the wrench thing as well. You know, we want that really bad too, because we are looking to sort of continue to develop this project and get support. And as everyone knows here, and these things, getting those experiments, getting things lined up takes resources and support. And right now we're in this, we're in a couple different phases, but one of them is what I'm leading on the software side, which allows us to do this analysis. I shared one that's the first forthcoming version of the fruits of that will be able to reproduce the muon electron production ratio that the LHCb is. We'll be able to reproduce that ratio analytically from the framework, and like, you know, as I suggested, it's not the 1-to-1 ratio that standard model puts out. So that's one way. It's not wrenches on pipes, I'll give you that, but it's a start on things getting measured, and we consider that a big deal. Another forthcoming one that we're working on now is also the coming up with an approximate ratio of what of essentially particles that would be candidates for dark matter particles, i.e. particles that don't interact with the tiny end of the particle spectrum, we'll say, that we're in. and coming up with something that hopefully should reproduce the 1:5 ratio that we see, the visible to the dark. And in other ways that we'd love to support and able to define, to apply this analytical framework other places. So if you're interested so far, again, this is the kind of thing you can reach out to us and be part of that as well, as far as how we're researching, exploring, and then there's later steps, but that comes when some of the research is more filled in, which is what we're doing now.
Well, now if I could ask, I don't want to put this is more from a conference perspective, right? But so I believe that I have a link to Ken's videos, his YouTube channel up. Do you guys have a website or anything like that so that I could, so basically a way to get people in touch with you without putting your emails in the open, which would be really bad. So.
So we're going to have the website hopefully up at the end of fall.
Or Facebook or LinkedIn or anything like that.
Yeah, Ken, can you drop your email in the chat there?
Yeah, absolutely.
Yeah, and that would work. I never put those up on the open web, right?
So I appreciate that. Thank you.
Yeah.
But please, if you've been hearing this presentation and it's calling to you and you're interested in learning more to deal in, then by all means, I would love to hear from you.
Yeah. Well, and we've got about 5 minutes left. Let me go to Harold Tabarez, and then I think after that we'll probably go back to Mark Sokol. But let me go to Harold really quick. Harold, sir.
Thank you. I have one comment and one question. And the comment is that what you're doing is worthwhile, and I believe you should apply for a grant to the National Science Foundation. They give $256,000 at the first shot. Now, my question is this, speculative,
Yes.
Jeremy Reese asked an interesting question, at least from the sci-fi viewpoint, it's interesting. Now, looking at from an engineer viewpoint, can an engineer look using your theory, let's say, your Phoenix theory, and decide, okay, you want to design a photon that has, like the oil grenade, you put the pin or you press the fuse and it makes two chemicals and boom, explosion. Can your theory, for example, be used to at least theoretically predict, let's say that if you use this, or several of those particles and you combine them, let's say in a torpedo, and it would create, for example, an antimatter, instantly that will annihilate, say, an enemy ship, or that create a gravity wave, artificial gravity or anti-gravity wave or whatever, or a mini black hole, something like that. A speculative can be done with your theory, in which at least, it will make some prediction by combining this particle and that particle in certain way, something that can be engineered into something, either a sci-fi or preferably at the real thing. What are your thoughts?
Oh yeah, no, it's funny because I've been for the last 9 years, we've been looking for practical applications, like what can we actually do with this? And one of, so what you're talking about, for example, I want to bring it back a little bit from the blowing up technologies, but at least, for example, with respect to nuclear energy, right? So we've got a lot of various spin-offs that describe, well, what the heck are we talking about when we talk about nucleons? And how can we describe the periodic table of nuclear matter? And then how do we use that in order to create batteries, for example, to store the most amount of energy in the nucleus that's possible, and then how do you release it, right? So there are a lot of things that we've investigated and that we can bring together in order to explore modern technologies. And so the answer is yes. There's a lot of yes going on with that. In other words, we know how to create antimatter. We know how to create antimatter in a way that it actually amplifies the production rate of the antimatter. We know how to use nucleons in order to store the maximum amount of energy and then how to release that energy. We know how to utilize this new energy carrying technique in order to create, I guess if you want to create an explosion with it, you certainly could, but how to not do that, but in a controlled way, right? So advanced systems of nuclear energy, you might say. But what's been very important to us is how do you create negative energy? And then how do you store that negative energy in order to manipulate, create an Alcubierre warp drive? So that's been a really big zone for us as well, that we've figured out ways to do. So there are some very standard ways of creating negative energy, and then there are some very advanced propulsion ways of creating negative energy. So you have various forms of warp engines that come out of this theory. And then comparing the types of technologies that we can produce with standard ways with what we observe from UFOs, for example. Why is it that that a standard observation of a UFO at night has all of this dancing plasma-like light shows going on around it? Why is there generally a static electric field in the vicinity of seemingly these advanced propulsion systems? Why is there no sound, for example? Another interesting question is why, historically, do we might think that gold might be some interesting, atom that a various UFO might actually give a hoot about? What the heck's going on with things like gold versus any other sort of nucleon of the periodic table? So there's a lot of questions that we can actually answer and address fairly directly when you actually exploit what Phoenix is saying about these fundamental particle types. But it's a great question.
One more question.
Actually, Harold, we're just about out of time. So if that's okay, yeah, let me. Okay. So Mark is getting ready to go again. So let me do this. Let me mute everybody out, and I want to put this back on gallery view. Okay, and I should apologize because we did have lots and lots of questions coming. But everyone, please put your hands together again for Mr. Ken Griggs and Mr. Drew O'Meara. Gentlemen, thank you both very, very much. And I should apologize. We're just pushing up against our time constraints here. So I want to hand this back over to Mark, if I can find him. Here he is. And he's muted.
Okay. I also have another screen that needs to screen share on. I logged in from the computer over here.
Okay, and I can do that. So with this one, let me see.
Okay, do you see that?
I do see that. Okay.
So these are live measurements in pounds. I found the problem in the end. There was a software update with Apple, and the app is no longer compatible. But look, I lift that up, and we're down to near zero. You're just seeing the weight of the sample. And okay, yeah. So we'll start by just pouring the liquid nitrogen in over here. I'm going to make a little space for it. This is the same experiment we were running before, just now we'll actually get some weight measurements. Also, I asked him to keep everyone's mic unmuted. So if anyone wants to ask any questions while this is cooling down or anything, feel free to chime in. Hopefully my microphone's going to be working properly. It's going to take a couple of minutes for this to cool down. It is a pretty large superconductor.
Okay, and Mark, I think I have this set up correctly. So I have spotlighted your video and then spotlighted the Falcon Space Lab. Yeah, that looks right. And so what I'm seeing is, for me, I am seeing the Dewar and your superconductor on the right-hand side of my screen and the weight on the left.
Oh, okay. Yeah.
Yeah.
Yeah, I'm probably seeing something different because I'm the
Yeah.
presenter. You shouldn't see any weight on it right now because I took the mug off so I could actually make the pour. There just wasn't any room.
Now, if I could ask, what is it that you're pouring that into? What's holding the superconductor? There, it looks like actually, it looks like a Chinese muffin, but I know that's
Oh,
not
so what it is it's a foam cup that I heated up and sort of squished it in on itself toward the top. So it's like a cocoon of foam that's surrounding the superconductor. This way, when the superconductor starts to spin,
it won't spin out. Yeah.
Yeah, it'll be trapped in there in a reservoir.
That was what I was worried about because I didn't want that to get in your eyes or your skin.
I'm more worried about these heavy magnets flying off and smashing the screen of my laptop or hitting me in the chest or whatever. Or
Well, that too. We'll have a betting pool about what hurts you worse. No, I'm just kidding. So don't hurt yourself on air.
So far, it was the X-ray microwaves, the X-band microwaves. Yeah, those are not fun. We're getting there. We're not fully superconducting yet. This superconductor is pretty large. It weighs a couple of ounces, maybe like even half a pound. It's a pretty large superconductor, so it takes quite a bit of liquid nitrogen to cool it down properly. See it in from that angle. It's bubbling vigorously. You really don't want to move it while it's in this position because it's getting locked. The field lines from the magnets are getting locked inside the superconductor, and we want to maximize that effect as much as possible so that it really attaches to the disk apparatus. When it's locked in properly, I should feel it. No, not there yet. The plastic is making some scary sounds. I wonder if it's getting brittle from the temperature changes. No, it's not there yet. It's going to take a little bit longer. Oh shit, that's cold. Okay, now we're there. Let's put a little bit more in for good measure. It takes a lot of liquid nitrogen to get this superconductor cooled down. It's quite a large YCBO. Okay, so our weight is stable, and while I was putzing around with it, figured out how to get it in scale measurement in pounds. So we have something to base it off of. Now I'm just going to start off with a simple spin up. We're not taking into account any air currents or anything, so we'll just see what happens when we spin it up. Get a RPM measurement. We're at around 1,000 RPM. 750, 800, 900, 1,000. Shaking pretty bad. Not so sure I want to go much faster than this, especially in this setup. It is shaking quite a bit.
Have you got a spare bar magnet? Spare bar magnet?
Yes, I do.
Is there any way you could try a different orientation? So rather than the sort of plane of the rotation, if you try something more axial or at an angle direct to it, could you try that, please?
You know, if I could offer a suggestion,
the thing in your hand, yeah, the thing in your hand, yeah. Just curious.
I think that I think that. Sorry, I think that Pogklanoff applied an RF frequency to it, right? A megahertz RF frequency, kilohertz RF.
I don't know. I don't have a megahertz RF frequency generator right now. That's coming on Tuesday. I got a couple of those. I'm going to try this as well. This is another version that we thought of trying, which is just to hold that steady. The problem is I'm touching the cup. Oh, fuck. I'm going to need a different glove for this. Try to hold it steady there while spinning it through the field. The issue is the liquid nitrogen is seeping in. It's freezing up the foam pretty well. So you get a frostbite burn pretty fast in this configuration. So you need some PPE to hold it. Okay, stabilize that. Pour a little bit more liquid nitrogen in there just to keep it going. Now, in this setup, I'm going to hold the superconductor steady with the magnetic fluxes flying through it. Let's see if the okay, so the scale measurement is stabilizing.
Sorry to cut in, but you said you've got the magnets moving with the rotation. You said you want to try other scenarios where the magnets aren't traveling with the superconductor. Yeah, if you've got a spare bar magnet, just wave it around, see what it does. Try it in the plane and try it actually, just sort of up and down, sort of over the range of 90 degrees from the
Might be
axis.
something happening, but I can't. The thing is, my hand is too close to it. I might be touching it. I'm confident I'm not seeing anything here.
Try it without the superconductor and also let everything warm up and try it without the superconductor and see if it's just the magnetic field reacting with the cup.
Oh, you just put the magnet on the superconductor on the side. Let's try that.
Because the cold air is changing there because of liquid nitrogen.
Yeah.
Well, you know, Mark, I think if nothing else, this is probably a historic first in terms of experiments.
Yeah. I mean, it's scary. I've had one of these explode before. These things are scary.
Also, without the superconductor there, you need to move the cup closer to the magnets because the superconductor had a flux field pinned in it, which made it fields closer to the cup.
That's a good point. That's about as close as I can get it without adjusting the thing too much. Let's try that. Oh, shit. Here, we can get a live RPM measurement. We're at 1200 RPM, 13, 16, 1700, 1780, 1800, 1800 RPM.
The way you're holding that controller, if you just wave the magnet around like that from 90 degrees to the axis, up to the axis, I'm just curious to see what happened.
1 second. Is this with the cup in place or without?
Yeah. Yeah.
Okay, so let me give myself a little space. So you want the superconductor in the in there, and I'm doing something with
No,
it.
if you could somehow hold it with your hand, like you're holding the controller, and if you sort of rotated the controller so it's parallel with the axis, and if you brought it down perpendicular to the axis, I just want to see the effect of an external.
I got a bar magnet. What am I doing? With the bar magnet?
That's not rotating with it. If you vary the angle, yeah, just curious.
And Mark, with no disrespect to NASA, maybe the problem is that it's a NASA cup because that won't work, right? So you may need a different cup. It could be just that
I don't know, Tony, what do you think of that?
Yeah, that's what I'm thinking. It's bad mojo.
I work for NASA, but I didn't like NASA.
Do you think their cup is cursed too? I have a shot glass. Maybe that'll work.
NASA shot glass. I'm sure it would.
I don't collect
You
NASA.
can feel the domains.
stuff,
It's pretty cool.
so.
Like you can feel the domains here. It'll stick to here, but it won't stick to here. Gets pushed away. Yeah, the domains are in there. They're locked in. I mean, you got to kind of feel it with your hands, but the domains of the setup we have here are locked in place. I'm gonna try this one more time. Try to get those switching domains. See what happens.
Now, was there a reason to try and lock domains into it?
I think that was the way that Podklanov got it to spin. He wasn't using magnets per se. He was using like electromagnetic coils, I believe.
It sounded like he was turned the coils on while he was cooling it down. They were wrapped from the center hole to the outer hole, and so it pinned the field in there. And then he three-phased the coils so they acted against that pinning flux to get it to rotate. That's the way it sounded to me.
Well, Mark, that's an interesting experiment. And right now, I'm sure there's a lot of experimenters salivating like hungry dogs to be doing what you're doing right now.
Well, they're welcome to come to Hawthorne, New Jersey, and join me with Frostbite. I need some better way to hold this thing. It really is. It gets through everything. Cold. But I don't think I've seen anything so far. One more shot. Sort of shaking like a diaphragm of a speaker. And the weight loss that you're seeing is from my finger that I just simply can't get out of the way. Probably to do this experiment properly, you're gonna need some sort of apparatus to hold the superconductor in place. Like a clamp or something. Or actually I have a pair of this might not get stuck to the magnets, but oh, look at that. Okay, that works. Great. Now I could get the human element out of it. stop freezing my hands. Let's pour a little bit more liquid nitrogen on it. Oh. Okay. This is the correct setup that we need. Definitely vibrating. Superconductor, that is. Not seeing any weight loss. Oh, there you go. It's about as fast as it can go. Wow. Any other suggestions? Where'd the superconductor go? Tim, are you there?
Yeah, I'm here.
I think my superconductor went flying with that last spin up. I gotta find it now.
I think this is really interesting. I mean, maybe somebody else has done it, but I've never seen anybody do live superconductor on YouTube before.
We've done it before, but we've actually done live experiments with superconductors.
Oh, well, that is a point. You did the power one, right? Where you blew it up.
Yeah, it wasn't really done correctly, but we gave that an attempt as well. And yeah, when you do it live, you usually show all the fuck ups. And
Mark, what happens if you put the bar magnet in the cup while you're
you want me to stick a bar magnet in the cup?
in the cup? Yeah, just stick it in there.
It'll probably start to spin with it.
Well, the weight should go up, right?
Well, it did.
And then the cup starts to vibrate.
Yeah, now the cup seems to be more.
Let's see what happens.
Well, but if the magnet is vibrating, that's probably going to miscalibrate the scale, right?
Can you hear the magnet moving in the cup, or is it moving with the cup?
It's moving with the cup. I think it's too off balance right now.
It does seem like it's oscillating.
Yeah, let me try to rest that oscillation and see if we can get it steady.
There you go.
Let me get that.
It's the cup. It's jinxed. I told you.
The cup's turning with the magnet.
Yeah.
That's cool. So it's obviously communicating with the cup now.
Uh-huh. Now the magnet's starting to flick around inside. I don't know what just changed.
Well, maybe the flux of the magnet in the cup is pinning to the superconductor. Maybe that's what changed.
Try spinning it, adjusting the rotational speed, and see if you can sync the two.
They're spinning in the same direction.
I hear the magnet moving in the cup.
Yep. Yeah, you can hear it.
So the magnetic field is within the distance of the inside of the cup.
That's right. Well, that's magnetic field.
That magnetic flux should change depending on the speed that you're spinning the disc, because you've got the bar magnets on the disk are changing direction, right? Every 90 degrees. How many?
Every 60 degrees.
Every 60 degrees.
It seems at a certain point it just loses it.
Yeah, so at some point it's in sync, at another point it's out of sync. So there's a phase. There's a phase there.
Yeah, I think it's just the weight of the cup throwing it off.
Yeah, there you go. So if you go slow, it's easier to get, but if you go too fast, it loses it, right?
Something like that. Yeah. Here, yeah. At this point, it's this speed. It's pretty much lined up with it.
Take this cup still and then start it again. So now look, it's like oscillating on its own.
Mark, while we have you on, let me ask about you. You mentioned September 8th.
September 20th, I'm going to be going to that conference, the Interstellar Research Group in Tucson, Arizona. Okay, I'm going to put this away. It's starting to, it's pretty out of balance right now, the superconductors. Anyone have any other suggestions of what to try?
Hey, Mark, is the movement of the cap similar to something like a gravitomagnetic frame dragging? You know, the interaction between the magnet, you know, the superconductor and the cap, the material, the magnetic lines interacting with the cap. Would that be something similar?
I don't think so. That was just the reason why it was interacting with the cup was because we put a magnet inside the cup. Before that, we weren't seeing much interaction with the cup.
So the two magnetic fields are interacting with each other.
Yeah, there's actually several magnetic fields here that were interacting with the magnetic field of the superconductor as it was spinning around, and we didn't see any weight loss in the cup during that segment.
So you're measuring the weight loss in the cup.
Yeah, we're measuring for weight loss in the cup. That's right.
So simply it's pulling down the cap.
Yeah, the cup is on a measuring tool over there. That's hooked up to a computer, which is behind me over on that side. It's a Windows computer, and that's where it's giving us this weight measurement. So if I lifted up the cup, the weight measurement drops to almost zero. That's what you're looking at here. So we want to see how much the NASA Huntsville mug weighs.
Without the magnet, is there any movement in the cap itself?
I didn't see. I mean, you can scroll back on the videos and watch them yourself. You were just watching it with me live, so you can figure that out yourself. But there was also a lot of me touching the cup with my index finger until I got the prongs in place. So there was a couple variables. There was also bits of air current because this thing is not, there's no insulation between the two layers. So there's a couple variables that would affect that. If we did see any weight loss or weight gain, but we didn't really see much. So there's that. And also, this superconducting disk is way smaller than what
Oh, sorry. I think Harold was getting some background noise. Yeah, so September 20th, that's the Interstellar Conference. And I believe that's Richard Obusi and Icarus and a lot of those fellows, right?
It's one second. If I can do a share screen over
So
here.
maybe we can try and do something live from that. I mean, we did test the tech. That would.
Yeah, that would be really cool. Actually, they have a very in-depth program. Like they're doing nearly. They have like a presenter every 20 minutes there, which is pretty amazing that they're able to do that. 1 second. You can turn off the share screen for the weight. Can you do that on your end?
Yeah.
Okay, and now I'm going to share screen over here, and we can talk about the Interstellar Research Group. So
The Interstellar guys are doing their own stuff, so they might see you doing something against what they're doing. So make sure you talk with them first before you film anything.
Oh yeah, I actually was invited from one of the founders of the Interstellar Research Group to come join them.
I have a poster session on Saturday and Sunday there. I'll probably get there late Friday evening or in the afternoon,
okay.
hopefully.
Okay, I heard a couple other people we know are going to be there as well, so it should be pretty interesting.
The NIAC conference got canceled though. That was before that.
Oh, really? That's great because I was didn't have time for the NIAC conference, but they did have. There's like another small session later that said NIAC on it.
Yeah, some of that NIAC stuff that they have in there may not happen if the NIAC people don't show up. So don't know yet what's going to happen.
This is one of the ones I was most interested in is Mark Millis breakthrough propulsion study. Definitely want to talk to him. Again, the Interstellar Research Group is very academic and mainstream. You're dealing with people who are talking about solar sails, stuff that are already being used, or just lots of theoretical stuff as well. But there's not much of the anti-gravity and that kind of talk going on.
Now they're mainstream. If you're trying to do something new and radical, they won't let you. I was surprised they even let me be there this year, but it's just a poster session. And several of the other posters are theoretical, so maybe they're trying to try that out and see what happens.
I'm also excited to meet Avi Loeb, who's going to be giving a keynote speech they gave him a full 40 minutes.
I'm excited I have met so many people who have recommended him and his work. I've just
I think I'll really connect with him because he's an Israeli from Jerusalem, just like me.
He's also, I think he's also open-minded. He seems open-minded and balanced on the UAP topic. And that's something that I think is desperately needed, right?
Yeah, it's definitely something that we desperately need. And I'll try to reach out to the mainstream people and show them what's going on here at APEC, try to get them involved in some way or another. In a way, Avi Loeb's Project Galileo, to look through the telescope and see what's available. How about you have a Project Galileo just looking online and looking at all these patents that have been filed that have never been tried, that claim to, that we already know how these experiments work, how these craft work. So there's another aspect to his project. Also, notice the timeline over here. People are giving speeches for 20 minutes. I've never seen such a packed schedule before. It's really, really intense. Tony, when are you speaking again?
I'm not speaking. They let me do a poster.
Tony, could you describe what you mean by poster?
I get to make a picture that they put on a easel, and I get to stand there and talk about it as people come by.
Oh, okay.
Wait, maybe Mark, maybe you could help him. So when people get close, you grab them and you put it in front of Tony. That's
the plan. Yeah,
yeah. We'll strong arm the conference. Be like, no, you need to see this booth. No, wrong way. This booth. Turn around, sir.
Yeah.
To talk to this gentleman here.
I'm more interested in the people doing posters than I am on the rest of the conference. The rest of the conference to me is just garbage. It's just talking about what you do once you get to a planet. And it's like, well, we haven't even got to a planet. Why talk about this stuff?
Well,
yeah.
So Tony, you're going to be in the what are they had that at STAFE. It's like a presentation, not a presentation area. It's the, what do they call that? I'm thinking lobby. That's not the right word. Exhibits.
Exhibits, yeah, sort of.
Well, that honestly, my impression has been at these conferences, that's where the real excitement is anyways. Because with the exhibits.
Maybe we could do one for APEC. Can you design an APEC poster, like one of the ones that like a 2x4 or something like that, 2 horizontal, 4 vertical? And we could just talk about APEC and get people involved. Try to get more mainstream people on.
No, I'm not going to waste my time on a poster. I got plenty to do.
Oh
You
no,
can
I'm
do it.
always talking to Tim.
Oh, Tim.
Yeah.
Tony, what are you going to be working on there?
It's hopefully it's a more in-depth stuff on my paper I've been writing. I've already got the poster done, which pretty much relates to the paper I've already written, but Sam Reed is supposed to be helping put some more meat into the paper. So I hope the paper that I have there to go along with the poster has more meat to it, but we'll see. Sam's been kind of slow.
Yeah, Sam is the CEO of like 7 different companies and counting.
Yeah.
Yeah, his time is very stretched.
Yeah, I've been trying to get them to help pull a conference together, and it's just hard to get them to do anything, help with it.
For those who don't know, Sam Reed is also sending a satellite to the moon using crypto as payment, Dogecoin as payment. Yeah, so Dogecoin is making it to the moon with Sam Reed.
Once this COVID crap gets done, I plan on flying up there to Calgary, Canada, and visit their company up there. But this COVID's put a stop to everything.
And if I could, I just want to.
Chantel will be there at the conference too.
I'm in the Seattle area, and in Washington State, I'm not sure why, the Delta variant is moving very rapidly, and so it's also like Texas and Florida. So if you're in one of those states, if you're not vaccinated yet, definitely consider getting vaccination. We're going back into masks, and we may be going back into lockdown up here.
I was out at Midland, Texas, back before the Tesla attack, and we drove up there from Midland, Texas, up to Albuquerque for Tesla attack, and stopped by Roswell. I was disappointed that I couldn't find a flying saucer dealership there.
Yeah, they're going out of business.
Yeah, I know.
Mark, I put a couple of poster images in chat. You can take a look at those.
Oh, okay. Sweet. I'll check that out. So anyways, this is what's going on there at Interstellar Research Group. It's at the Marriott Hotel. And they're giving people these 20-minute slots to talk about breakthrough propulsion study, an overview and plan of interstellar mission study with a novel velocity drive fusion propulsion concept. A lot of this stuff is, far out ideas that will never happen. Some of it's stuff that already happened, like the solar sails. There is an overview of NIAC, NASA Innovative Advanced Concepts Program. So hopefully I'll be able to talk to them as well. And
I mean, if we're able to, on that Saturday, if you're going to be there, I would love to do spot interviews like we did for Tesla Tech. On Saturday.
That would be pretty cool if we can set that up.
Okay.
Saturday the 25th. Do we have? We're scheduled for the 25th, right?
Well, we can be actually. I haven't really set a schedule up for September yet, but
yeah, we can. I'll probably grab some interesting people and maybe like 4. Yeah, that's like 5 o'clock, 5 to 7 p.m. Arizona time would probably work. See in the afternoon, and I'll be able to grab some people. I don't know if Jeremy Riss is coming down as well.
are they going to be there in Phoenix? Is that where you're going?
Tucson, Arizona.
Okay. Tucson's actually cooler than Phoenix. It's not as hot.
And it's going to be late September, so things should be cooling down by then.
Well, not in Arizona.
Here, this guy's going to talk about how to get to Alpha Centauri and what to expect when we do. Of course, they're all assuming that it's going to take lifetimes and that we have to worry about, you know, multi-generational spacecraft. So this entire conference is mostly based off of, you know, suppositions that we don't think are true. But yeah, it should be pretty interesting.
Yeah. Yeah. No, I think it will be interesting if you'd like to attend. I would love to do spot interviews. You know, I'm happy to work this end of it if you want to try and do something live.
Yeah, sure will. Is Jeremy Rist here? We were going to talk about Tesla Tech and what happened there. And we also went down to see Roswell, the crash site.
Let me see if Jeremy's still here.
Oh,
Jeremy is.
Oh, Jeremy. Jeremy, can you unmute yourself?
There he is.
Yeah, I'm still here, Mark. I have all my Tesla Tech videos on the other computer. I was just wanted to maybe I don't know. I'm still editing them all down. I want to make like a highlights reel and like a promotion and a thing for next year. We didn't have the turnout at Tesla Tech as we had hoped this year because of COVID. But hopefully next year we can have more people show up to that. It was a pretty cool conference, but again, I feel like a couple people that were going to go and display some stuff held back because of all the happenings and everything going on. So yeah, that was the unfortunate part. But it's still a fun conference, and it was a pleasure to get to meet up with some of you there.
Now, if it's okay to ask, one of the things, and see, I know this because you guys told me, but I think most of the folks in our conference don't realize, after Tesla Tech, after you guys finished doing spot interviews, you bought a bunch of used equipment from the Air Force, and then you went to Roswell. So those were the things I thought it would be interesting to kind of share with folks.
Oh, okay. I actually have a couple pictures that I can show. Let me see if I can figure out how to do the share screen. And here, these are just some pictures that I took on my phone that will upload to the computer. So this was our booth, quote unquote, at Tesla Tech. We got the all propulsion sign up there, and anyone who was building shit just threw it on the table. We got Aiden's stuff over there, and at one point there was this kid playing with Lego. I asked him to make a Tesla coil out of the Lego, and that ended up on our alternative propulsion engineering conference table. It was a Tesla coil made out of Lego. It was kind of cute. This was some like overstock store that me and Aiden stopped by. This wasn't the one that Jeremy's talking about that we went to later. And they just had tons of random shit for sale at like rock bottom prices. And look who I met, Mike Gamble. We were checking out, and there's Tony as well. We were checking out the Gravy Flyers over.
Oh, okay. So those are Russell's Gravy Flyers then. Yeah,
those are Russell's Gravy Flyers.
Neat.
And yeah, this is the presentation room. Looks like here's Russell playing some guitar later. Then I set up this device, the gyroscope contraption with the ping pong balls underneath it. Moved around a little bit, but I think there was a lot of stiction on the floor and it wasn't built properly. We're going to be rebuilding a similar device using much larger gyros and stronger servos. That's going to be coming hopefully in the next month or so. Actually, me and Mike actually had a conversation before APEC. We were discussing servo types and motors and all that kind of, nitty gritty details on how to do it right. It's more, this is the, you can order the DVDs. He still sells DVDs. That's where he makes a lot of the money. And I was taking a lot of pictures with a Polaroid camera just to give everyone a view. And this was the reseller of high-end equipment from like Sandia Labs and Los Alamos and stuff. So during one of the presentations, I was looking for an RF amplifier in the 400 megahertz range, like that's around 30 centimeters. or up to around a gig. And there was only one place in the country that just listed it for sale. They had 6 of them in stock, and it was located right there in Albuquerque, New Mexico, the only place in the country. So I went down there and saw what they had. It turns out they had a lot of equipment that we could have used. So ended up getting some stuff. Here's Aiden Schaefer, Jeremy, and me.
We didn't get any
Brandon
stuff
just-
physically that day. We basically put it on a pallet and we're gonna have it shipped out to the lab.
Right. We actually
but-
went back there again because they had more stuff. that they were gonna bring in.
Those amplifiers that they had, which were in the microwave range that we wanted to experiment in, were built by a custom company called Space International too. I wish I had the video of that right in front of me, but I don't. Yeah, that company was really interesting that we found it on there. The guy said he'd never seen anything like it before, and he thought it was almost a proprietary company that was like right out of Sandia or Los Alamos that built stuff specifically for their equipment and stuff out there. There was a lot of EG&G equipment as well that we found. So like a lot of real interesting stuff that might have been used for all kinds of classified work. Who knows? But
Okay, and this is us in the executive suite. Alien Girl showed up and Russell was playing music. And here's a whole bunch of pictures that were taken.
oh, Brenda was in the chat too. There's Brenda's here in the chat too.
Oh, sweet. Oh, we'll go back to that picture then for a second.
Mark, are those Polaroid selfies?
Oh yes, I was taking Polaroids and handing them out. to
Polaroid
people.
selfies? That's so retro, man. That's weirdly retro.
Okay, and this is Jeremiah Ferwerda, who was working on his Tesla turbine device. And here's the medical marijuana store. They kicked me out for taking a picture.
That's an
here
illegal
is
picture. You're not even supposed to have that.
Oh, shut up. So this is Brent from Kepler, and we were here with the whole Kepler team. This is all the stuff that I purchased. I got a vacuum pump and 3 amplifiers on a pallet. So that's my pallet of shit. And there you can see Brandenburg back there, and Jeremy's interviewing him. So I want to get that footage from that conversation over there.
Oh, interesting. Yeah, that is interesting. Yeah, you can just make them out. Yeah, well, thank you for showing these photos. This is interesting.
And here's the good part. When we went out to the crash site, and we basically just went to these coordinates, and there's like freaking nothing there. It's just rocks and dirt. And there was this like little ditch in the ground, so we assume that's probably related. And we snapped a whole bunch of pictures, assuming that it was the spot. It definitely was within like 100 meters of it. Carry them out, a couple.
You know what? I think I've seen that rock wall in videos.
Yeah,
I think so. Yeah, that rock wall you guys were at. I think I've seen that in videos about Roswell. Yeah, that one.
So it could be we're in the right spot. I mean, there is
no, it's like that low
marking.
rock wall, and supposedly
there's no markings whatsoever, telling you what's going on over here. But
maybe that was the UFO. Maybe it was spoofing, right? Like they were talking about spoof. It was camouflaged as a rock wall.
Could be. I mean, that's this is where the GPS coordinates led us. We met the neighbor who was there, and that was like some real freak coincidence that we met somebody there, because you're in the middle of nowhere. We haven't seen a car in half an hour driving 80 miles an hour down a highway. And then suddenly we reach the spot, and there's the neighbors locking up his gate to the property. And Jeremy, I rolled down the window and started talking to him, and Jeremy caught that on video. So we actually have video and audio of me talking to the neighbor, asking him what's up. And he told us exactly where the site was, or how to get there roughly. And he said there's not much to see. And they took the plaque and moved it to Roswell. So there's not really much there. And maybe it'll become a historic site, but there's nothing out there. There's no utilities, there's no water, there's no nothing out there. Like you're in the middle of nowhere.
Did you try to measure any magnetic fluctuations in the area?
We didn't have any tools with us, no.
I couldn't bring anything on the plane. I don't know anyone out there that has stuff, but it would be nice to go out there with you know, the whole place has been swept clean with metal detectors anyway, and but I was thinking maybe we took a couple samples and I tried looking through them for any signs of nanotech, and I haven't found anything so far. I might send them off to another lab and have them looked at. But again, I really wish we had planned it out a little. It was hard without a guide going out there your first time. So I might put this video together as a guide of just, you know, how to find the site. And
I mean, we had the neighbor. I should have continued talking to him for a little bit, offered him some money to take us to the site. Because that was golden.
Right? We should have capital. That was gold, man. That guy was you couldn't have found a better actor, man. The guy was perfect. He was cattleman.
It was literally locking up the gate as we showed up. And the GPS said we need to go through that gate, but he was like, no, it's over that way. You know, your coordinates are off a little bit.
Yeah, well, I think you guys had a really interesting trip. I think it was a really interesting trip. You know, and like I was saying in chat, you know, I think it's worth it to go there just that you said that you went there. You know what I mean? Even if you didn't, even if you're not tripping over UFO parts, it's still, you know, you could say, hey, I did Roswell, you know, on to the next one. So.
Well, you did the real Roswell. Most people who do Roswell just go to the museum in Roswell, which is many hours away. It's actually closer to Corona than it is to Roswell. But Corona is a nothing town, even today. We did a drive-through of Corona. It has one gas station, and the mini mart in the gas station is the grocery store for the entire town, and it closes at 5 p.m. It's like a 9 to 5 grocery store, one gas station for the entire town, and it's like I think we drove through every single street in Corona in like 10 minutes or something like that.
Oh, okay. Somebody's. You know what? Here, somebody he put up the rock wall. Roswell crash site. He's at, okay. It's on my computer, not yours. Do you want me to share? No.
Oh, I see that.
You see that? That one looks okay. So that's not the same one I was pointing out.
That's not the same one that I saw, and I don't remember these big cactus plants here either.
Maybe the neighbor misdirected you. Was he like dressed in like, you know, all in black suit, mysterious sunglasses?
No, he looked like a farmer.
Oh,
a rancher.
He's like, you are in the wrong place. It is not through this gate.
Yeah, so I was tracing back our steps a little bit too, and just looking at the roads of where we parked and a couple other things. And man, it's so confusing because there's so much land and so much area out there that you can explore. But I think if we weren't at the crash site, we were very, very close to it. Again, I don't know how much is left out there or how much it was really worth our trip, you know, but it was still cool just to go and say we went and to see it, you know.
Yeah, I think it was worth it. It's one of those bucket list things, you know. It's good to do just to say I did it, you know, and so. Well, guys, let me open it up for open discussion now. So let's do that. I think we're just about there. Okay. So actually, you know what? Here, let me put it on gallery view. And quickly, everyone, give Mark and Jeremy Reese a hand. We have photos, experiments, future plans. So you guys went through a lot of stuff. Let's put this on open discussion. And again, anybody, you know, just unmute yourselves as you know, and oh, and I see Ken there. Ken, you have your mask off. Oh, it's only for presenting. Wait, you don't have to put it back on. You don't have to put it back on.
Hey, Mark, Was the Gravity Flyer you saw at Tesla Tech the real working unit or just nothing?
No, that was that was Russell Anderson's attempts at making it work. No, those were not working units. I mean, they spun. That's about it.
Oh, okay.
From what I understand, he's published a lot of information, right? Alexi's put a lot out there, and then other people have tried to figure other pieces out. But from what I understand, you have to kind of go around and collect all that info and bring it together. It's not really in one place.
Yeah, I think the main issue with the Gravity Flyer device is getting a standing wave going on the center disk. And he's using a Tesla coil to do that. And I mean, there's a Slayer exciter circuit for a Tesla coil that allows it to be in resonance with whatever it's attached to a degree. But if you want it to be in proper resonance with the disk, just make a perfectly round disk and find its resonant frequency and vibrate at its resonant frequency as a resonance antenna from the center feed point. And that's what I plan to do with those amplifiers, that the RF amplifiers that are coming in, this coming week. I already cut out the copper discs that I plan on using as the to make the standing waves. And if you get a standing wave, it's basically just a magnetic field in space floating above the disk in one spot, not traveling anymore because it's standing. And if you can then latch onto that, you now have a hook to grab onto space-time with and move along.
Yeah, that is kind of interesting. It'll be interesting to see how that goes. And then more superconductor, sounds like more superconductor experiments, right? So
yeah, I mean, we filled up on the liquid nitrogen, so we gotta get some superconductor experiments going now.
Wait, how much liquid nitrogen do you have? Is it that little? What's enough? So that little container, isn't it?
It's 10 liters. 10 liters.
Oh, okay.
That's enough to run a couple experiments. Yeah, I probably barely put a dent in what I have right now. The thing is that it evaporates on its own. So if you don't use it, even if you didn't take a single drop out of it, it'll be gone within a month or two.
Yeah. But it stays at that same temperature, right? It stays below the transition point. So
anything that doesn't stay below the transition point evaporates out. Yeah, it leaves.
So
yeah.
what's left is still cold after a couple of months. Yeah, that's cool.
After a couple of months, nothing's left. That's my point. Hey, Mike. Are you excited for our gyroscope experiment? Mike, you have to unmute.
Oh, Mike. There's Mike. Okay.
Yeah.
Mike, welcome back, sir.
Well, I've been sitting here. I've been doing some calculations, heading in that direction. I'll get you copies here as soon as I get it all prettied up.
So, Mike, were they a wreck at Tesla Tech? Because they look, they tried to cover things up, but I mean, I don't know. It looked like they were partying pretty hard there.
Well, I was only in on a little of it. I did present there, and that went fairly well. They had some technical problems when they first started, but I pitched Saturday. So by the time they got around to Saturday, they had most of the bugs worked out, but it got off to a rocky start.
How many, do you have any idea what the attendance was for your presentation?
My presentation, maybe 50 to 80, somewhere in there.
Okay.
I think total there was like 150, 170 people there. It was down about half of what it usually was.
Yeah.
Normally it's like a couple hundred, 250, somewhere around there. They usually pack that place pretty good.
That's surprising. Yeah, that you kind of surprised me. I mean, I went there back in like 2004, 5, something like that, and I think it was like 600 people one year.
Yeah, yeah. When they used to have it at the other hotel there when I first started going for Boeing there, and yeah, they'd pack the place.
Yeah.
But,
Well, still, it's
this COVID has kind of put a monkey wrench in there.
you know what? I think it's good. My wife had her projects she's doing too, and I've been telling her the same thing. I'm like, this is just me, but you know, it's right now in the summer, things seem kind of quiet. I'm like, get out there and do it. Have fun. Do the conferences, do the stuff. I'm not positive, but I have a feeling that we're going to spend this winter hiding again like we did last year. So
Well, if you live in Washington, they just clamped down on this place.
yeah, we're masks only. We're up at the border. Yeah, we're up in Blaine, masks only.
Yeah.
And our daughter is not going back to school. Even last week, I thought she was, but we just hit a new record for cases.
Yeah.
So my wife, she just showed it to me. She's like, she's not going back to school, and I'm like, how can I argue with that?
Yeah. Homeschool is taking over in this neck of the woods.
Yeah. So yeah, it'll be interesting. Well, you're down. Are you in Issaquah? No, you're
Puyallup, further down yet.
further south. Yeah.
Yeah.
Well, it's not as population as dense down there.
Well,
Right.
it's still thick in here. So, we get the tail end of Seattle and Tacoma, which everybody's moving out of there over here.
You guys had the fair too.
We got the fair starting here another week. Yeah.
Oh, yours. Okay.
I'm just
Okay.
up the hill from the fairgrounds.
Yeah. No, I've been to Puyallup a couple of times.
Yeah. Yeah, and then getting ready for winter and got to butcher the beef and all the farm chores, get the place ready for winter. Speaking of that, when you want me to pitch again?
Well, it's up to you, sir. When would you like to?
Well, I'll go once a month like we were doing, whenever you got a schedule there.
Okay. Well, yeah. Let me make a note then. Let me make a note. Yeah, I'm pretty mellow. I don't know if you probably didn't hear, but I got my in fact, I took the whole family down. We got flu shots yesterday, and I just read that flu shots, I would not consider it an alternative to COVID vaccine, but they did a study that shows that flu shots apparently help a little bit with COVID resistance. And then the other part, the reason that we got them is I didn't want to drag our systems down with the flu and then have COVID sneak in, right?
Yeah.
So we did that, and I don't know if it's the vaccine or what, but that flu shot I woke up, I just feel beat up today,
Well,
I woke up looking for the guy who punched me out. It was one of those.
Well, I had to do some work overseas in that, and I went down, and before I went over there, I had to get a whole bunch of shots, and in order to go overseas, I was headed to Taiwan and that, and I got about a half dozen shots, and they didn't mix very well. And yeah, the boss, I got back to the shop, and he says, "You look more dead than alive."
Yeah. I mean, I guess that can happen sometimes, but the flu shots are out though, just so you guys all know. And I just read an article. It wasn't a doctor, but it was somebody saying he was recommending the same thing. He said it's best to have the flu shot. Just try and get as immune as much as possible. Build up those immunities. For a lot of folks, flu shot's free. If it's not free, it's only usually $20 to $40. So probably worth doing it. And then this Delta thing, again, we just hit new record for Washington State. So.
Well, they're going to milk that, Delta plus, and they'll just keep going that as long as they can. Name of the game is lock you down.
Yeah. I mean, I think they'll do it as long as they think that they can get away with it. Then the question is how long can the economy take it, right? How long can people take it?
That's the second point, is to run the economy in the ground and make everybody dependent on the government. I mean, you got these eviction things going on now, legal battles on and off about evictions because nobody's paid the rent for a year.
Yeah, I had a lot of quiet time last year. I got back to work a couple of months ago. Actually, it's probably been closer to 4 months now, but
Depends on what you're doing for work. During the whole pandemic, I was working a lot because construction's considered what do they call it?
A vital industry?
Critical critical work. They want to keep building houses.
I thought you were teaching, Michael. I thought you were. I thought you were teaching.
No, I'm an archaeologist. I watch people dig.
Oh, so you were doing? Wait, you were doing construction?
Yeah, well, it's archaeologists nowadays. They're not like Indiana Jones. They're watching a backhoe dig a hole and make sure they don't dig up your relative.
Oh, okay.
We're not looking for dinosaurs. We're looking for people.
Yeah, well, and you're in California, right? So there's a lot of indigenous. I'm sure there's a lot of indigenous stuff that you have to kind of watch out for and protect.
Well, it's not just that's called prehistoric. There's historic stuff is also, I mean, you've got the Spanish and then the Mexican period, and then after 1769, that's when the Europeans first came to California. Alta California, that's where the first mission was built. So that history only goes up back to 1769 in California. But there's a lot of historic stuff. Remember, the gold rush happened. And then the next year, California became a state. So, I mean, things go, there's a lot of history around. And so when I'm watching them dig, I'm looking for both stuff. I was working on a project, it's called Middlebury Institute in Monterey, and found a bunch of glass and stuff. And then when the boss was going through all the materials that I collected, she showed me this bottle. It was the bottom of the bottle and it had the 1852 stamp on it, on the bottom of a bottle. So yeah, there's a lot of both. And for as far as the prehistoric stuff, you know, if you were going to be living anywhere in the Americas, I would think you'd want to live in California. There were supposedly over 1 million people living here before the Europeans showed up. And then after 200 years, it got down to like 15,000. So.
Yeah, I'd heard a lot of that was, what was that? I just read something new about, there was a pandemic that came through California, came through the US, right? Came through the New World. And then, but there's been debate for a long time. They said that this was from the Spanish, right? That they basically, they accidentally introduced all this disease that went out in front of them and wiped out indigenous peoples.
Yeah, they would bring people that had smallpox, they'd give them their blankets.
That was later, right? But
what if the native people were killed by
and plus rats on the ships that came, you know, created like a major hazard.
But the biggest thing that killed the native people was slavery. There's a book, if you ever are interested, called The Other Slavery, and it's about the history of the enslavement of the indigenous people of the Americas. The Spanish were really bad for that. And what they would do, like the island that Columbus landed on, Espanola, when they treated him as a visiting chief, and all the people came out and greeted him, and the chief of the village showed up, and he was like putting a big party on for him. And the first thing they noticed is he had a gold ring in his nose. And when they saw that gold, that was it. It was over for them people. And within 10 years, there were not original native person was left on that island.
Yeah.
The first 2 years, they sent 4,000 women and children to Spain to be house servants. So, and the men, they sent them off to work in the silver mines on the mainland. So yeah, it's a pretty brutal history. But the Americans were even worse. Like during the gold rush, they just slaughtered people. In fact, in 1850, when California became a state, the governor petitioned the Congress for $2.1 million for all the heads and scalps of the murdered native people. And in 1853, they got it. So, I mean, it's not like you read about in the history books, although I like history.
It's a checkered history. We'd call it a checkered history. That's the polite version.
Well, but it's really interesting because it shows, it has a lot of our culture that we have today is built on all that stuff that happened back 100 years ago. So
yeah. Oh, that is interesting.
I mean, we're still paying for it, and different geographic location where it's an Indian reservation camp, or the taxation. Some of these places have free tax just because paying penance back to that dark part of history.
yeah, that's true. Yeah, they sent a lot of one of the other things they did is they would take the native children and send them off to these boarding schools where they basically would punish them if they spoke their own language.
Yeah, they
kill the Indian to save the Indian.
I know. Well, and this is open to sky. I know we're going way off topic. My wife has been following that too. There's one up in Canada. Have you read about that one, Michael?
Yeah.
Yeah, and that one was really bad. That was
all the graves they found.
Yeah. Well, no, and this, like thousands or something like that. Yeah, that was.
That's part of the problem with our culture is we don't deal with that trauma and we pass it on to our kids. So it's really the best thing to do is to talk about it and deal with it so we don't do it again.
Yeah, no, it was an interesting presentation that you did. Yeah, so
And
I just got yelled at because it was too far off our topic.
Modern day is as grotesque as the a couple of 100 years ago. How people were. The ideologies changed. Now we read it as a story. We don't read it as a lesson that to learn from, not to do. Because I think we've a little bit more have evolved from that.
Yeah, but things are changing, don't you think? Things are getting better. I think people are more open to talk about it.
I think also, and Michael, this would go to your psychology. This would go to the intergenerational trauma. One of the things my mother has said this. She keeps telling me on various topics. She's like, you have to remember, psychology is a part of our culture today, and it wasn't, right? Like even 50 years ago, not much. 80, and so you end up with stuff like we still have abusive marriages, we still have child abuse, we still have kids beaten with a belt, stuff like that. But the thing is that years ago that was just normal, right? It's like that's the way it is, and now that we have more therapeutic, it's just become more a part of our culture, and so we're still like that. Maybe it happens, that's not right, and here's why it's not right, and here's how it'll affect people. So.
Well, I think it affects, like I've said before, I think it affects this whole area of contact with other species and civilizations. I mean, if they see us killing ourselves over stupid stuff, I would tend to think they would want to stay away from us because we're too dangerous.
Well, that's a good point. Yeah, I mean, you got to ask. Yeah, you got to ask. I mean, what's ET going to say? I mean. Look how they treat each other.
It's like your topic of that you were talking about with the nukes and how they were dealing with the nukes. I don't think they were doing that to be aggressive. Do you? I don't think they were trying to harm us. They were probably trying to save us from ourselves, don't you think?
So I have to read more through Robert Hastings' work. Again, the thing that really surprised me was, I caught that from Luis Elizondo as a passing comment. There were two things that I caught as kind of passing comments. I thought, these would be interesting to read up on. One of them was the travel through water, the Transmedium. And then the other one was the nukes. And I thought, well, that one's a little easier in some ways. So I figured, hey, maybe I'll find 2 or 3 stories, because rumors always have a basis. I'm like, and I knew about Rendlesham and stuff. I was like, and I hit 40 and I was like, okay, that's, I was like, I got to stop. It's too easy. And then
40 is a magic number in statistics.
Well,
when you get 40 data points, that's enough to do statistics with a confidence of 5%. So you can, you can do statistics with 40 data points. I learned about that when I was doing testing, but the point is 40 is a significant, statistically significant number.
there's a pile. I mean, Robert Hastings, and now the challenge with Hastings is anecdote and story versus like substantiated, right? And it looks like a lot of his stuff is well substantiated, but it's also, you've also got like anecdotes, right? Like, you know, Bob says he worked security at this base and he says they saw this, and it's like, well, how credible is that? And I saw kind of a mixture. But the thing that did get me was, even though the way I looked at it was, even if half of the material in his book is just, you know, myth or legend, that still leaves possibly hundreds of additional cases. And so that what I came away with was this feeling that there is absolutely an interest in nuclear devices. And honestly, just reading through all of it, the only thing that popped into my mind was curiosity. I didn't really sense any hostile intent. I didn't really sense that, you know, a lot of people say they don't want us to blow ourselves up. That's why I don't really get that feeling. I just get the feeling it's more like curiosity. Like, what are these people doing? You know? And I don't know.
What's messing with there?
Could be. Yeah, I mean, it very well could be that. You know, one of the things I'd wondered was, you know, these craft, I'm sure they can detect neutrinos, right? If they're super advanced vehicles, all of your nuclear assets would give off neutrinos, even despite shielding. So maybe it's just really obvious, you know. Maybe the reason that they're around nukes is because for them it's like a light bulb in the dark, you know.
Well, it's interesting because it goes back so far. It goes all the way back to the 40s, right? As you showed data all the way back to like 45.
Back to the beginning, it looks like, yeah.
Yeah.
And every major, I noticed a few.
Interesting though is if you look at the technology that they used with the missiles and stuff like that, I mean, it's really primitive electronics like switches and relays and stuff like that. So like a magnetic relay, you could hit it with a certain kind of energy and make it turn off, right? And really, when we're talking about disabling a nuke back in the 60s, in the 50s, that's all it took. All it took was sending a magnetic pulse to the right area, and it would switch off. And basically, their sensor, all it was looking for was a dead short or an open. And you open it up, and all of a sudden, all your nukes are disabled. Okay?
Yeah, I mean,
it was a lot easier to disable our weaponry back then and is now. But then there was, like, when we were developing radar, obviously that disrupted their technology somehow. That's why we had crashes. That's why Roswell probably happened, was because we were hitting their technology with this really high powered radar system that you wouldn't sit next to one of those radars when it was running.
Well, it could be, and you know, again, Mark's stuff is all microwave frequency, right? So radar's microwave frequency, so it's possible that if you have a propulsion system that uses that, then it doesn't have to turn it off, right? It just has to knock it far enough out of kilter that it doesn't work right anymore. You know, gravity does the rest. So
yeah, right. Or it could be like lightning hit it. Lightning is the same kind of thing. It's a high energy pulse. It's it's high frequency.
Yeah, it's interesting. The other thing I noticed from digging in, and again, I don't have the expertise that most people do on this. I mean, who are into it, but I definitely did see the way that this information, not as a suppression, not government suppression, but like, okay, you have a bunch of airmen that see something, they file a report, and in several of these, you hear the investigator come out, the investigator be like, okay, the first thing the investigator thinks is, well, I'm out in the middle of Montana and these guys haven't seen anybody for weeks, so the first thing he's asking them is, how much do you guys have to drink, right? And so the problem that I see there is, on a case-by-case basis, it's pretty easy to dismiss it. And then there's this thought of, it's not very often that somebody like Robert Hastings comes along and looks at all the different cases. And the military, even, you know, most of the time, I mean, these things, again, for us, we can say 1967, 1965. For them, it's been 2 years, you know, and back then, right? Then they didn't have the internet and stuff like that. So something may or may not have happened a couple of states away. It's a rumor kind of a thing. So they handle them one at a time. And they're like, well, this is kind of weird, but what can we do about it? It's already happened. Nobody got any photos. Okay, you know.
Well, I think a lot of that has to do with our national security system. Back then, I mean, when I was working for Hughes, hell, you couldn't leave a folder sitting on your desk.
Yeah.
Or else you could get arrested. Right?
It's very well, it was that World War II holdover.
Get arrested, right?
Yeah. Well, Mike's in my chat window. Mike, you probably had that at Boeing too, right?
Oh yeah.
I can tell you some good stories about hot packages.
Oh yeah, they had all these file cabinets and stuff where you had to like fill out a log book and then you had to take it, and then when you were done, you had to fill out the log book then, and then you know there were 2 locks, or not just one, but 2 locks on this box. Okay, if you had to walk across the parking lot with something classified, they gave you this metal briefcase and they handcuffed it to you. Okay, that's just to walk across the parking lot. So you know that every little document that was generated, they still got it and they know what's in it, because that's just how there's, if they didn't know there was a problem, that meant something got out.
Yeah, that was.
I think they like the drama.
These guys are antiquated, but in reality, they still got all that information. I'm sure it's all still there.
Well, no, isn't it? Don't they? Well, from what I've heard, that's the thing is, so they handcuff you to walk across the parking lot so they don't lose any. But the minute it turns 7 years old, then they take it out back and burn it, right?
Well, it depends on what it is, right? If it's now, one of the things I noticed is a lot of these secret programs were secret because they just didn't work, and they didn't want anyone to know they were a piece of crap, and the government was getting gouged. The taxpayers were paying for something that was useless, and that's why they made it secret, because they didn't want anyone to know that it was garbage that they were working on, and there was billions and billions of dollars spent that way.
like in World War II when they trained the bats to carry, was it they trained the bats to carry fire bombs to the Japanese belfries?
Oh yeah, and remember the Japanese had the balloon bombs.
Yeah. So the Nazis are building UFOs, and that's the best we got, is exploding bats.
It's all over the world. We're not the only ones who waste money.
Yeah.
We're just good at it. That and breaking stuff. That's why I think Roswell was one of ours, because it broke.
Well, it was interesting. So hopefully today went pretty well, guys. I hope, seems like things went pretty well.
You can't expect aliens to travel trillions of miles through the universe and then get killed on Earth by microwave ovens.
Exactly. But us, on the other hand, we break stuff all the time. That's how we learn.
Well, I'm gonna wrap it up on the live stream here, and we're dropped over.
I gotta go.
Yeah, I think. Well, I
fun.
mean, it's pretty quiet now. Yeah, why don't I shut things down too then? So why don't we call it a day, guys? Thank you all for attending. Hopefully we did well. And
yeah, I really liked your presentation, Tim. I thought that was timely. So.
Well, thank you. So
a lot of good information there. A lot of things that we know. I am glad I saw your presentation. It was wonderful.
Thank you. Okay, well, let me let you go then, guys. We'll
a
shut
lot
the
of
conference.
interesting things.
We'll shut the
Sorry,
conference
a lot
down for
of
this week,
interesting
and I will get another one scheduled, and we'll do this again in a couple of weeks if you're all able to.
Awesome. Sounds great, man. Thank you all for watching, and thank
That's
you for
great.
the super chats and everything else, man. Thank you. Take care, and we'll see you at the next one.